All right, we're going to move into our next Domain 3 security engineering topic, which is the application and use of cryptographic features. Quite an extensive discussion that we have here to discuss cryptography, all aspects of cryptography. So cryptography is really one of the cornerstones of the concept of the CIA triad, right? There are a bunch of different cryptographic controls or cryptographic processes that provide the means of availability because they limit access to particular systems. They provide us the ability to do multi-factor authentication, essentially denying unauthorized access. Not to say that cryptography will prevent against things like distributed denial of service attacks and so on, but there are some aspects of cryptography that do apply to the concept of availability. Most certainly, though, many aspects of cryptography that apply to the concept of confidentiality, right? Being able to hide a message, typically by using some form of encryption, whether it's symmetric or asymmetric encryption, and we'll get into the significant differences between the two a little bit later on in this section here. And then also providing the ability for message integrity, ensuring that whatever message is being generated and delivered hasn't been altered or otherwise misused along the way to its destination. So we'll talk about various cryptographic functions, encryption features. We'll talk about various integrity mechanisms. And then we'll also talk about different types of cryptanalysis attacks, how we can protect against those different cryptanalysis attacks, and of course look at all the fundamental aspects of cryptography, well, some advanced aspects as well throughout this section here. Cryptography's been around for quite some time, actually. Now, in the past, we have seen the use of cryptographic features, using physical assets, right? So, for example, the SciTel that we see here, which was a tool used as what we call a transposition cipher. A transposition cipher, we'll see this definition a little bit later on, is really just a method of encryption where the positions that are held by the plaintext get shifted according to some sort of predictable, well, I wouldn't say necessarily predictable, but at least known system, so that the ciphertext will constitute some sort of variation or permutation of the plaintext. So as an example, we take a leather strap with letters burned into it, and we have a wooden dowel, and that dowel has a very specific shape, and we wrap the leather strap around the wooden dowel, and because that wooden dowel has a very specific shape, it reveals the message that is wrapped around that wooden dowel, and the key in this case is really a combination of where the letters are on the leather strap as well as the wooden dowel itself. All right. Now this is obviously an example of a basic cipher, but the rod allows us to write letters around the circle, and the plain text would get translated somehow based on whatever mechanism it is that you're trying to define. Decrypting that message is just a matter of having that ciphertext say, okay, every fifth letter will appear on the same line, so the plain text becomes, whatever it becomes in this particular case. All right. That is an example of one confusion technique that we use. There's transposition ciphers. There are substitution ciphers. There are basic concepts of mathematical calculations, modular math, and we'll take a look at that when we look at the Reindel algorithm a little bit later on. So we had this kind of mechanical, cryptography phase, the Enigma machine, the cipher disk, red-purple machines, and so on. The idea is that we were introducing some form of randomization, which was our cryptographic function, and then we had to have a key or some knowledge on how to decrypt that information, which became the crypto variable. In the past, these types of ciphers, these mechanical ciphers, were very effective because we didn't have computers, we didn't have computing power, and it was very difficult to, unless you understood what the key was, it took time to analyze and identify how these ciphers worked and how you could decrypt the information. All right. Now, obviously, we don't really see too many mechanical ciphers these days. We're more in the modern era, so we are typically employing the use of mathematical functions to perform cryptography. And we'll take a look at some of those mathematical functions throughout this section here. Now, we are also kind of getting into an era of where we are looking at physics as well. Most cryptographic systems today are based on the concepts of mathematics, but we do see with the introduction of quantum cryptography, particularly with QKD, quantum key distribution, using photons and the properties of photons to distribute keying material so that the keys can be much more, distributed much more securely. We'll get into that concept in a little bit here. So modern crypto systems operate essentially so that anybody with a computer can use cryptography, perform cryptographic functions, advanced mathematical functions, and so on, so that we can transmit and send data in a secure manner. Most attacks against crypto systems are actually typically not a weakness in the algorithm. The algorithms are actually, surprisingly enough, and this is why one of the reasons that I go through the operations of the Reindel algorithm. The cryptographic functions are relatively basic, relatively straightforward. But if you don't implement the cryptographic system securely, you can introduce weaknesses in the implementation, not necessarily the design. There certainly have been weaknesses in specific algorithms. We'll talk about some of those weaknesses and how they were addressed later on in new algorithms that have been developed. But the first thing that we're going to do in this section here is kind of go through what the concept of cryptography is. We'll take a look at all of the different definitions of cryptographic features and so on. What is randomization? What is transposition? What is a crypto variable? How is that crypto variable utilized in the cryptographic process? What is the difference between a symmetric cryptographic process versus asymmetric? What are hashing methods, and so on. When it comes to cryptography, some of the newest developments in cryptography is the use of physics rather than mathematics to perform a cryptographic function. Quantum cryptography, little bit of a misleading term because we're not doing any encryption with quantum physics or quantum concepts, but we are doing key exchange, specifically with something called QKD or quantum key distribution. Quantum key distribution is a way for us, or a secure method, that uses or implements a cryptographic process of key exchange utilizing quantum mechanics. So basically it allows the two parties that are communicating with each other to produce a random secret key that's known only to them, which then can be used to encrypt and decrypt the messages. I think you guys would agree that one of the key elements, no pun intended, but one of the key elements to any cryptographic system is the crypto variable. That crypto variable is the key itself. So, quantum cryptography is kind of misleading in this case because we're not really using quantum mechanics to perform all of the cryptographic tasks. We're just simply using this for key distribution. One of the unique properties of quantum key distribution is that it provides the ability of the users, we'll call it Alice and Bob, A and B, that's why we call them Alice and Bob. We see that referenced in a lot of documentation, want to be able to share or communicate to each other securely. But one of the challenges that has always existed in cryptography is, how do I share something secret without having a secret channel for the purposes of creating a secret channel, right? It's a chicken or the egg type of concept. How can I create a secret channel that is guaranteed to be secret, in which I have to share private information, but the channel's not secure yet, if that makes sense. And that is where key distribution and the process of key distribution comes into play. Now, that's been addressed in traditional mathematical cryptography with the use of things like Diffie-Hellman and other mechanisms for the distribution of keying material, the public key infrastructure, making use of private and public keying material, and so on. But in this particular case, we want to be able to come up with a method of detecting if there is a third party trying to gain knowledge of the exchange of that keying material. We'll call that third party Evil Eve. So we have Alice, we have Bob, and we have Evil Eve. Okay? Now, there is a fundamental aspect of quantum mechanics. The process of measuring any quantum system, and in this case it would be the photons that are being utilized, their polarization and whatnot, being utilized to measure the key space. If it is viewed, and I'll get into the details of this in a minute, but if it is viewed by Evil Eve, that disturbs that system. So any third party like Evil Eve trying to eavesdrop on the keying material must have to measure it, must have to view it in this case. And then that would introduce a detectable anomaly, meaning that we're able to identify that somebody is viewing the keying material, and for that reason, we can then identify that keying material is suspect. We use something called quantum superpositions. I don't want to really get into that, in quantum entanglement to identify the quantum states. In this particular case, the transmission of photons. Again, I'll break that down as simple as I can over the next couple of slides. But if the quantum states of the material that's being exchanged has not been viewed or has not been disturbed, then we can recognize that as well, ensuring that we know that the keying material has not been intercepted. All right, and in that sense, the key is guaranteed to be secure. The eavesdropper, Evil Eve, doesn't really have any information about it. The security encryption that uses quantum key distribution relies on the foundation, and this is why it's called quantum cryptography, of quantum mechanics. If we're looking at traditional cryptography, like public key cryptography, or even symmetric cryptography, we're basically just doing everything with mathematical functions. There is no proof that the actual complexity of reversing those functions has been done. So it indicates that quantum key distribution provides that level of guarantee. Okay? So let's take a look at the process here and see if we can kind of break it down in a simple enough method that that is kind of easy to understand. Like I said, I don't really want to spend a lot of time going through this because it's not really covered on the exam, but I did want to introduce the concept, all right? Within quantum cryptography, there are two unique channels. One is used for the transmission of the quantum keying material via single photon light pulses. That is the physics piece. The other channel carries the message, which is the cryptographic function, which is traditional encryption. That's the mathematical piece. So just be clear, we're only using this BB84 protocol. BB84 is a quantum key distribution scheme. Was developed in the middle of mid-80s, I think, and has pretty much been adapted and used even today. But as I stated, within the laws of quantum physics, one photon, if a photon is observed, its state changes. So we can identify that. Quantum key cryptography is perfect for security because if somebody tries to eavesdrop, it will cause the disturbance of the flow of those photons. So in essence, the quantum algorithms are much more secure. Not to mention, by the way, key space can be much larger. Keeping in mind, of course, we are still using the same traditional cryptographic methods for encryption. So generally with symmetric algorithms, if it's a 256-bit algorithm, it's going to have a 256-bit key. It's only when we get into the asymmetric algorithms where key space gets expanded quite a bit because of the mathematical principles of asymmetric cryptography. It is theorized that quantum factorization can factor a number 1,000,000 times longer than what's used in RSA in 1,000,000th of the time. We'll talk about factorization a little bit later on. Factorization is a concept that is primarily reserved for asymmetric encryption. We don't typically see factorization in symmetric algorithms, but we'll talk about that concept of factorization a little bit later on. Okay? So as I mentioned, these two gentlemen, Bennett and Brassard, in 1984, published the first QKD protocol called the BB84 protocol. And let's kind of see if we can break down how this functions. So the sender, Alice in this case, and the receiver, Bob, have some sort of quantum communication channel which allows these quantum states to be transmitted back and forth. In the case of photons, this channel is maybe an optical fiber, or it could be free airspace, open airspace or whatnot. In addition, they also are communicating via a classic channel. Well, they could be communicated via a classic channel. The protocol, just like any other cryptographic protocol, is designed with the assumption that the eavesdropper, that's why we call that person Evil Eve, because eavesdropper starts with E, and Alice and Bob, because we're trying to get from point A to point B, can interfere in any way with this quantum channel and we would be able to identify that, right? Whereas in traditional cryptography, with classic channels, we would have to authenticate that channel. All right. Now, this is where it gets a little bit complicated, because we are talking about physics, and I'm not a physicist, but I'll try to explain this as best as possible. But let me talk about the third bullet point here, Heisenberg's uncertainty principle. I always think of Breaking Bad when I read that. But Heisenberg's uncertainty principle guarantees that Evil Eve, the eavesdropper, cannot measure the photons that are being transmitted back and forth between them without disturbing those photons in a detectable way, which reveals the presence of that eavesdropper. All right. Now, if you're looking at the diagram here, we're essentially encoding the information in what we call a non-orthogonal orthogonal state, which means that we now have to define orthogonality, which is basically just a generalization of kind of the definition, if you will, of the perpendicularity, not of 7 red lines, but the perpendicularity and the geometry of the state of whatever it is that you're trying to measure. I'm not really explaining it very well, but you can see from the diagrams here, we represent different binary values based on the photon's polarization and whether or not we're using a rectilinear basis, which means that we're going to have a 0 degree and 90 degree representation, or a diagonal basis where we have a 45 or a 135 degree representation. All right. And again, the Heisenberg's uncertainty principle guarantees that we can't measure those photons without disturbing them. That's called quantum indeterminacy, right? Again, I'm not going to try to define that. I think we have a good enough understanding. So we have those two pairs of states, and they are essentially conjugate to each other. The pairs of the orthogonal states are referred to as a basis. All right. The polarization state pairs use either the rectilinear basis, which is the linear polarization or plane polarization of the electromagnetic field, if you will, which is a vertical of 0 degrees and a horizontal of 90 degrees, and the diagonal basis of 45 degrees and 135 degrees. Any of these two bases are can represent the values, right? So 0 degrees, 0 degrees on the rectilinear scale. I think that's actually, that diagram is wrong. I thought the 0 degrees represented a 1, and on the rectilinear scale, and this one right here, I'd have to look that up, but I'm pretty sure that this is correct. 45 degrees represents binary 0, and 135 degrees represents a binary 1, but I'm pretty sure that this should be a 0 and this should be a 1. We'll have to take a look at that some other time. Again, it's not really important that you understand the details about how this works. I think it's really kind of more important to understand, just theoretically what it is and functionally how it may work, how it allows us to share crypto variable information without the concern that that crypto variable information is being intercepted in some way. All right. Yeah, that's going to bug me though. Hold on one second. I just did a quick search, and it seems like there's just a couple of different representations of that. The diagonal basis is there doesn't seem to be any confusion. On the rectilinear basis, there seems to be different representations. So we'll go with what's on here for now. But I think that maybe perhaps this is a more modern representation, but the original specification on the rectilinear scale at 90 degrees was a 0, and a 0 degrees was a 1. Yeah, we'll move on, right? Again, the main thing here is that you kind of understand the general principles. And if you're interested in learning more about quantum key distribution, certainly go out and research it and take a look at it. All right. So anyway, the first step in this quantum transmission process is that Alice needs to create a random bit. Could be a 0 or 1. And then she needs to randomly select one of the two bases, either rectilinearly or diagonally in this particular case. So we select a random bit. Each bit then is then encoded randomly based on that rectilinear or diagonal basis. She then generates or prepares the photon polarization state depending on both the bit value and the basis. So for example, a 0 is encoded in the rectilinear basis, which is often represented with a plus symbol as well, again, that's the discussion, right? Is it a vertical polarization state, or is it the horizontal polarization state? But we'll say the vertical polarization state in this particular case. And the 1 is encoded in the diagonal basis as a 135 degree state. So then we transmit that single photon in the state specified, the one that we created, to Bob using that quantum channel. Then we just simply continue to repeat that process from that random bit stage. Alice is going to be recording the state, the basis, and the time that each photon is sent. Okay? Now, ultimately, and this is the whole concept of security with quantum mechanics, it is not possible to measure or distinguish between the 4 different polarization states because they're not orthogonal. The only possible measurement is measuring in a rectilinear basis, giving us either the horizontal or the vertical. Now, if the photon was created as a horizontal or vertical, meaning the rectilinear state, then the measure, then this means that you're going to be measuring the correct state. But if it was created using the diagonal basis, then the rectilinear measurement returns, a horizontal or vertical value, right? So, for example, we don't know necessarily how that state was measured. Now, what's interesting is that Bob doesn't really know the basis that the photons were encoded in. All Bob can do is select a basis at random to measure the values, because we have 2 values that are represented. We have 2 1s that are represented, and we have 2 0s that are represented. And we can represent those 1s and 0s in either the rectilinear or diagonal phase or state. So what Bob does is he receives the photons, he records the time, the measurement basis that he used, and the result of that measurement. Okay, again, we're not we're not actually transmitting ones and zeros. We are transmitting photons that are polarized in a specific way, and we are translating that polarization to a binary value. And ultimately, the goal is that both Alice and Bob have a key that they agree on because they use the same measurement basis and they got the same measurement result. So after Bob has measured all the photons, he then communicates back to Alice over that classic channel, that public channel, and Alice broadcasts the basis that each photon was sent in. Bob has the basis that he used, that he measured in. And essentially what happens is they will both compare that, and they are going to discard the measurements where a different basis was used. And typically that's going to be about 50% of the message is going to get discarded, or 50% of the measured value is going to get discarded. And whatever's left over ultimately becomes the shared secret key. All right. So let me actually go back here and kind of take a look at these phases one more time. So in phase one, Alice communicates to Bob over the quantum channel. Alice chooses a random string of bits, and each bit is encoded randomly with a particular basis, rectilinear or diagonal. She transmits the photons for each bit with their corresponding polarization to Bob. Bob receives those photons, measures the photons' polarization with a randomly chosen basis, rectilinear or diagonal. Now, if it happens that Bob chooses the same basis as Alice, he's going to measure the same polarization, and he can correctly identify the bit that was originally sent by Alice. With the wrong basis, his result will be random, or at least not comparable to what Alice had sent. In phase two, Bob notifies Alice over that insecure channel that the basis that he used to measure the photons. Alice reports back to Bob if he chose the correct basis or not for each photon, and then Alice and Bob will discard the bits that correspond to the photons that were measured on a different basis. Hopefully, just by going through that again, it kind of makes a little bit more sense. All right. Now, if there aren't any errors, if Bob just happened to guess the basis correctly for every bit, then they're going to have an identical string of bits. And this is what we call our sifted key, meaning that we've gotten rid of the erroneous information and we've sifted out all of that erroneous information, and we're left with the valuable information. All right. Now, if you look at the table here, see, this table kind of represents what I anticipated, which is that on the rectilinear basis, 90 degrees is a 0, and 0 degrees is a 1. Sorry for that confusion. I would have to kind of go back and review documentation to find out why there's that discrepancy. But again, the general idea here is understanding the concept of sharing a crypto variable. Before we're finished, Alice and Bob have to agree on a random subset of bits to compare to ensure consistency. The absence of noise or measurement errors, a disagreement in bits is compared would indicate that an eavesdropper is on the quantum channel. So in essence, that means that, and that's part of that Heisenberg's theory that we talked about, which states that you're not going to be able to view the photons without disturbing the state of the photon, which means that the measurements wouldn't match anyway, and those bits would be removed from the sequence. Because an eavesdropper is attempting to determine the key, they would have to measure the photons sent by Alice before sending them to Bob, not knowing the basis, that should say basis with an I, not bases, well, I guess that would be plural. Not knowing the bases Alice used to encode encode the information, they're forced to guess, and Heisenberg's uncertainty principle means that the info encoded on the other basis is lost. All right. Yeah, I guess that's it. Okay. In essence, that is. I mean, that's kind of the basic description. Certainly, there's a lot more information that we could talk about with this, but you know, how is it being implemented? Is anybody actually using this in a commercial sense? There are actually 6 different companies that offer quantum key distribution technologies, but you know, all around the world actually. Some French and Asian companies. There's even a Russian company and so on. Yeah, that is quantum key distribution. Probably not enough information to completely understand the concept, but it does lead us to discuss what's really kind of critical here. Coming up with a method that provides us the ability to establish a shared secret value that we can use for our encryption process, right? And that's really what we call the crypto variable. That is really the important concept here. And ultimately, that's the goal. And we'll see that is a very common concept with the traditional cryptographic processes as well. Most cryptographic systems symmetric cryptographic systems make use of a private key. Asymmetric does as well. It's just not established in the same way, right? In asymmetric cryptography, we're not ever sharing the private key. The private key is literally held private because we use a different key to encrypt that we use to decrypt, depending on what our goal is of that cryptographic system, whether it's confidentiality or origin authentication, right? We'll get into that a little bit later on. But with regard to symmetric algorithms, we use the same key to encrypt that we use to decrypt. So the parties have to agree on that keying material. Now, unless we're exchanging that keying material, you know, by literally handing it off from Alice to Bob, knowing that it leaves my hand and goes into your hand, there has to be a way of transmitting that secret value, or at least determining that secret value, so that nobody in the middle can understand what that secret value is. So, you know, that's essentially what we're talking about in this particular case, using physics to do that as opposed to using mathematics or some sort of mathematical function like a Diffie-Hellman key exchange process, which we typically will see in a symmetric encryption process. So what we're going to be doing now is kind of getting into what really is important for the exam and for this class, is we're going to now kind of explore a lot of the different terminology and a lot of the different definitions of cryptography, right? We're still going to take a look at cryptographic functions later on, but it's important to understand, you know, what collisions are, what non-repudiation is, what authentication is, you know, what an initialization vector is, all kinds of different definitions that we're going to go through here. Okay, so let's start with non-repudiation. Okay, by definition, non-repudiation means that you just simply cannot deny that you did something, right? There's some sort of method involved of ensuring that you were the individual responsible for taking an action, okay? So, for example, if you purchase something and you sign for it, and later on you're being criminally prosecuted because that thing was used in a criminal action, we have you on camera, we see you signing the document, you really can't dispute it. That is the concept of non-repudiation. Now, in the terms of cryptography, or what we call digital security, there are a couple of different non-repudiation means that are available. One called origin of data, and the other is just generally a function of authentication. Most commonly, the most common method to provide non-repudiation in the context of cryptography, at least, is with digital signatures. And we're definitely going to get into this idea of what a digital signature is later on. I don't want to dump everything on this particular slide here, but basically, it's a tool that provides us the ability for non-repudiation in a verifiable manner, a publicly verifiable manner. We can use message authentication codes. We can use digital signatures and so on, which make use of public key cryptography, private and public keys. Or we can actually use trusted third parties and so on, certificate authority. We'll talk all about public key cryptography or the public key infrastructure a little bit later on. Now, typically non-repudiation is not used in a sense to ensure that somebody doesn't have the ability to deny that they did something. The idea of non-repudiation is, by definition, is that's what it is, but the reality is this idea of digitally signing something or attaching some sort of function to a communication channel that guarantees the source of that information is more for authentication, verifying that the message came from the party that it was intended to come from. But non-repudiation is always something that we discuss when we talk about cryptography. But the third bullet point is really kind of the important aspect of this, providing assurance of who sent the message. Maybe not as much as that the message was delivered to the right person. There are ways to do that. That is not non-repudiation. But we do use digital signatures and public key cryptography, what we call PKI, or the public key infrastructure, which we'll get into a little bit later on. All right. Once a message gets received, what prevents the recipient from changing the message and contesting that the altered message was the one that was actually sent by the sender? Now, there's a couple of aspects to this that we have to discuss. There's the concept of origin and guaranteed, sending party, right? Authentication of the origin. But then there's also an aspect of integrity, providing some sort of guarantee that the message hasn't been altered, which is a secondary function. It's not really non-repudiation. It is the function of message integrity. And we will, of course, talk about that as well, using various hashing methods or hashed message authentication codes, which we'll talk about later on. Non-repudiation prevents this and can be accomplished through the use of public key cryptography and digital signatures. Digital signatures are really just a form of public key cryptography and is verifiable by a trusted third party. That goes into the authentication piece, where we have maybe a certificate authority that is digitally signing a certificate, a public certificate that doesn't guarantee origin, non-repudiation. The public key is never used for non-repudiation. The public key is used for origin identification. Again, we'll have some pretty diagrams, and we'll get into the concept of origin ID a little bit later on. Authentication. Hey, we were just talking about that. The ability to determine that whomever you state you are, we're able to verify that in some way. Everybody understands generally what the concept of authentication is. But in the terms of cryptography, this is primarily done through keys. What's interesting, though, is that the key that's used for non-repudiation is different than the key that is used for authentication, typically. Now, it does depend on the communication channel and how that channel is being used. Authentication, it states here, is not as strong as the non-repudiation of origin. There's a reason why that is. Because when it comes to non-repudiation, I verify my identity by using a private key that only I know. That private key is never shared with anybody. It's never sent out to anybody, and is never publicly made public. Whereas with authentication, typically when it comes to public key cryptography, authentication is done with a public key, which is shared. Now, that public key needs to be digitally signed by a trusted third party, but because it is public, it would certainly be less trusted, or at least not as strong as the concept of non-repudiation, which doesn't use public keys. We'll get into the details of all of this stuff throughout this section here. All right. What is the cryptographic life cycle? Cryptographic functions and implementations have a useful life. And that useful life is typically based on the concept of work factor, right? Work factor is, by definition, how long does it take us to effectively perform cryptanalysis for the purposes of either finding ways to break the cryptographic system or a way to establish the crypto variable, which is supposed to be secret. And typically that would be based on computing power, right? Work factor is just, the cryptanalysis often involves just iterative processes of trying to decipher values based on plain text or known ciphertext or a meet in the middle type of scenario, or just looking for inherent weaknesses in the cryptographic process. So over time, these cryptographic functions, either a weakness is discovered or computing power has become so powerful that the work factor value goes down significantly, and it becomes easier and easier to discover information that's not supposed to be discoverable. Computational power increases, and the ability to analyze cryptographic systems, which is called Crypta Analysis, becomes refined, and the cryptographic system continually gets tested to ensure it still meets the original specified requirements, which is typically based on things like lifetime, the key lifetime, and so on. Any function, any cryptographic function, here they're specifically mentioning a hashing function. We'll talk about that in a minute, but any cryptographic function is no longer effective when the work factor to break that particular cryptographic system is not significant enough to protect us, right? Now, specifically with hashing functions, we'll talk about, again, what the details of hashing functions a little bit later on. Hashing is not really, well, I don't want to say it's not encryption. Hashing functions are typically used for integrity functions. It can be used in conjunction with variables to provide at least some level of authentication, but for the most part, they're used for message integrity. A hashing function is a one-way mathematical function where we take a random amount of data in, or a subset of data in. I wouldn't say it's random. Cryptographic functions are rarely random, because if they were random, you wouldn't be able to undo them, or at least verify them in the case of a hash. We take a portion of the message, a portion of the plain text message, run it through the hashing process, and out comes a fixed length hash value, a message authentication code. That fixed length value is supposed to represent the data. And when I receive that data on the other end, which is received in plain text, if I'm not doing any kind of encryption, I run through the same function and generate the hash. And if the hashes match, then I've verified that the data hasn't been modified. Now, we'll get into more details about how that doesn't really help if there's no secret sauce to the hashing function, and we're just simply using hashing alone. There is no guarantee of integrity in that process, but we'll see that visually a little bit later on. All right, but a hashing function is considered to be broken if collisions occur. Okay, now we'll see the definition of a collision later on, but I'll define it right now as well. A collision in the hashing world is where two different input variables result in the same hash output. And it can happen. It absolutely can happen, particularly with some of the older hashing functions. Collisions were more prevalent. The concept is that if two different plain text input variables result in the same ciphertext output, how do we know which message is authentic, right? We don't. Or if it's considered broken if the hashes can be reproduced in an economically feasible fashion, meaning low work factor. I'm not talking about financially. I mean, there would be some financial investment, I suppose, in tools to do the work. But when they say economically feasible, in this case, they're talking about the work factor. How much time does it take? And then the implementation of a hashing function allows a side channel attack. We'll talk about what a side channel attack is a little bit later on. Encryption systems. Notice how they differentiate that, right? A hashing function is not traditionally an encryption system. An encryption system is considered broken so the encryption system is considered no longer effective if the cipher can be decoded without access to the keys. Now that is exceedingly difficult to do, but you can understand why that would, kind of render the entire cryptographic system unusable. Or if the implementation of the encryption system allows for unauthorized disclosure of any information in an economically feasible fashion. Ultimately meaning that the cryptographic system is not secure in any way. Okay? NIST publication 800-131A specifies essentially what specifies the acceptable use of cryptographic processes. What's acceptable, what is deprecated, what is restricted, what is considered legacy. We'll talk about also something else later on called Suite B protocols, which are the kind of the more modern encryption algorithms and protocols that we can use that are identified to be, somewhat, modern and they can be used, on a in a secure system, I guess is what I'm trying to say. All right. So if a protocol is acceptable, that means it's safe to use. There is no, I wouldn't say no security risk. There's always risk with anything, but no perceivable security risk. A deprecated algorithm you have to accept some risk. So an example might be of acceptable would be AES. Deprecated would be like triple DES. We'll talk about those symmetric algorithms a little bit later on. Almost always, usability has to do with key space, how large the keys are, but not always, almost always. There are other aspects that would make a protocol less acceptable. Weaknesses in its design, potential weaknesses in the operation of the cryptographic functions and so on. Restricted are algorithms or key links that are deprecated. Additional restrictions are required to use those algorithms or key links for applying cryptographic protection on data. I'm not sure specifically what they would define as restricted. I would say DES, the data encryption standard, but to me that would be more of a legacy protocol. If you look at the definition of legacy, an algorithm or key length used to process already protected information, that to me would be, okay, I encrypted this information 20 years ago with this DES algorithm. The only way I can decrypt it is with the same DES process. That's what they're referencing in this particular case from a legacy perspective. So maybe DES would be classified in both categories, both as restricted and as legacy. So if you go take a look at that special publication, you can see how those protocols are classified. So let's talk about a bunch of definitions. Really important concept here. You're more than likely, if there's any cryptography on the exam, you're going to see references to these terms. Plain text or clear text is the message in its original format. Now, some people differentiate. Some people say plain text is the static message in its normal format. Clear text is the motion or the data in motion of the original message in its natural format. But in any event, in either case, it's the message that's not encrypted. All right, so that's typically going to be your cryptographic input, along with the key, of course, but that's going to be your cryptographic input. The ciphertext or the cryptogram is the output of a cryptographic system. It is the altered form of the plain text message. Ciphertext, right? It's what we transmit to the recipient to be decrypted. The crypto system is the entire cryptographic operation. And we'll see this actually. We're going to analyze AES. AES is considered a crypto system. AES is not an algorithm. AES is a crypto system, the Advanced Encryption Standard. The algorithm within AES is the Reindel algorithm, which we'll take a look at a little bit later on. Any crypto system has three major components. You've got the algorithm, you've got the crypto variable, and then you have some way of managing those crypto variables, the keys. Key management is a big concern in cryptographic systems because if the keys are compromised, then the system is not going to be secure. Encryption is the process of converting the plain text message to ciphertext. Decryption is the opposite, converting the ciphertext into plain text using the cryptographic algorithm and the key or crypto variable. The crypto variable is the input that controls the operation of the cryptographic algorithm. Now, I don't know that I necessarily completely agree with that definition. To say that it controls the operation of the algorithm, no, the operation of the algorithm is set. The steps, the rounds of operation, the 11 rounds of operation that we see in AES, for example, is predictable. It doesn't matter really what the crypto variable is going into that cryptographic system. But we do know that the crypto variable is key to the secrecy, right? Pun intended. It is essentially the only thing that goes into the entire crypto system that is hidden, at least, or should be hidden. I guess plain text could be considered to be secret as well. That's kind of the whole point of cryptography. But the crypto variable determines the behavior of the algorithm, and it permits reliable encryption and decryption of the message. Again, I don't really agree with that definition. That was the definition provided by ISC² in their CBK. I don't believe that, and I think you guys will see this when we go into our breakdown of AES later on. But the crypto variable does not change how the crypto system functions. It's just a different element of input data into the crypto system. So you have essentially two inputs and one output. You have a plain text input, you have a key input, and you have ciphertext output. Just about every symmetric encryption process uses that concept. Plain text input, key input, ciphertext output. Now, some employ the use of other variables like an initialization vector. But we'll take a look at that later on. You know, we'll get into the design and so on. What is the algorithm? That is the function for the encryption and decryption. Typically, in the case of confidentiality, it is going to be a mathematical function or a set of mathematical functions. Not always mathematical functions. Yes, we do. We use logic gate functions or Boolean math to do an OR function sometimes. There is some modular math that we might do, but there's also just some substitution and transposition stuff that we do that's not really technically mathematical. It's just another type of confusion. Crypta Analysis is the study of the techniques for attempting to defeat the cryptographic system, to find weaknesses in the cryptographic system, to discover the key. Cryptology is the science that deals with hiding or disguising or encrypting messages. A collision occurs when a hash function generates the same output for different inputs. Collisions are only in reference to hashing functions. There is no concept of a collision when it comes to encryption, only with hashing. Key space represents the number of possible values that a key has. Typically, this is going to be represented as a power of 2 function because we are using binary. So a 20-bit key would have a key space of 1,048,576 values because it's simply 2 to the power of 20. Because again, we're still dealing with binary mathematics, right? Key clustering. 2 different keys generate the same ciphertext from the same plain text using the same algorithm. We'll see later on how that might be applied in modern crypto systems. A hashing function. Hashing functions are interesting. They are considered to be one-way mathematical operations. In other words, they are very easy calculations to do in one way, but impossible to reverse in the other direction. So it's practically impossible to take a ciphertext hash output and somehow reverse that process and derive the plain text. Almost always the only way that you can, there's only really 2 ways that you can, I'll say one way, because a collision is not really the same concept, but one way that you can break a hash, and that's through brute force. Iteratively trying different things to see if you can generate the same hash. Now, collisions would demonstrate a weakness in the verifiability of the hashing function, meaning that we couldn't be guaranteed that the message is not modified, but it might not allow us to derive the message directly. Digital signatures. using public key cryptography, asymmetric encryption, a way for us to authenticate the sender, number one, and also a way for us to verify the integrity of the message, number two, that the message hasn't somehow been modified along the way. All right. And we'll get into the concept of digital signatures a little bit later on. I'm not going to kind of break down each of these in detail right now because the whole point of this section is to go through this. A digital certificate, X.509 certificate specifically, is an electronic document that contains information about a particular organization. It contains cryptographic features like the digital signature of a trusted third party. The holder of that certificate's public identification key, expiration date, serial number, etc. But digital certificates can be used for many different things. But primarily they're simply used for authentication of origin. So a web server might present its public certificate, which is signed by a trusted third party, to the client, and then the client would use that certificate chain, a relationship that it has with that certificate authority, to be able to verify the authenticity of that certificate, in turn then verifying the authenticity of the web server. We'll get into that structure a little bit later on as well. A certificate authority is that trusted third party. Registration authority is somewhat a trusted third party as well that acts on behalf of a certificate authority and performs various functions to kind of offload the work that a certificate authority might have. Issuing certificates, revoking certificates, digitally signing certificates, and so on. All right. The RA is typically going to be used for verification or maybe for some subordinate steps of generating that certificate, even though it's not responsible necessarily for generating or signing the original identity certificate. We'll get into that later on. Asymmetric is a term in cryptographic terms or in relation to cryptography where we use one key to do one thing and we use a different key to do another thing. Now, I didn't mention encryption. That is an option. We can use a public key to encrypt and a private key to decrypt, which provides confidentiality, but we can also use a private key to encrypt and a public key to decrypt for authenticity. So asymmetric algorithms can be used for many, well, at least a couple of different functions, right? Authentication of origin, confidentiality, message integrity, and so on. The term work factor represents the amount of effort that it takes to break a cryptographic system or a function of cryptography. An initialization vector. Now, initialization vectors, we can kind of have a whole different discussion about it without seeing how it applies to, an encryption chaining method and encryption processes in general. It doesn't completely make sense, but I'll read the definition here. It's a fixed size input. So fixed size to me means that it's going to be used in a symmetric process. Asymmetric processes do use fixed key links, but they're just completely different types of math and types of cryptography. We use a fixed size input to a cryptographic primitive, typically required to be random or pseudo-random. Now, whenever I see the term random with cryptography, it always kind of raises a red flag with me, because the whole point of cryptography is being able to do something to get a result, and then on the other side, being able to reverse that function, right? Encrypt, decrypt, encrypt, decrypt. Anytime randomness is generated into that process, it makes it exceedingly difficult to figure out how to undo something. The idea that an initialization vector is random is a little bit counterproductive, or at least counterintuitive, I should say. But we'll talk about why they can be random, because they're not necessarily secret. We'll talk about that a little bit later on. The randomization is going to be crucial for the encryption scheme, because repeated use of a scheme using the same key does not allow the attacker to infer relationships between segments of the encrypted message. Close parentheses. We are going to talk about encryption chaining methods later on. Different block chaining methods that are used in symmetric cryptography. And there are many different block chaining methods. It's kind of iterations, if you will, of the encryption process. Within the algorithm itself, we have different iterations of encryption. But then on top of that, we also run that encryption process multiple times in these block chains, in these chains of encryption. Cipher feedback mode, ECB, there's a bunch of them. We'll get into them a little bit later on. I keep saying that, but yeah, we do have quite a few slides left of cryptography. What they're saying here basically, though, is that those encryption rounds, if you will, not within the algorithm itself, although those are somewhat predictable as well, the encryption rounds with the chaining method that we're using are constant. They're consistent. And without having some random input value, over time, using frequency analysis or some other method, we can start to see patterns, or we can start to see, recognizable traits of a cryptographic process, and then infer from those recognizable traits or those patterns how the cryptography is working, and eventually being able to find maybe a weakness or a way to break that cryptographic system. So by introducing this pseudo-randomness into the process, it makes it much more difficult for frequency analysis and for us to be able to identify those patterns. All right. And we'll see how the initialization vector is used. I'll talk a lot more about IVs later on. For block ciphers, which are typically going to be all your asymmetric algorithms, we use an initialization vector as part of the encryption process, typically in the initial round of encryption, and then the following rounds are based on output data from the previous round. But randomization is required for primitives like universal hash functions, message authentication codes, and the size of the IV is dependent upon the primitive that's used. For block ciphers, generally it's the cipher block size. So if I am using AES 128 as an example, I'm going to have a 128-bit IV, and I will have a 128-bit primitive or cryptographic key. Because it is a block cipher, we're operating on blocks of information. Stream ciphers operate on bits of information. Typically, your symmetric or asymmetric algorithms are going to be stream ciphers, and your symmetric algorithms are going to be block ciphers because they operate on blocks of data at a time. Again, we get kind of into that a little bit later on. All right. Encoding, the action of changing a message into another format through the use of a code, taking a plain text message and converting it to a format that can be transmitted, is usually used for message integrity instead of secrecy. That is true, and we'll see how that gets applied when we break down the details of our hashing processes a little bit later on. Do not confuse encoding with encryption, though. Encoding could be something like a function, a single step within an encryption process. shifting rows or mixing columns, doing transpositions or substitutions. And we'll see that when I break down the Reindel algorithm a little bit later on. Decoding is the reversing of that process, converting the encoded message back into its plain text format. Diffusion is basically mixing things up, right? Through different methods, transposition, substitution, Boolean operations like OR functions, logical OR functions, or mathematical calculations, even applying some sort of modular math, which is the kind of the mixed columns concept. We have shift bytes, shift rows, mixed columns. There's all kinds of different transpositions that we can use, or confusion techniques that we can use to mix up the data, so to speak. Avalanche effect. This is an important concept. We don't want a situation in which I encrypt the big brown dog bit me, and it generates a ciphertext. And then I encrypt the big brown dog bit me exclamation point, and it generates ciphertext that's only slightly different, right? Because if that were the case, using frequency analysis and other techniques, we might be able to infer what the message is. So the avalanche effect basically states that a small change to the plain text input results in a massive change on the ciphertext output. So if I encrypted the big dog brown bit me, I get ciphertext A. If I encrypt the big brown dog bit me exclamation point, ciphertext B, but ciphertext B is significantly different or completely different than ciphertext A. Keep in mind that, literally, we are generating, typically going to be like a hexadecimal output from our plain text input. And we want to make sure that that is different, significantly different, by just changing little bits of the input. All right. SP network. Substitution and permutation, what we call transposition. AES uses the SP network in its function. It has essentially 4 functions internally that it does. Now, the key scheduler and other aspects of the algorithm incorporate other things, but there are essentially 4 separate kind of diffusion or confusion techniques that are used by AES. And 2 of those techniques are substitution, using an S-box, and permutation, using transposition by shift bytes and shift rows. Now, the idea of an S-box is a key in and of itself, albeit static. It's just defined as part of the algorithm that allows us to do one of the diffusion techniques, which is substitution. So now they say breaking plain text blocks into subsets of smaller S boxes makes it easier to handle computations. That's not really what I define as an S box. I suppose technically that is what it's defined as. But when we look at the Reindel algorithm a little bit later on, it'll make a lot more sense what they're referencing in this particular case. Yes, we do break messages up into blocks of data. If it's AES 128, we operate on 128 bits of data at a time, 128-bit blocks. So there is an S-box that's used in that process, but I don't know that I would necessarily call that 128 bits of plain text data the S-box, but that's how they define it here anyway. Okay. Some other terms, transposition or permutation. Transposition or permutation is the process of reordering plain text to hide the message. So we see our plain text message here. Plain text message is hide. And we create essentially our encryption process or our defined transposition process, which is the reorder sequence of 2143. So the H or the I, which is the second position, becomes the first position. The H, which is the first position, becomes the second position, and so on. Very, very simple concept of confusion, but believe it or not, it is still a concept that is used in modern cryptography today. Substitution is the process of exchanging one letter or byte for another letter. So this case, the plain text is hide. The substitution process is to shift the alphabet 3 spaces. Now, I would argue that this is kind of a transposition cipher because we are essentially shifting the letters, but by definition, it is a consistent confusion concept, meaning that that H is always going to result in K, I is always going to result in L, D is always going to result in G, and so on, which is why we call it a substitution process as opposed to a transposition process. Because if I'm taking this plain text in nibbles, basically 4 characters each, and this reorder sequence is being applied, yes, hide would always be encrypted as IHED, but the next 4 letters, if they aren't hide, maybe they're walk or something like that, would be translated into something completely different. Whereas in this particular case, we're simply shifting the alphabet over 3 spaces. Confusion is the idea that we're simply mixing up values during the repeated rounds of encryption. And we'll see the confusion techniques that are used in a very modern algorithm today, Reindel algorithm. Keys get modified each round to provide additional complexity. Those are called round keys. We haven't seen this process yet in the encryption process, where we actually have different iterations or different rounds of operation. We have a main round typically, and then we have, or kind of an initial round, I should say, typically, and then we have our main rounds of encryption. And then in the end, we have our final round of encryption. Depending on the algorithm or depending on how many rounds of encryption we perform, typically the main rounds are all the same processes, the same functions, but each round employs the use of a different crypto variable. Not to say that we're using uniquely different keys every time. The keys are a derivative of our primary key. And we'll see that again. That's why I kind of break down AES a little bit later on, because I think it's important to kind of understand generally how a cipher works. XOR operations, what we call an exclusive OR operation. A lot of cryptographic functions or even really just computing functions use logic gates to perform tasks because we use binary, we use transistors to perform calculations and functions on electrons. So AND gates, NAND gates, OR gates, XOR gates, NOR gates, they're all different types of logic gates that we use in computing systems. But exclusive OR tends to be an operation that we see quite a bit when we're dealing with things like cryptography or other calculations and so on. So we take our plain text data and we XOR it with a generated key stream. In this case, 0111, 0011. Exclusive OR operation is just a Boolean operation in which we take 2 inputs and it's going to always result in a specific output. we see the translation table, or the state table at the bottom right. A 0 and a 0 will result in an output of 0. A 0 and a 1 will result in an output of a 1. A 1 and a 0 will result in an output of a 1. And a 1 and a 1 will result in an output of 0. By definition, that is exclusively one or the other. That's why it's called an exclusive OR operation. Exclusively, if one or the other, but not both, bits are a 1, the output is going to be a 1. All right, very, very simple binary operation, very easy to calculate. And that's one of the things that you'll find with these encryption processes as well. Mathematically, they're very efficient. The complexity is not there. There's just not a whole lot of complexity with these calculations. Even the modular math, where we're using the Galois field and our mixed columns option, or mixed columns confusion step in the Rindell algorithm, is a very simple mathematical calculation, at least for a computer anyway. All right. So this is mentioned, the cryptographic XOR operation, specifically because it is used in most modern encryption processes. What is the work factor? As I stated previously, the work factor is the amount of effort or time it takes to break an encryption system. Typically, this is measured in a unit of time, right? Hours, weeks, days, months, years, and not so much a cost, although typically the more powerful the computing system, if you're using some sort of distributed computing system to combine the resources of multiple computing systems, there is a cost associated to that, but for the most part, it's based on time. High work factor means that there's less of a likelihood that that system is going to be broken because it's just not economically feasible. So, for example, if a cryptographic process takes 1,000 years to break, well, within that 1,000-year time frame, most likely something about that system is going to be altered. Probably most likely the key. So even if I was able to derive portions of that key or portions of the crypto variable, by the time I've done that, that key material would have changed anyway, and I would have to start all over again with the process of decrypting that information. All right, so work factors are required to break cryptographic systems, and that's going to vary over time with the computing power that we have today. We'll talk about a concept. All right, now with algorithms and protocol governance, obviously these are technologies. And just like with any type of technology, we want to be able to assess the risk of that technology, the risk of using that technology, what is the likelihood that that technology can be compromised. So we would analyze these systems. We would implement policies and standards and procedures for implementing these systems, key space size, algorithm choice, chaining method, whatever it is that we're trying to decide. We're going to approve those cryptographic algorithms and those key sizes for operation based on the accepted risk in our organization. If for some reason we've identified that a particular algorithm is weak or not really, doesn't really provide a whole lot of protection. We saw that when we went from RSA 1024 to 2048 recently, within the last 10 years. Then we would migrate from these weaker standards and move into stronger standards. Obviously, that transition can be pretty significant, though. There may be actual additional resources that need to be applied. For example, moving from WPA to WPA2, we had to go from one chipset to another chipset because of the encryption standard. So it's not just a matter of, well, let's just go ahead and start using this algorithm. There may be other considerations that we have to take into account. We also have standards for key management, key distribution, standards for implementation of the algorithms themselves on components, import and export restrictions, etc. So when it comes to governance of a cryptographic system, there are many facets that we have to manage. For example, how do we generate the keys? How do we store those keys? How do we share those keys? And when the keys are expired, how do we destroy those keys, and so on? Also, as with anything, we have to have some sort of auditing and reporting function that encompasses that technology as well. What are some of the issues that we have with cryptography? Number one, cryptography can be misused, right? Criminals like to hide their activities, maybe their communication. That's what WhatsApp does, and a lot of people had an issue initially with WhatsApp because of its encryption, built-in encryption technology. Because criminals want to hide their conversations, they want to hide their plans of world domination or whatever it might be, and cryptography is a good way to do that. Also, cryptographic systems can be subject, and we saw this in one of our previous slides, subject to exports and law enforcement requirements. Remember, cryptography is on the United States munitions list, which restricts the import or exclusively export of specific cryptographic processes or cryptographic algorithms. We also talked about the idea of ransomware. Cryptography is used to facilitate that type of attack where we encrypt information with a public key. And then the only way you're going to be able to decrypt that information is if you have the corresponding private key. Disgruntled employees might encrypt information. And quite frankly, without the key space or the key material, the crypto variable, it would be extremely difficult to decrypt that information. So lots and lots of kind of ways to utilize this tool, which is supposed to ultimately protect us in nefarious ways. And we see it all the time, actually. All right. Countries have specific regulations regarding the use and or distribution of cryptographic systems, primarily to keep cryptographic tools away from criminals. Cryptography is considered on par with munitions and is managed through laws written to control the distribution of military equipment. International export controls by governments are in place to limit the shipment of products containing strong cryptographic functions to trustworthy countries. The United States and governmental agencies like the NSA, the Department of State, the Department of Commerce have restrictions. There are concerns over national security related to cryptography established as technologies are detrimental to national defense, and they need to be controlled through export regulations. And finally, vendors market two versions of their product, one strong encryption and another weaker encryption that might be sold in other countries. I haven't seen a specific example of that. I've seen plenty of times where I get the notification banner that says that this particular product contains cryptographic features and you are restricted from exporting this product to specific areas. But I've never seen where, only a weak cipher suite is included because of those export restrictions. I imagine it exists. I just haven't seen it. Okay. With regard to law enforcement, privacy is a key issue in countries where the culture of freedom of speech and protection from unreasonable search and seizure is a consideration. Some countries, though, have laws that require organizations and individuals to provide law enforcement with cryptographic keys, or they're required to use weak keys or no encryption at all. Thankfully, in the United States, we haven't gotten to that point just yet. Getting pretty close, but we haven't gotten there quite yet. Electronic surveillance is a powerful tool for law enforcement. technological and legislative challenges are finding ways to guarantee that law enforcement has the ability to legally access encrypted information without damaging the commercial viability of that cryptographic tool or civil liberties of citizens. One of the things that I think about, it's not directly related to this, but it's kind of falls along the same concept, is that IPv6, right? One of the issues, IPv6 offers a lot of benefits to an organization in terms of functionality. But what is considered, generally speaking, one of the issues with IPv6 is that it has IPsec built into it. Now you might say, well, that sounds like a good thing, right? I can do ESP and AH in the protocol. I don't have to use a third-party application or third-party software to do it. I just simply use the ESP or AH extension headers in IPv6. But inherently, that means that clients now have the ability to encrypt their own data without any other application or without the need of any other tool. Which means if a corporation has the intent of sniffing data for the purposes of protecting a network or something like that, then that becomes exceedingly difficult when the data is encrypted. So oftentimes vendors will say, or enterprises will say, you know what, we are not going to permit the use of those extension headers. If you do have those extension headers in place, we're just simply going to drop those packets. Not entirely related to law enforcement, but it's a similar concept, right? Some sort of policy enforcement is going to be restricted by the fact that the data gets encrypted and we don't have the means to decrypt that information effectively to be able to do what we want to do. There is a general public acceptance that the use of telephones and mail is protected, and you need a warrant to be able to access that information. So hopefully the same would apply if you're seeking to gain access to encrypted information. There's a general aversion to similar warranted accesses of encrypted communication. Meaning that, yes, I kind of assume that if I am speaking over a phone or I'm sending an email, that there is, at least a minuscule level of what am I trying to say? There's some consideration to privacy in that case. Although I know that, that's not encrypted communications. It's not a secure line. I'm not using SMIME or PGP to encrypt the email exchange. So if somebody was able to capture that, I would kind of assume that would be possible, in other words. But when it comes to encrypted communication, we're encrypting that information for a reason, right? That there's a specific reason why that data is being encrypted, because it's specifically intended to be secret. So, getting a warrant to decrypt that information kind of defeats the whole purpose of the data being encrypted in the first place. All right. So what is the public key infrastructure? We could actually spend quite a bit of time talking about PKI, the public key infrastructure. It is an architecture, if you will. It is not a specific protocol. It is a group of things that happen together, functions that occur together to create this architecture. It establishes different roles, different policies, hardware and software, that would be necessary to create, manage, distribute, store, revoke. Revoke would be a good one. Digital certificates, or what we call identity certificates, and to manage public key encryption. Okay. The whole purpose of this public key infrastructure is to facilitate the secure electronic transfer of information for different network activities. Could be online shopping, internet banking, sending emails, and so on. In essence, it is a cryptographic process that is used when basic security is not going to be adequate. In the terms of cryptography, public key infrastructure is a architecture that binds public keys with different identities of entities. Could be a server, it could be an individual, it could be an organization. That binding is established through a process of registration and then the delivery or issuance of certificates by a specific certificate authority. Certificate authority is essentially just an entity that stores, signs, and issues these things called digital certificates. And the whole purpose of that digital certificate is to certify the ownership of the key, also to verify essentially the authenticity of the owner or the presenter of that key. This can be done with an automated process. It can be done with human interaction or human supervision, and so on. All right. Now, the PKI role that is typically delegated by the CA to make sure that we have valid and correct registrations is called an RA. We don't see a reference to RA on this particular slide, but an RA is a registration authority. Basically, an RA is essentially responsible for accepting requests for digital certificates and then authenticating any kind of individuals or entities that are making some sort of request. All right. By definition, it's just kind of a subordinate, I guess, of a CA to provide identification and authentication of certificate applicants, to facilitate the approval or the rejection of applications, to initiate certificate revocations if need be, under certain circumstances. Could be that some key material was compromised or a business is no longer operational, or something else happened that would cause that certificate to be revoked. But the thing that the RA does not do, it doesn't sign the certificates. It just delegated certain tasks on behalf of the CA. Now, the certificate standard that we use today is called the X.509 certificate. And we'll see an example of this a little bit later on. An X.509 certificate is an ITU standard for the specific format of our public key certificates. And they're used in all kinds of processes. Okay. Now, there are several kind of moving parts to this public key infrastructure. I will try to demonstrate that as much as possible throughout the rest of the section here. But again, like I said, that we could spend quite a bit of time talking about this. Okay. Let's see. I'm just kind of scanning through the bullet points here to see if I missed anything. I think I have kind of most of it, but let me see what's next here. PKI continued, public key certificates. Yeah. So they have quite a few slides on this, so I'm going to kind of go into more detail on this, but the idea of public key cryptography, it provides two functions in terms of its capabilities, right? The whole concept of PKI is to provide a level of trust, right? Now, this can be done through confidentiality, using these certificates to provide encryption, This can be done through integrity, using the certificates to ensure that tamper resistance is in place. And it can also provide for authenticity, making sure that you are communicating or talking to the appropriate individual. The public key infrastructure is this whole system. And again, it's all about creating, storing, distributing, revoking digital certificates, which are used to verify that that particular public key belongs to a specific individual. In the PKI architecture, we create these digital certificates which map public keys, not private keys. The PKI structure provides mechanisms for deriving a private key, but those private keys are never shared with anybody else. So we map the public keys to the respective entity that is supposed to be presenting that key. All right? So we have a certificate authority which issues and signs the digital certificates. We have a registration authority which verifies the identity of entities that are requesting their digital certificates to be stored at the CA. They do other things as well, but that's one of the primary functions. We have a central directory. That's a secure location where the keys are stored and where they're indexed. We have a certificate management system that's part of this, managing things like access to those stored certificates or the delivery of the certificate to the parties that are being issued to. And we have a certificate policy, right? What are the procedures to analyze the trustworthiness of the public key infrastructure, to analyze whether the key is valid and so on by utilizing CRLs or certificate revocation lists, or the OCSP, the Online Certificate Status Protocol. We'll talk about that a little bit later on. All right. But broadly speaking, there are some basic concepts that are involved in PKI. The certificate authorities provide that kind of high level of trust. We create this web of trust. A web of trust is a concept that allows us to establish a chain of trust, meaning that you're presenting a certificate to me that is digitally signed by this certificate authority. I inherently trust that certificate authority, which means I inherently trust you because they signed off, basically. Okay? So the role of a CA is to digitally sign and publish the public key that's bound to a particular user. Now, the way that this is done by using the CA's private key. Let me kind of walk through a scenario here and see if I can't kind of demonstrate generally how this process works. Okay, I've got a web server. This is just one example. This is for authentication and ultimately for encryption as well. I've got a web server that's on the internet, and I want to access that web server from a client. So here's my client. I need to access that web server. Now I'm going to try to access that web server over a secure channel, port 443, which is HTTPS, HTTP using SSL or TLS. Now that web server has on it a set of keys. It's got a private key and it has a public key. Now the private key and the public key were locally generated on that web server. And these are my X.509. Well, it's not specifically the X.509 certificate, but the X.509 certificate is derived from this material. Okay, that's ultimately what's going to be presented to the client for authentication. Now, I could create and generate these keys locally and just self-sign these keys and present those keys to the client. But if they're self-signed, there is no web of trust. There's no trusted third party then there's no trusted third party that's verified the authenticity of the client. So what I would do as an organization is I would take this public key and I would do something called, I would submit something called a CSR, a certificate signing request, to a certificate authority. All right? And it might go to an RA, and then the RA would process the information, and ultimately the CA would sign the certificate, but we can kind of keep the RA out of this process for now. Now, the CA also has their own private and public key pair. Private key is never shared. Public key is publicly shared. In fact, that public key would exist on the client, in the browser, or the storage of that particular client. Either it needs to be downloaded, or it was already downloaded when you updated the software on the web browser. All right, goes into your certificate store, and you store that for future use. So the CA takes that information, and we'll see a representation of the certificate a little bit later on, but they take that information in that certificate, all right, which includes things like a serial number, the lifetime of the certificate, the key material for the client, the web server, other information about the client, what the intended use of that certificate is, etc., etc. They go through some secondary process of screening. Now, ultimately, we're talking about for the use of authentication. If I'm connecting to Bank of America, I need to know that I'm connecting to Bank of America. So the CA will go through some process to say, oh, you want us to digitally sign this key? Well, first we need to verify that you are who you say you are. And that can be done in another channel. It can be done over the phone. It can be done via email, done through a web portal, whatever. But there's some way that CA goes and verifies the authenticity of that web server. Once that's done and the CA feels comfortable that we are in fact signing a key that belongs to a legitimate individual, entity, they will take their private key, running out of colors here, but they will take their private key and they will generate a hash of this certificate, and that hash will be installed in the certificate. So the certificate is sent in plain text, but now it contains this kind of digital signature, if you will, of the CA, saying, I verified this individual, I know who this individual is, and you can trust this certificate. So that certificate then gets issued back to the web server, and that becomes essentially the public certificate that the web server uses when it communicates to the clients. So in this process now, I'm going to send that certificate over to the client, that digitally signed certificate over to the client. That client is then going to verify that signature using the CA's public key. Verifying the hash, decrypting information, whatever it might be. It's going to verify that the signature is valid by using the corresponding public key that was published by the CA. If everything goes as planned, we're able to verify this key, okay? And then based on that, we're able to verify the identity of that web server. This is that web of trust. This is authentication. We're not talking about integrity. We're not talking about encryption. We're talking about authentication. But what's interesting is that I have now a key that I can use. Let me make it green because it's already green on the other side. I have this public key of the web server. So I can actually now use that public key of the web server to go into the next phase, which is to establish a channel for communication, a secure channel for communication. So I can generate a key for communication, and I can take that key and I can encrypt that key using this public certificate. Remember, this is going to be the shared secret key that we're going to use for our encryption, establishing the encrypted channel, TLS, SSL, AES, whatever it might be. I'm going to send that encrypted key over to the web server. The web server is going to use its corresponding private key to decrypt that information, and then ultimately that keying material now exists on both sides of the channel. If somebody were to intercept this encrypted key midstream, they wouldn't be able to do anything with it because they don't have the private key. The only way that you can decrypt something that was encrypted with a public key is to decrypt it with the corresponding private key, which is never shared and never made public. All right. So now we have a shared secret key that we were able to securely exchange, and now we can start to send and receive our data using some sort of encrypted tunnel. Ultimately, public key cryptography is what allows us to generate and manage and share these private and public key pairs, and also to verify the authenticity and so on. So visually, that's kind of in a nutshell what it looks like. All right, it's all about the trusted third party, the certificate authority, etc. Make sense? All right. Now, there are ways that we can revoke keys as well. There can be many reasons why keys get revoked. Traditionally, in the past, we would use something called a CRL, a certificate revocation list, which means that any certificates that have been revoked, we would just simply put them on this list. And when I get a key from somebody or certificate from somebody, I can compare it against the list. If the key was revoked, then even if the certificate shows as valid as far as lifetime goes, because it's on the list, I can simply discard it and say, well, it's been revoked for whatever reason. Okay. The problem with the CRL is that it is somewhat static, I guess. You download that list on a periodic basis, so there may be the potential that the list is not up to date. So they have a new option called OCSP, which is the Online Certificate Status Protocol. It's a way for us, it's RFC 6960, I believe. It's a way for us to alternatively and in real time verify the revocation status of a particular certificate. And you'll see if you do like a Wireshark capture for this transaction, you'll typically see that OCSP, those OCSP messages going back and forth. All right. Now, many other things that we can talk about: decentralized PKI, web of trust, single sign-on, one-time passwords, or temporary certificates. There are many things to talk about. Public key cryptography is used for all types of things: XML encryption, SSL or TLS transactions, like I just described, the bootstrapping of communications through the use of Internet Key Exchange, the Internet of Things, authentication and encryption of email using things like PGP and SMIME, and so on. There's many different applications. There are many different applications for this architecture, and we see it every day. It's definitely something that's used on a regular basis. Okay. Let's see. Public key cryptography is when it's enabled, it's more effective. Let me see what they're trying to say here. Public key cryptography enabled more effective use of symmetric cryptography and greater access control. Yes, I understand what they're saying there. When it comes to symmetric encryption, if you think about the concept of symmetric encryption, there really is no guarantee of origin, because you're using the same key to encrypt and decrypt. So there's nothing unique about the individual that has the key. If anybody gets that key, they could still participate in that process of communication. So I suppose there's a kind of an assumption of privacy, at least. But is there anything that uniquely ties that individual to that key? Whereas with asymmetric cryptography, because we have the private and public key pair, we are specifically tying a key uniquely to an individual. So things like digital signing, non-repudiation, I'm not sure, access control, I guess that's authentication in this particular case. That is uniquely different with asymmetric versus symmetric cryptography. All right, that's what they mean by that. Public keys can be published on web servers so customers can establish confidential communication. Remember, confidential communication is the second step. Authentication is the first step. So if you're only concerned about confidential communication, you don't need third-party signed keys. You can generate your own keys and self-sign those keys, and the other party can simply accept that keying material as authentic, because we can still use that keying material to establish a shared secret key for encryption. It's how you decide to deploy this public key cryptography will depend on what your overall objective is. What if an imposter sets up a rogue web server to redirect confidential communication to an attacker's site? The trusted public directory of keys, where users register with the directory service and communicate securely between the user and the directory, allowing the exchange of keys, or the directory to force the change of keys, would help protect against this, right? Because even if I'm an imposter and I somehow get a hold of your public key, and you use that public key to encrypt a shared secret key, there would be no way for me to derive that shared secret key because I don't have the private key. That's an important concept, very important concept. Public keys are public. There's no guarantee of privacy with a public key. They're supposed to be shared. They're supposed to be public. Private keys are always supposed to be protected and never shared. If, as long as that private key is protected and that private key is private, we should never have an issue with the public key cryptography. So what is an X.509 certificate? It is, like I said, an ITU standard. It's really it's the certificate that kind of binds the identity to a public key using digital signatures. It's going to include things like identity. It could be a host name. It could be an organization. It could be an individual. It's going to include public keying material, which would be an RSA key or a DSA key or ECDSA or even those are the main ones, I guess. And it's either signed by a certificate authority or it is self-signed. When the certificate is signed by the trusted certificate authority or validated by other methods, someone holding that certificate can then use that public key to establish secure communications with another party and providing, almost a guarantee of authentication. Now, X.509 is not the certificate structure. X.509 is the whole standard, if you will. It does define the format of the public key certificate, but it also defines how revocation occurs, how certificates are managed, and so on. How we distribute information about certificates, how we invalidate certificates, for what reasons. It also defines certificate use, and different types of certificates are issued for different types of use, and so on. All right. Let's see. This is an actual picture of the certificate. This has been around for quite some time. I think it was initially created in the 80s, like the mid to late 80s, based on the X500 standard. And we've already talked about generally what the architecture is. Like I said, the certificate that you see here is what's going to bind an individual or an entity to the public key using that digital signature. In the X.509 architecture, there are two types of certificates. The first is the CA certificate, and then the second is the end identity certificate, or basically the endpoint identity certificate. The CA certificate is a special type of certificate that can issue other certificates. It's what we call the top level, what we call the root CA certificate. There are other CA certificates like an intermediate CA or a subordinate CA, and then of course the end entity certificate, which identifies the organization or business or user. End certificates, or end identity certificates, I just simply call them identity certificates, cannot be used to issue other certificates. These are oftentimes called leaf certificates, since there are no other certificates that can be issued below them. All right. If I want to sign, if I want to use a signed certificate, I can use many different options, right? I can send a certificate signing request. That's just basically a message that's sent from the application, from the applicant to the registration authority to say, let's go ahead and start the process of verification. I can use a protocol called SCEP, the Simple Certificate Enrollment Protocol. And I can also use a certificate management protocol. What happens is, and I kind of went through this process when I was drawing my pretty little diagram, is we first generate a key pair. We generate the key pair. The certificate authority does not generate the key pair. This is pretty important because nobody knows the private key. The private key is separate. It's secret. And if somebody else was generating the key pairs, that means that they would have to know what the private key is. The private key needs to stay private. All right. Now, the certificate signing request contains information that identifies the applicant, right? That's the user's identity in this particular case. It also contains, what the intended use of the key is, and other information, right? Distinguishing name that would be unique to that person, and then the CSR might also include other credentials or other methods for identifying essentially the identity of the individual, if you will. Okay. All right, the CSR can be sent to the RA, but ultimately it is the CA that's going to sign that certificate. You can see here that we have a subject, we have the issuer, we have at the very bottom the CA signed by the CA's private key. In essence, this right here is a hash of this information. So we take all this information that's been generated and we use our private key to generate a hash, and that hash goes into this field, and then we verify that hash using the corresponding root certificate or public certificate of the CA. All right. Let's see, version 3, yep. I don't think we have to say much more about this here. What is the key management process? An important part of any cryptographic system is the implementation of key management. How do we issue keys? How do we revoke them? How do we recover them if we've lost them? How do we distribute them? How do we maintain a history so that we're not repeating keys in the future, etc.? KMP, the key management principle or key management process. Kirchhoff's principle, I talked about that previously. I mentioned it very briefly. A crypto system should be secure even if everything about the system except for the crypto variable is public knowledge. And in fact, that's the case. Most cryptographic processes are public knowledge. They're not secret. In fact, many would argue that if the cryptographic process is secret, it can't be trusted because we don't know how things are being accomplished. All right? Does that make sense? The key itself, or the crypto variable, is the strength of the crypto system. The size of the key and the secrecy of the key are the two most important aspects. Size being key space, and of course the secrecy of the key being the privacy of the key. The secrecy of the algorithm, the cryptographic operations that are used in the algorithm, or the technology to protect data cannot be relied on solely, and I would argue actually that algorithms are generally not secret, at least not the ones for public consumption. We know the government has their own internal algorithms that they run that are not published or not public, not made public. Perhaps one of the most commonly used algorithms today, or cryptographic systems used today, is AES, the Advanced Encryption Standard, which again, we're going to spend a lot of time kind of breaking down after lunch. A symmetric algorithm shares the same key between the sender and the receiver. We use one key to decrypt. We use one key to encrypt. We use the same key to decrypt. So that, again, poses the problem, how do I share that key without Evil Eve getting access to it? We'll talk about key exchange processes a little bit later on. All right, so we'll kind of go through a few more things here before our lunch break. Segregation of duties is a concept not necessarily directly related to cryptography, but it can be used in cryptography. We have to maintain control over sensitive cryptographic keys that enforce the need to know principle. One person is not allowed to have full control over all phases of transactions without some sort of accountability enforcement. More negotiable assets under protection, the greater the need. Let me see what they're trying to say here. Not sure what they're saying here. More negotiable asset under protection, the greater the need for proper segregation of duty. I understand generally what they're trying to say. I believe that what they're saying here is with respect to exchange of information. Damage for unchecked access to cryptographic keys that unlock high risk, high value, or high liquidity information. In that sense, we would want to make sure that's protected. Make sure we do a cross-check to prevent misuse and the abuse of assets due to innocent mistakes or malicious intent. Definitely. That's probably one of the more significant bullet points on this slide because that is directly related to segregation of duties. It is difficult for smaller organizations to have segregation of duties because they don't have the resources to have additional personnel. So we would have to have other compensating controls, active monitoring, auditing, etc. There are two mechanisms for high integrity cryptographic operating environments. One is called dual control, and the other is called split knowledge. And I have some examples of each of these. Split knowledge. If you look at the diagram there, the CEO has half of the information. The CTO has the other half of the information to be able to access the database of encryption keys for the database password, to get access to the keys, the stored keys. So, the idea here, it's a very simple concept, is that the CEO, as long as the CTO doesn't share their half of the key, the CEO would never be able to access the database of encryption keys by himself or herself, and the CTO, the same scenario. Split knowledge. Multiple individuals know only pieces of important information, and by putting that important information together, we're able to affect whatever it is that we're trying to access or whatever. But both need each other to be able to do that. Okay? So split knowledge is very similar to dual control. The difference between split knowledge and dual control, though, is that split knowledge is generally something you know, whereas dual control is something you do. So, for example, we need to access this secure facility. I need to put my hand on the biometric scanner on the left, and somebody else needs to put their hand on the biometric scanner on the right to be able to open the doors. Although those doors wouldn't open because they would hit the scanner. But anyway, you get the idea. And the scanners are far enough apart that it would be impossible for me to be able to trick the system, so to speak. Not to mention that they probably have different databases, and I always have to use the scanner on the left, and the CTO always has to use the scanner on the right. Another example of dual control, launching nuclear missiles with keys, right? Two people have to turn a key. The old war games reference again, and if only one person turns a key, the missiles don't launch. So that's another example of dual control. Okay. Another element to asymmetric cryptography is the use of factoring. Integer factorization is where we basically take a composite number and we break it down into products of smaller integers. If we want to restrict the possibilities of that decomposition, then we will use something called prime factorization, where we're restricting essentially those factors to prime numbers. If the numbers are very, very large, it becomes exceedingly difficult to do that factorization. It's very, very simple to say, let's multiply two prime numbers to get a product. But it's exceedingly difficult. So that is this is what I'm referring to in this case is a one-way function. For a human, it might be difficult to multiply two 1024-bit numbers, but specifically 1024-bit prime numbers. But imagine if you were trying to find the factors that resulted in that product, right? How many iterations you would have to go through to be able to discover the original prime numbers that were used to create that product. So cryptography, a lot of different cryptographic protocols are based on this difficulty of factoring large composite integers. The RSA problem is an example of that. RSA is an asymmetric algorithm, and it does use these large prime numbers to derive keying material. If there was a way that we can decompose this product into its prime numbers very efficiently, then it would mean that the algorithm is not very secure. All right. The reason this is called a one-way function, it's not impossible to do. Certainly, if you take two prime numbers and multiply them together to get an integer, ultimately you're going to be able to figure out eventually what those two numbers are. You might say, well, wouldn't it be better if I was using all numbers instead of just prime numbers? But it's all about the time it takes to discover what those smaller integers are that were used to produce that product. So integer factorization is that decomposition of those composite numbers into that product of smaller integers, meaning what are the factors of 10, for example? 1 times 10, 5 times 2, etc. Those would be considered factors of 10. All right. Cryptographic algorithms like RSA, well, pretty much any asymmetric algorithm relies on the fact that prime factorization of large numbers takes a very long time. Public keys consisting of a product of two large primes for encrypting the message and a secret key consisting of those two primes that are used to decrypt the message is how we protect the data. The public key is public, but you only know the prime factors, and you can, only you know the prime factors, and you can decrypt the message based on knowing those prime factors. Everybody else has to actually do has to factor the number to be able to figure out what the primes are, and that's going to take a lot of time. So when it comes to cryptography and encrypting information, it's really important that we develop systems that provide us the ability to encrypt very efficiently and decrypt efficiently. But we don't want to make it so simple that the work factor is low enough that the system is not secure. All right? We cannot factor numbers without trying every possible combination. We divide by 2, then by 3, then by 4, and so on. So factoring a prime number, a very large one, and when I say very large, we are talking about 4,096 bits, 8,192 bits, maybe at a minimum 1,024 bits. So imagine if you took 2 different prime numbers that are 2,048 bits each and multiplied them together. That would be a really, really large number. All right. These are called trapdoor functions, by the way. Trapdoor functions are functions mathematically that are easy to compute, but extremely difficult to decompute. Multiplication of large prime numbers being one of those by definition. Asymmetric cryptography and asymmetric cryptographic systems depend on how hard it is to solve the mathematical problem. Problems are time-consuming to solve, but faster than trying all of the possible keys by brute force. Asymmetric algorithms' keys must be longer to provide equivalent resistance to attack than their symmetric counterparts. You're not going to have to know this for the exam, but most people that deal with cryptography understand the fact that the key space for asymmetric processes needs to be larger to provide the same level of security. Okay? And by the way, these are the prime numbers. This is just an example of the size of the prime numbers that are being multiplied to generate the key. Imagine trying to go through all of those different iterations. So if I want to have a key space or key strength of 80 bits equivalent in Symmetric, I'd have to have a 1024-bit RSA key. 112 bits Symmetric would be a 2048-bit RSA key. 128-bit Symmetric, 3072-bit RSA key. I think the standard pretty much today is 4096. That's kind of what I always use when I'm generating keys, 4096-bit key. Even though it does state that the 2048-bit keys are sufficient from a work factor perspective up to 2030, and the 3072-bit keys should be used beyond 2030. I'm not sure how they calculated that number. I would assume it's based on, the current condition of computing power and computing resources. So obviously that will change over time. That will change over time. NIST key management guidelines state that a 15,360-bit RSA key is equivalent to a 256-bit symmetric process. Elliptical curve keys should be twice the length of the strength of a symmetric key. We'll talk about ECCs, the elliptical curve cryptography process, after the break. What are the key risks to the exposure of keys? Obviously, the strength of the cryptographic system, the algorithm, the key length, the block size, the mode of operation are all going to contribute to the strength of the overall system. The operating environment. Oftentimes, if you get access to things like CPU and memory and even emanations from the computer itself, we can identify attributes of the encryption process, and that can introduce weaknesses into the cryptographic process. The more information that I encrypt with a key or a particular system could result in identification of patterns and whatnot. We call that frequency analysis. The security life of the data and the security functions also indicate potential to exposure, right? If the data is being stored for 1 day, it's less likely that it's going to be exposed. If it's being stored for 10 years, a high work factor might not be as big of a concern because we have a significant amount of time to be able to break that cryptographic function or that cryptography. How do we rekey the data, right? If I'm doing data in motion and I'm encrypting data over a channel, how often am I changing the keying material? And by the way, how am I doing that? Am I entering it on a keyboard? Am I using some sort of key loading method? Am I using an algorithm to establish, or a mathematical concept to establish a derivative key? That kind of thing. The number of nodes that share a common key could be a huge concern. And of course, the target would be a huge concern. Who is the information protected from? What are their capabilities? What are their resources? What are their, what do they have available to them to break that system? I said the target. That would also play a role as well, right? The U.S. federal government, for example, probably more of a mainstream target than the mom and pop donut shop, right? I put this slide in here just as a reference. It kind of identifies, longevity of keys for a specific purpose. And then there's another one, I believe, that I have here. I'm not going to go through this slide, but yeah. So as an example, AES 256 would be equivalent to a modulus of 15,360. and it would be protected well beyond 2030. AES 192, a little bit beyond 2030. AES 128, kind of slightly beyond 2030, and so on. And then there's different algorithms that use these different methods. Well, actually, let me rephrase that, because this is the symmetric algorithm and the key space. Let me use my pen here. These two columns kind of go together. So this is asymmetric, and this column is kind of by itself. This is my asymmetric, and then this is like a Diffie-Hellman type of process, elliptical curve, and then different hashing methods. I'm not entirely sure why they have hash A versus hash B. But yeah, I'm not sure why they have why they differentiate hash A and hash B. But hashing algorithms are used for, obviously, integrity. Okay. A digital signature is a cryptographic scheme that allows us to essentially verify the authenticity of a message. It, in essence, also provides us the ability to provide message integrity as well. Because if a piece of software or a block of data or information is digitally signed, it would not be able to be modified, and the digital signature would not be able to be recreated effectively without knowing that the data has been modified. It's similar to, obviously, somebody writing their personal signature, but actually it's even more secure than that, because personal signatures, handwritten signatures, are easy to be, can easily be forged. In essence, the way that digital signatures work is Alice wants to send a message to Bob. Alice is going to generate her message, and then she's going to generate a message hash using the private key of Alice. All right? Of course, the only person that has that private key and the only person that knows that private key is Alice herself. So as long as that private key is secure and it hasn't been compromised or shared with anybody, when Bob receives the message, he can verify that signature. He can verify that hash by using the public key from Alice. So, we're not necessarily encrypting the message. We're not providing confidentiality here. We could do that as well by using another set of keys. But in this case, we're simply trying to ensure that the message is not going to be altered and that it comes from an appropriate source. So let me kind of show you what I mean here. So I've got this little message that I want to send, and this is from Alice. Alice is going to take her private key, and she's going to hash that message using the private key, and then take that original message and send it along with that hash to the destination. So we're sending the message in plain text. Now, if somebody were to intercept that message and they would want to modify it, they're not going to modify this component, but they wanted to modify this component. When Bob receives the message, Bob is going to use the public key of Alice, to essentially verify the hashed component of that message. And if that hash works, right, we've got our message here. If that hash works, then we've essentially identified two things. Number one, the message has not been modified, and number two, that it was digitally signed by the only person that has that particular private key. So in essence, it's a mathematical representation of a unique signature. And in most cases, a lot of different protocol suites and cryptographic processes are going to use this as a standard method for digitally signing software, digitally signing messages like emails that are being sent. SMIME incorporates this concept when we're signing emails or electronic signatures to get applied to legal documents or other any kind of transmission, really. So the key here is that we're using asymmetric cryptography. We do provide, like I said, a layer of validation that the message hasn't been modified, even though the message is being sent through a non-secure channel. But it does give the receiver the reason to believe that the message was sent by Alice in this particular case, or by the claimed sender, and provides that scheme for verifying that. All right. There is a standard called the Digital Signature Standard, and the Digital Signature Standard is just a way of kind of verifying that we're using a modern protocol to provide this function. In 1991, FIPS 186 proposed using SHA instead of MD5. MD5 is Message Digest 5. That was a hashing algorithm that was used previously. The proposal was to go ahead and use SHA. There are some additional releases to this, by the way. That in 1991, that was the original release, and then there were some additional releases in for FIPS 186-1 was in the mid-90s, -2 was in 2000, and then I think they even released something fairly recently in 2013, 186-4, because as as protocols change and as the strength of protocols change, obviously we're going to modify the algorithms and whatnot that we're going to use for this digital signing. Okay, 186-4 is in 2013. Again, based on public key cryptography, asymmetric algorithm does not provide confidentiality. We can add confidentiality on top of it. DSS has two methods for creating the digital signature. We have the ability to do RSA signatures. RSA is an asymmetric encryption process that was invented by three individuals: Ron Rivest, Adi Shamir, and Leonard Edelman. And they've been, I guess it was founded in the 70s, right? It's been around for quite some time. And it has a key space of 2048 bits all the way up to 4096 bits. Generally, we try to operate on the high side. All right. Now, RSA is used for other things as well, but RSA utilizes those large prime numbers. In this particular case, they also use an auxiliary value for encryption, but it relies on the difficulty of factoring the product of those two large prime numbers, called the factoring problem, and that it's difficult to do so. RSA is a relatively slow algorithm. It's not, in fact, most asymmetric algorithms are relatively slow. So generally speaking, they're not going to be used for bulk encryption. We're not going to use asymmetric algorithms to encrypt data in motion. But as far as using it as a digital signature component, that would be definitely possible, because number one, we're not encrypting a large amount of data, and we're not doing it multiple times. We're only encrypting a small piece of data. All right, there's also ECDSA, elliptical curve digital signature algorithm. We'll talk about that later on. And there is DSA as well, the digital signature algorithm. each using kind of different encryption techniques and applications of encryption to provide for the security. All right. So how can that digital signature be created? It can be created by encrypting either the entire message with the private key of the sender. Not really practical because of the computational cost for this particular algorithm. In most cases, the signature is created by encrypting the hash of the message with the sender's private key, which is what I was describing. I think I kind of misspoke a little bit by saying we're going to hash with the private key. No, we're going to hash using a standard hashing algorithm like our SHA or MD5, and then we're going to encrypt the hash. And we decrypt the hash on the other side, and then we recompute the hash, compare the hashes to verify the integrity of the message. We cannot do direct encryption, or we can't generate a hash from a private key. Messages are encrypted with a symmetric algorithm for more confidentiality. Maybe we may choose to add a symmetric encryption for confidentiality. If it's an email or something like that, we may choose to use an asymmetric process to encrypt the data for confidentiality. And that would involve encrypting the data with the public key of the receiver, whereby the receiver is the only individual that then would be able to decrypt that message with their corresponding private key. If it's a large amount of data or bulk data, most likely we would be using some sort of symmetric algorithm on the flip side. The digital signature gets appended to the message, and then it gets sent to the receiver. We decrypt the signature with the public key of the sender, and then we verify the message is not altered because we're able to verify the hash. We also establish that non-repudiation of origin because the only individual that would be able to encrypt that hash with the private key is the individual that has the private key. Assuming that private key is secret, which it should be, nobody else should have that capability. Okay? How do we use these digital signatures? Primarily for non-repudiation, but we can also use it to protect the integrity of transactions. If we're downloading software from an internet portal, we can use these digital signatures to verify that the software has not been manipulated either on the website or during the download process. We can make sure patches are legitimate in this case. Digital signatures, of course, would be used to sign digital certificates. Remember I said the CA would hash the information of the X.509 certificate and then encrypt that hash using its private key. We can also use these for electronic document to assert authenticity, meaning that we know that the message is authentic and it comes from the appropriate source. The recipient would decrypt that hash value using the sender's public key. The hash computation is performed over the certificate content, and the hash value is encrypted using the private key of the sender. In this case, they're talking about in reference to the X.509 certificate and digitally signing that certificate. The receiver uses the public key of the sender to verify the sender's authenticity with the same hash computation over the certificate contents as it was done by the sender. Because remember, hashing processes are very, very predictable. Every time you hash the big brown dog bit me, it should always generate the same ciphertext output. There's no randomization. It's just going to simply result in the same ciphertext data. And that's the way it should be. So hopefully that would be the case. And we also haven't been able to discover some other ciphertext output that would match based on a different input, resulting in collisions. The receiver uses the public key of the sender. We did that. The hash results are the same. If the hash results are the same, then the sender is authenticated and the integrity of the data, in this case the certificate, has been established. We'll see a visual representation of this process a little bit later on. I created some diagrams that kind of describe the use of this asymmetric cryptography. So we'll see that a little bit later on. What is hashing, cryptographic hashing? Hashes are functions that take input messages of any length and generate a fixed length output. The size of that fixed length output will be determined based on the algorithm that you're using. MD5, for example, generates a 128-bit hash. SHA generates a 160-bit hash. We have different variations of SHA as well that will have larger hash values. The output that we get is called the hash code, or MAC, message authentication code, or message digest. Most people simply refer to it as the digest. We generate the hash, but hashing does not imply any secrecy. So if I was to take data and my goal is to ensure integrity, and I run that data through some sort of hashing process, we'll call it MD5, and I get the hash output, the digest output, and I send the data along with the hash to the recipient, there's absolutely no guarantee in this case that that hash or that data is protected. Yes, the individual that receives the data is most likely going to run that data through the same hashing process, and it's going to generate a hash on this side, and we compare this hash to this hash. If they're the same, okay, maybe the data hasn't been modified. But what would prevent an individual in the middle from intercepting that data, throwing away the original hash value, modifying the data, and recalculating a new hash? Nothing. There's no way for the recipient to know that that would have occurred, because it's just going to verify the hash based on the data it receives. Bob is just going to verify the hash based on the data that Bob receives. And of course, the hash will be verifiable because the hash was recalculated. So hashing alone does not provide integrity. Hashing alone does not provide authentication of origin. There always has to be some sort of secret sauce that goes into the hashing process that Evil Eve would not know to protect this mechanism. So there's got to be some sort of keying material that both parties know that goes into that hashing process that the person in the middle doesn't know, in order to provide for true integrity. Now, it's not to say that hashing by itself doesn't have a function. You know, hashing passwords in a database, for example, would be an appropriate use of hashing without secret material. Creating a hash of software that's being installed on a website. So if you go to cisco.com and you go to download software, you will see the calculated hash for that software published on the website. So if you download that software and run it through a hashing process, and the hash matches, you know that the software is legitimate and that it hasn't been modified. So there are applications of hashing by itself that are useful, but as a security mechanism for data in motion, not really that useful by itself, unless there's some secret function going into the hashing process. What are the 4 key properties of a hash? Hash output values should not be predictable. Now, what does that mean? It means that if I encrypt a bunch of data with a bunch of letter A's in it, right? Maybe it's a sentence or a statement or, a paragraph or a book, whatever it is. I'm encrypting a bunch of data with a bunch of A's in it. There shouldn't be any indication in the hash output that those A's exist. So if I encrypt something with a bunch of A's in it and I get output X, and then I encrypt something else with a bunch of A's in it, but it's a different document, and I get output Y, and they look similar, leading me to the ability to infer, that there are some common characters. We don't want that to happen. It has to appear to be random. All right? Meaning that, now it's not to say that every time you hash something that it should be different. That's not how hashing functions work. In fact, it's the opposite. The last bullet point says deterministic. Given input X, it needs to always generate the same value Y. So from that perspective, yes, it needs to be predictable. But like I said, if I hash the big brown dog bit me, and then I hash the big brown dog bit me exclamation point, there should be a significant difference between those two hash outputs. Very difficult to invert. It should really be a one-way function. You should never be able to derive the hash input by reversing the hash function on output Y. And quite frankly, most hashing processes are one-way functions. Even the legacy hashing protocols would be extremely difficult to reverse. The hashing protocol should be very resistant to collisions. It should be difficult, not impossible, but it should be very difficult to find two different inputs that end up resulting in the same hash value output. That's what we refer to as a collision. We talked about that previously. So let's talk about some of these different hashing algorithms. We'll start by talking about one that was developed in 1992 by Ron Rivest. Ron Rivest was responsible for developing these algorithms. This digest size is 128 bits. It operates on 512-bit blocks of data, and it has 4 rounds of operation. Each round contains 16 steps. Now, what does all of that mean? One of the things that we do later on, towards the end of this chapter actually, is we look at the Reindel algorithm, and we actually look at how we operate on the data. Most encryption algorithms will have very predictable rounds of function. Okay? In this particular case, this particular encryption process has 4 rounds of operation. And within each of those rounds, we're doing 16 steps of confusion. And I'm not particularly sure what those steps are. I haven't gone through to look at the individual steps. But it would be, stuff like XOR operations and mixing bytes and shifting rows and other things. And again, don't quote me on that, right? Because I literally don't know what those rounds look like. It is based on what we call Merkle Demgard construction. And again, that is essentially kind of the algorithm, if you will, that describes the different rounds of operation. And it's the same construction that's used in SHA-1 and SHA-2, where we're operating on these different blocks of data. But again, you don't need to know that for the exam. All right. This is a series of publications. There was MD2, MD4, MD5. And MD6, but for the most part, this particular algorithm has been somewhat retired. All right. So we generate a 128-bit digest. We operate on 128 bits of data at a time, which makes sense. 512 bits of data each time. And we have 4 rounds and 16 steps within each round. The likelihood of finding 2 messages with the same hash code is estimated to be 2 to the 64. And the difficulty of finding a message within a given digest is 2 to the power of 128. Well, that's simple enough to calculate. Well, first of all, 2 to the power of 64 is related to a paradox that we're going to talk about later on called the birthday paradox, and 2 to the power of 64. And 2 to the power of 128 is simply related to the fact that we're generating a 128-bit digest. That would be equivalent to how many iterations you'd have to do before you might find, you might be able to decipher the message. Extremely difficult. All right, there are several attacks against MD5. It is possible to find collisions, and generally speaking, MD5 is considered to be a legacy protocol. All right. It was developed in 1991, and it's RFC 1321 if you're interested. RFC 1321 is the request for comment that describes the operation of the protocol. SHA, the secure hashing algorithm, is, and there's many variations of the secure hashing algorithm, is another hashing protocol. All right, and there are, like I said, different variations. SHA-1. We'll start with SHA-1, and then we'll talk about some of the other variations. But this was developed by the NSA, the National Security Agency. It was first published in 1995. Well, there was a previous version, SHA-0, that was published in 1993. It is certified under FIPS publication 180-4. It generates a 160-bit digest, and it operates on 512-bit blocks as well, just like MD5. There's 4 rounds of operation, and each round includes 20 steps. So it includes essentially 80 steps of confusion. All right. Is it really any different? Not really. I mean, its overall function is considered to be the same as MD5. It is considered to be more secure because it does have up to 264 bits in length that we can deal with, but it's 160-bit hash as opposed to 128-bit hash. All right. Now, Google and some other folks have performed collision attacks against SHA-1, so I wouldn't necessarily say that it is weak by any means. There are some vulnerabilities. A linked extension attack was identified in 2017, but it's still considered secure for things like HMAC processes and so on. The SHA-1 process produces the message digest based on principles that are similar to MD5. It just generates a larger hash output, 160 bits. And again, this was part of the concept or a government developed hashing process, the United States government, for developing a hashing standard that would qualify for FIPS publication 180 certification. All right. Let's see. NIST issued FIPS 180-4, which recognizes SHA-1, SHA-224, SHA-256, SHA-384, 512, and 512.224 and 512.256 is part of the secure hashing standard. So again, we can go from output links from 160 bits all the way up to 512 bits. It's going to provide the same functionality, right, as far as being able to verify integrity and verify operation, authenticity and origin, guarantee of origin. It just depends on how it's being applied, how the hashing process is being applied. Still can be used for digital signing. It can be used for simply hashing data like software and whatnot to be verified later on. SHA-3 is also an algorithm that's available. SHA-3 is kind of the latest member, if you will, of this family, released by NIST in 2015. It was first discussed in 2007. It is part of the same series of standards, but SHA-3 is very different structure-wise from MD5 or SHA-1 and SHA-2. Several individuals were responsible for developing the protocol. It is certified in FIPS, but publication 202, not 180-4. The digest size in this particular case is somewhat arbitrary. It uses a completely different structure than SHA-1 and SHA-2. All right, it uses something called sponge construction. I would not even venture to try and describe what sponge structure is or sponge construction. I'm just not that well versed on it. So, all right, but be aware that it exists, right? And we'll see. It's not widely adopted yet, and we'll see how it how it gets adopted later on as we move forward. The sponge construction concept was interesting to me. I kind of reviewed a little bit about it. It's like, if you can imagine sucking data up into a sponge and then squeezing it out. That's the visual anyway of this sponge construction technique. But again, I don't know specifically, what the formula is for that, or permutations or the calculations for that. It is a very fast hashing algorithm, and there are many different data block sizes that we can have. 224 bits, that's SHA-3 224. 256 bits, SHA-3 256, 384, and 512. And then we have some other specifications as well. So maybe we'll see this later on, kind of more prevalent. Some of the more obscure protocols that we don't really talk about too much, and honestly, you're probably not going to see on the exam. One is Haval, developed at the University of Wollongong in Australia. It takes a variable length, combines variable length outputs with variable numbers of rounds of operation, operating on 1024-bit input blocks. Okay, it's been around for a while. It's considered kind of legacy at this point. It was broken in 2004. So it's been some time, but it would produce different hash output lengths, 128 bits, 160 bits, 192 bits, all the way up to 256 bits. Also it would allow you to define the number of rounds that you wanted to implement, either 3 rounds, 4 rounds, or 5 rounds. We don't really kind of talk about it too much because it's kind of considered to be a legacy protocol. It is faster than MD5 with 3 rounds of operation, but if you choose to operate in the variant of 5 rounds, it's about the same as MD5. All right, RIPE-MD is, again, just another hashing algorithm. It was developed in 1992, I believe. It operates on digest sizes or generates digest sizes of 128 bits all the way up to 320 bits. It stands for Race Integrity Primitives Evaluation. MD, of course, stands for Message Digest. Again, not a protocol that you're probably going to have to know. It was a European hashing algorithm that was developed. Yeah, that's about it. It operates, it generates an output of 160 bits. Well, it depends on the version. Obviously, we're talking specifically about 160, but there are other versions as well. There's RIPE-MD 128, all the way up to RIPE-MD 320. Okay. What types of attacks can we see against hashing algorithms? Cryptanalysis, as I mentioned before, is the science of defeating cryptographic systems, gaining access to encrypted systems or aspects of encrypted systems. The ways that we attack a hash function is either through brute force attacks or through cryptanalysis. Probably one of the most common methods of trying to defeat a hashing process is to use something called a rainbow table. And we'll talk more about rainbow tables and how we can protect against rainbow table attacks. But a rainbow table attack is like a brute force attack. It is a type of brute force attack, but some people would also classify it as a dictionary attack. In that it is essentially a dictionary of pre-computed hashes. One of the things that's difficult to do is to run through different iterations to try and duplicate a hash. Now, if I hash a sentence or I hash a paragraph or whatever it is that I'm hashing, and it generates a fixed length predictable output, it would make sense to say that, and by the way, this would not be typically feasible if it was the hash of a document or the hash of a large amount of data. This would be much more feasible if it was the hash of a password, as an example. So if we're trying to discover a password, that's where these rainbow tables would come in and be effective. Because passwords might have a specific key space, a key size, as opposed to a document or hashing an email or something like that, which could be tens of thousands of characters. Well, at least hundreds of characters if it's an email. So the idea of a rainbow table attack is that we've already gone through the work of running through our entire dictionary of passwords, generating the hashes or pre-computing the hashes for that dictionary of passwords. And all we simply do at that point is compare the hashes that we've pre-calculated to the hash that we're trying to break. So it is a rainbow table is, in essence, a dictionary of pre-computed hashes. All right. Both MD5 and SHA-1 are susceptible to cryptographic attacks. We were talking about rainbow tables. And one of the ways to protect against a rainbow table attack is to use something called salting. A password salt is a known variable that you add to the data before you perform the hash. It's like I always think of the Salt Bay guy that drops the salt on the steak. The salt is a known value. It's a published value. It's not a secret value. But when you hash something with a salt value, of course, it's going to change the cryptographic hash. And even though the salt value is known, even to the attacker, it negates the effectiveness of the rainbow table because the rainbow table was not calculated with the salt value. The rainbow table was calculated without a salt value. So in that sense, that means that the rainbow table is essentially null and void because the hashes were not calculated with the salt. So the only way now to break the hash is to do it through brute force, which takes a lot of time. Brute force also looks to find weaknesses in the algorithm. Ultimately, the goal is to figure out what the original message is, which would ultimately defeat the one-way property of the hash function, or maybe find another message that generates the same hash value, because oftentimes if hashing is used for authentication, the hash value could be used for authentication. So if I can find another message that generates the same hash value, I don't even need to know what the original message was. I can simply use that message to authenticate. So if the password is Cisco123 and Cisco123 generates a hash of X, and I happen to find that password Bob123 generates the same hash, then I could most likely authenticate with Bob123 because the authentication mechanism is looking to use that hashing process to verify the authenticity or to authenticate. So I wouldn't even need to know what the original hash was. And that's why collisions are so bad. Find any pair of messages with the same hash value. Urshot and Wiener developed a machine that could find collisions on a 128-bit hash in about 24 days. Also, side channel attacks are examples of Crypta Analysis. A side channel attack, we'll see this definition a little bit later on, but I'll describe it briefly here, is an attack where information is gained simply from the implementation of a computer system. So rather than a weakness in the algorithm itself, like a bug or some sort of cryptanalysis component, we look at things like timing information, power consumption, electromagnetic fields or leaks, sounds that are being generated, and by analyzing that information, we're able to attempt to break or at least find weaknesses in a particular algorithm. Way beyond the scope of my knowledge as far as implementation goes, but it is fairly well documented, a fairly well documented practice. Rainbow tables, I really just kind of described that. These rainbow tables can have hundreds of thousands or even millions of entries of pre-computed hashes. The whole point of creating these pre-computed hashes is to reduce the work factor. So if I have millions of entries of hashes in my database, all I simply have to do is compare the hash that I'm trying to break with the hashes in the table, which is just a one-by-one comparison, no mathematical calculation. And if I find one that matches, I haven't had to really do much work. So salted hashes will provide a defense against the rainbow table attack because the table was not created when the salt was used during the authentication process. The salt itself is made up of random bits, but it is known. It's a known value. In fact, let me show you something really quickly. So here's an example of a hashed password using a Cisco technique, specifically MD5. That 5 there indicates that this is a MD5 hash. And what you see here is the actual hash. This is the hash output. The R1, Bravo, Umbrella, Oscar 2, Tango 4, Whiskey, Whiskey, etc. This indicates that the hashing method that was used, but this value right here is the actual salt value. So if I was to go into my Cisco device and say enable secret Cisco or enable secret and then put in the password, and I use password A as an example, that would generate a hash, right? And then if I go and do that again, 2 seconds later, it would end up resulting in a different hash, even if I'm using the same password, because that salt value would change. That salt value changes every time we execute the command. But if somebody's verifying this hash, like this router, verifying this hash when you're authenticating to the router, the salt value is published. The thing is, that salt value was not utilized when we created the rainbow table. So all the hashes that were pre-computed in the rainbow table they're not usable anymore. Does that make sense? So we actually literally have to go through and do a brute force attack, which takes a lot more time and a lot more work. All right. Why is my mouse stuck? All right. The salt is stored with the resulting hash, so we'll use the same salt to get the same results. Salt values are not secret. What is the birthday paradox? It is a common discussion when it comes to probability theory, specifically when it comes to cryptography. The birthday paradox, well, let me see if I can describe it. I always have a little bit of a difficulty describing this in class, but in order for there to be a 50% probability that someone in the same room with you has the same birthday as you, there needs to be 253 people in the room. Okay? In order for there to be a probability of 50% or more that two people in the same room share the same birthday as you, you only need 23 people in the room. So again, let's take a look at that again. In order for there to be a 50% probability that someone in the same room with you has the same birthday as you, there needs to be 253 people in the room. Now, when you read that, you're like, that doesn't really sound right? That doesn't sound like that makes sense. But that's why it's called a paradox. All right, so you have a number of randomly chosen people. The birthday paradox literally states that at least two of them will share your birthday. We're not talking about your birth year. We're talking about your birthday, right? It's very counterintuitive. The fact that we say the probability of a shared birthday goes above 50% in a group of only 23 people, it doesn't make a whole lot of sense. It just doesn't make sense. They have a term that describes that, some sort of paradox. I don't remember what that term is, but veridical. I think that's it. But so it seems surprising, right? That only 23 people would be required to reach that 50% probability. But if you consider the comparisons of birthdays are going to be made between every possible pair of individuals, right? The top line describes somebody in the room having the same birthday as you. The bottom line, or the second line, describes two people having the same birthday. Not as you, but two people in general, any of the two people in the room. It would kind of make sense to say, well, yeah, I would need at least 253 people in a room to maybe share the same birthday as me, because there's only 365 possibilities in the year. So 253 people, you might actually conclude that that would be a higher percentage. But the second line is the one that can be really confusing. All right. If you take into account the 23 individuals, there are n times n minus 1 divided by 2 possibilities. N, let me write that down. N times n minus 1 divided by 2 possibilities. That's the formula that we use to do the calculation. So that would be 23 times 22 divided by 2, which would result in 253 pairs to consider. That's well over what we would have as far as the number of days in a year, right? Half of the number of days in the year is about 182 or 183 days in the year. So what does this mean to cryptography? There is an attack called the birthday attack, which I'll talk about in a minute, but let's go ahead and finish up this slide here, and then we'll move on to that. The pigeonhole principle, actually, let me do the third bullet point down first. The probability theory concerns the likelihood that in the group of randomly chosen people in a room, some pair of them will share the same birthday. The day, not the year, but the day. The pigeonhole principle of probability sets that likelihood of 100% if there are 367 people in the room. Well, there's only 365. There are only 365 days in the year, and then also if you count leap year, that would be 366 possible combinations. So if you have 367 people in the room, you're guaranteed to find somebody with the same birthday. They call it the pigeonhole principle because if you can imagine, you've got this pigeon coop, right? And you've got all these little boxes, and each one of those boxes contains a pigeon. Well, there's only so many pigeons that you can have, right? So, and they each go in a hole. Every hole is filled up. There's an extension of that as well, but that's how they came up with that concept of pigeonhole principle. The likelihood or probabilities are a result of that third-party number matching, that formula that I mentioned, the n times n minus 1 divided by 2. It's a mathematical calculation. It's just it becomes a little bit more obvious when you apply it that way. If you're an outside observer, you're looking at all the numbers to find the matching pairs. Under this condition, let's assume that each day of the year, with the exception of February 29th, is equally likely as a birth date. So you have a 99.9% probability that a match is observed within the group of 70 people and a 50% probability with 23 people. The same birthday with one person would give you 0%, with 20 people would give you 41%, with 23 people, 50%, with 60 people, 99%. It's just an interesting concept. It's just something that we tend to discuss, but we relate it to this. What is a birthday attack? A birthday attack is a cryptanalysis attack that exploits the mathematics behind this birthday problem, which we just described. We can use this attack to find collisions. So the attack depends on the higher likelihood of collisions can be found between random attack attempts if I have a specific number of permutations in general, right? Now, there is a mathematical formula to find a collision of a hashing function. It involves square roots and powers of 2 and everything else. I'm not going to get into that. But for the test purposes, we need to understand specifically how this concept of a birthday paradox gets applied to this birthday attack. In cryptography, hash functions are mathematical processes used to reduce larger strings of data into small strings of fixed length output. And that fixed length output represents that larger string. An ideal encryption scenario means that each hash value is unique. And when we decrypt it, it can be traced back to the one specific string that it produced, meaning no collisions. All right? But encryption is applied over a very large data set. And for any given hash function, there is the possibility that two different inputs may be hashed down to the same output, because it's possible that we're out of that large data set, we end up comparing similar values. The birthday attack is a specialized form of brute force attack to find those collisions in our cryptographic hashing functions. We exploit this underlying probability theory and the mathematics of the birthday paradox situation to reduce the number of samples and iterations that are required to find the matching pairs. So in other words, it's just simply going to reduce the work factor required for us to find a collision between two different plain text inputs. Does that make sense? So again, we don't need to look at the math of it. The math is a little bit more complicated. There's documentation that you can read that describes possible outputs based on probability inputs and so on, and how many different permutations you have to run and whatnot. I'm not a mathematician. I don't claim to be, so I wouldn't venture to try and describe that. I can do basic binary math and maybe add and subtract at a 5th grade level, but that's about it. Okay? So let's take a look at some of the other common cryptanalysis attacks. And just kind of describe what these are. When I took my exam, I didn't see really any reference to any of this on the exam, but it is part of our cryptography discussion. So a COA, or a ciphertext only attack, is an attack against the known ciphertext. So there's a couple of things that can happen in cryptanalysis. You can know all or some of the plain text. You might think, well, if I know all or some of the plain text, then what's the purpose? But we'll talk about that in a minute. That's a known plain text attack. You can know all or some of the ciphertext, which is more likely, right? Because the ciphertext is going to end up being transmitted in the clear. That's the whole point. We're going to send the ciphertext to the destination. Or you can know maybe information about the algorithm, or you might have some keying material. Maybe not all the keying material, but some of the keying material. Now, as I describe each of these different types of cryptanalysis attacks, I want you to think about what generally the overall objective is of cryptanalysis. It is not to discover the plain text. Most people think, well, yeah, I'm trying to find out what the secret message is. No, actually, most cryptanalysis attacks are looking for one of two things. They're trying to discover the key, or they're trying to discover an inherent weakness in the process. And the reason why we would try to discover the key or a weakness in the process is that we want to be able to continue to use those methods, not for one message, but for every message. Now, when it comes to password guessing and password cracking, yes, ultimately we are trying to guess the plain text. But when it comes to breaking a cryptographic system, we want to be able to do it in a way that it provides us access to that information over a large amount of time. All right? So all of these, will keep that in context, in the context of our discussion. All right? We assume the attacker is, in this particular type of attack, is assumed to have access only to ciphertext. We don't have any channel providing access to the plain text and or the keying material. The reality is that this is probably one of the most easily accessible types of attacks, because generally speaking, we always have access to that ciphertext. So we take that unintelligible data. We suspect that it may be important, an important encrypted message, and we start to do analysis. Now, what kind of analysis are we doing? We could maybe try and reverse engineer the process or reverse engineer the encryption. We could be doing frequency analysis, where we're analyzing and looking for patterns in the ciphertext output to indicate maybe patterns in the encryption process. We might know, for example, the language of origin. Knowing the language of origin might give us, the ability to use statistical analysis to identify, again, patterns in the ciphertext and so on. There's different types of ciphertext attacks. WEP, for example, was vulnerable to this. There were several attacks in WEP, actually, that were ciphertext-only attacks. Now, you don't need to know necessarily. Brute force would be another example, of course, of a common type of ciphertext-only attack, where you know the ciphertext and you're just simply trying to find what, the encryption algorithm, the ciphertext, so you're trying to find the plain text that results in the ciphertext, which means that you're able to discover the key, because ultimately that's our goal in this particular case. All right, so we might be looking for expected statistical distribution of characters. We might be looking for commonalities in the system and so on. It says here that the attack becomes simpler when the attacker gathers several pieces of ciphertext to look at for trends over time. That's why it's extremely important when we implement these cryptographic features that we introduce at least some form of pseudo-randomness to the encryption process, so we don't see the frequency of information. Encryption is defined as strong enough to make brute force attacks impractical, with a much higher work factor than the attacker wants to invest. I talked about the concept of Moore's law previously, but I didn't really mention its name. Moore's law states that computing power doubles every 18 months. So encryption strength that might be adequate for today will not be sufficient later on. And I would venture to say that time period is even shorter. With distributed computing techniques and the advancement in computing that we see today. All right. But as far as knowing the definition, ciphertext only, the name itself kind of implies what it is. A known plain text attack is what we call KPA, another cryptanalysis a method where we have access to the plain text and the ciphertext. The plain text is called the crib in this case, and we have access to the ciphertext. So you might say, well, wait a minute. If I have access to the plain text and I have access to the ciphertext, what do I need? You need access to the key, because that's ultimately what I need, right? If I want to be able to decrypt all remaining messages or future messages, I want to be able to decipher the key. So this isn't as common because, obviously plain text would generally be considered to be secure or hidden, but it doesn't have to be current plain text. It could be past plain text. The idea is that we establish either the code books that are being used or the secret keys that are being used so that we can decrypt, in the future. All right. Code books are just repositories for keys, right? And maybe in the past, certainly back in the day, we had cryptographic codes that were stored on paper. We weren't deriving cryptographic codes electronically because we were using different physical means of encryption. All right. Another type is a chosen plain text attack. Chosen plain text is very similar to known plain text. The only difference is that we're operating on a specific component of the plain text. We have the ciphertext, and we're going to analyze the encryption process based on arbitrary plain text values. Again, the whole idea here is that we're trying to gain information about the cryptographic process. Specifically in this case, gain information about the encryption scheme that might be used. All right? We as the attacker, we get the ciphertext, which is easy to capture, and we capture some or arbitrary amounts of the plain text, and then we look at the interaction between the plain text and the ciphertext to find issues with the encryption process. All right. This assumes, of course, that you do have access to some of that plain text information. We take, random pieces of that plain text. We send it through some sort of encryption process. We encrypt the attacker's plain text data, based on this plain text ciphertext pair, we can extract the keying material eventually, hopefully. Most of these different cryptanalysis techniques, that's our goal, is to identify what the keying material is. Actually, let me go back. I just want to make sure I'm hitting all these bullet points. The attacker knows the algorithm that's being used for encryption or has access to the machine that's used for the encryption. And the goal here is we're trying to determine the key. This could happen if the workstation used for encryption was left unattended. Now the attacker can run chosen pieces of plain text through the algorithm to see the result. So do we even need to know the actual plain text? No, we don't. We're trying to see we're trying to discover the key. But by going through iterations of putting plain text through the algorithm and knowing how the algorithm functions and looking at the ciphertext, I might be able to decipher what that key material would be. The adaptive chosen plain text attack is when an attacker can modify chosen input values to verify the effect that it would have on the outgoing ciphertext. That's again establishes that we're trying to do some sort of frequency analysis. We're trying to see, what changes are we making on the input that result in different changes on the output. So what is the difference between chosen plain text versus known plain text? Known plain text is the actual message that the original sender intended to send. Whereas chosen plain text is, we know the algorithm, we have access to the encryption process, the specific encryption process that was used to encrypt the data that we're trying to get access to, and we're just taking that chosen plain text and sending it through the system, and then comparing that to the ciphertext to derive the keying material. Chosen ciphertext. Similar to choosing plain text attacks or chosen plain text attack, the attacker has access to the decryption device or software and is attempting to defeat the cryptographic protection by decrypting chosen pieces of ciphertext to discover the key. Okay. Adaptive chosen ciphertext is the same, but the attacker can modify the ciphertext prior to putting it through the algorithm. Asymmetric crypto systems are vulnerable to chosen ciphertext attacks. That might be something that they would ask you on the exam. The attacker selects a section of plain text, encrypts it with the victim's public key, and then decrypts the ciphertext to get the plain text back. It does not yield new information to the attacker, but it can exploit properties of RSA by selecting blocks of data when processed using the victim's private key, which can yield additional information that can be used in the analysis process. We mitigate this by random padding. In fact, we mitigate essentially any of these attacks by introducing pseudo-random or random information into the encryption process. We'll talk about the different chaining methods that are used and initialization vectors and what kind of options we have for introducing randomness into the encryption process. All right. All right. Next one we'll talk about is differential cryptanalysis, where we analyze typically block ciphers in this particular case. We can also apply this to stream ciphers and hashing functions, but primarily we use this in block ciphers. It, in essence, is a, we take a look at how differences in the information input can affect the difference in the output. That's why it's called differential cryptanalysis. In the case of a block cipher, we employ different techniques for looking at those differences throughout the transformation process. And obviously in this case, what we're looking for is we're looking for non-random behavior that we can exploit to ultimately discover either a weakness in the algorithm or a keying material. All right. It's usually going to be done based on some sort of chosen plain text attack, meaning that we have to be able to get access to the ciphertext from us choosing our own plain text input. But there are extensions to this that would where you could use known plain text or ciphertext only, but for the most part it would be, we have access to the cryptographic system and we're injecting known plain text into that system to look for these operations. Differences can be defined in a lot of different ways, but ultimately the goal is to look for statistical patterns in the distribution of information. This is called a side channel attack. It is more complex to be executed because we can measure exact execution times, power required by crypto devices to perform decryption and encryption, and so on. Well, that's one option, I suppose. That's not what I described, but that is one option of differential cryptanalysis. By measuring those side channels, we may be able to determine the value of a key. We may be able to determine the type of algorithm that's being used. And as I did mention, it's applied typically to block ciphers. Yeah, I already kind of did all of these bullet points here. Okay. Linear cryptanalysis. This is a known plaintext attack using linear approximations to describe the behavior of a block cipher. Given sufficient pairs of plaintext and ciphertext, it may be possible to obtain bits of information about the key. Increased amounts of data gives us a higher probability. As you can imagine, this would take a lot of time. There are a variety of enhancements and improvements to this basic attack. There is also an attack called differential linear cryptanalysis, where we combine the elements of differential cryptanalysis with linear cryptanalysis. This probably would be one of the ones that would take the longest amount of time because we're actually trying to derive components of the key material. But it also assumes that we have access to both the plain text and ciphertext. All right. Trying to think if there's anything else I want to mention about this. It's called linear cryptanalysis, by the way, because we are using linear equations related to that plain text ciphertext pair to be able to do the calculations. And I'm definitely not going to get into the discussion of those linear equations. All right. Implementation attacks. Implementation attacks are most common and popular attacks against cryptographic systems due to the ease and reliance on the system elements outside of the algorithm. So side channel attacks, fault analysis attacks, and probing attacks. We kind of already talked about the idea of a side channel attack. This would be a passive attack where we're relying on physical attributes of the implementation, things like power consumption, emanations from the system, and believe it or not, people do this, and it can be somewhat effective, certainly for identifying the algorithm in use. Looking at electromagnetic differentials, looking at power consumption, on an oscilloscope, or looking for emanations from the computing system to be able to identify how that computing system is functioning. Fault analysis, we attempt to force the system into an error state. By forcing the error, we might gain some specific results. We compare it with known good results, and we can learn information about the key or the algorithm in that case. Probing attack, we attempt to watch the circuitry surrounding the cryptographic module, hoping that complementary components disclose information about the key or the algorithm. New hardware gets added to the cryptographic module, and then we can observe and inject information in that cryptographic system. All right. A replay attack. This would be much more common, actually. Replay attacks are pretty common, pretty easy to implement. In a replay attack, this is a network-based attack. We take valid data transmissions that we've captured, and we simply repeat them fraudulently with the idea that we're either going to spoof information from an individual, or we're going to be able to spoof an authentication session or an identity session or whatever it might be. We intercept the data, we retransmit it. That's why it's called a replay attack. We can substitute data. Maybe we're doing an IP packet substitution, or we're doing some sort of spoofing attack. It could also allow us to facilitate man-in-the-middle types of attacks, but generally speaking, it's to facilitate authentication. So let's say, for example, that Alice wants to prove her identity to Bob. Okay? Bob asks Alice for proof, password in this case. Give me your password, all right? So Alice provides that information. Maybe it gets hashed or encrypted in some way. But in the meantime, Evil Eve is sitting there, and she or he or they, them, or whatever, however you want to call it, are observing the conversation, and they keep that information. They capture that information, and they keep that information. Now, once Alice and Bob are done communicating, Eve then makes an attempt to connect to Bob, but asks, probably essentially trying to identify herself as Alice. So when asked for proof of identity, guess what Eve does? Eve sends the hash that was read from that last session. Bob accepts it and gives access to Evil Eve. How do we prevent against this? We use temporal values, right? We either encrypt information, or we have some sort of component value or session ID that is tied to an individual session, and that session ID is never duplicated. Because there is a unique, somewhat random session ID that gets created for each time the transaction takes place, whatever that transaction might be, it would be much more difficult to replicate. We would be unable to perform that replay attack because we would have to generate the new session ID, which would be generally based on some sort of one-time token that Bob would actually send to Alice and then Alice uses that information to incorporate it as part of the hash. The token itself might even be used to compute the hash along with the password. So Bob performs that same computation, not only on the password, but on the hash, but with the session ID. And that's not something that Evil Eve, even if Evil Eve captured that value, if she tried to use it in a new session, it wouldn't work because we'd have a new session token. So if Evil Eve replies with her captured value, it's going to be different than Bob's computation because it doesn't include the same session ID. Make sense? All right. And that's done quite a bit, actually, in most transactional communications that we see today. Frequency analysis. I've mentioned this term a couple of different times. Frequency analysis, quite frankly, is just looking for patterns in the ciphertext using various methods, but we're looking for patterns. So, for example, if I was using kind of a legacy encryption method, a physical encryption method where I was taking a letter, I want to send a cryptic letter to Bob, and I decide that I'm going to use a substitution cipher. So I have a substitution key that is static, that Bob knows and that I know, but hopefully nobody else knows, that says for every letter A, we're going to replace that with a letter S, or for every letter G, we're going to replace that with a letter P, and so on. Now, if you know the language of origin and even maybe know the context of the message related to a war, related to a battle, related to some trade secret or whatever, you might be able to look at that letter and start to find, based on the language of origin and based on the context of the message, values that are easy to determine, right? So you might see a whole bunch of letter G's, and you might be able to infer, well, the most common letter in the English language is this letter, or the most common combination of letters is these two letters. I see that 100 times in this document, and I'm going to make that assumption and replace those with what I think they are. It's like doing a word puzzle, right? Crossword puzzle. Once you get a couple of up and down or left and right answers, it becomes easier and easier to decipher the crossword puzzle because you're able to fill in some of the gaps, so to speak. That's essentially what frequency analysis is. We just have different, different expectations of, basically what patterns might look like. All right. Now, we're talking about the English language, right? E and A and the letter O might be the most common values. Maybe Q and X are kind of the rare values, if you will. And then we also have a lot of combinations of letters that are very common, like TH, for example, or ER, or AN. Or we might have most common repeated letters, like double T or double E. So some phrase that might look nonsensical, by applying this concept, knowing the language of origin and understanding the English language, we might be able to decipher that message. All right. Isn't that kind of how Wordle works? I've never played that, but anyway. What is a factoring attack? A factoring attack is an attack against, in most cases, against the symmetric algorithms, right? We're trying to derive the keys based on finding the two prime numbers that were multiplied together to create the key. Not much else I can say about this. That's exactly what it is. And typically it's going to be a iterative process, brute force process to derive the two prime numbers that were used to derive the key. Social engineering can be used as well. The most common types of attacks often involve social engineering. Maybe not as much for cryptographic processes, but if you know that somebody knows secret information or has access to secret information, you might befriend that individual. There's all different types of social engineering attacks. A watering hole attack, an example of a watering, well, actually we'll break these down a little bit later on. I think in the next couple of slides we look at different types of social engineering attacks. All right, dictionary attack. Now, a dictionary attack is different than a brute force attack. A dictionary attack is where you're using a pre-computed dictionary of passwords or hashes to use as a comparison against whatever it is you're trying to analyze. All right, so maybe it's a password that you're trying to decrypt or a password you're trying to discover. So you have a dictionary of passwords that you can use to either try to authenticate to a system or compare to some authentication process. The difference between a dictionary attack and a traditional brute force attack is that brute force, you don't have a pre-computed dictionary. You're simply going through different iterations trying to discover something that works. So you might start with 2 characters and do all the different iterations of 2 characters and then 3 characters and 4 characters and so on, as opposed to having this pre-computed dictionary. So a rainbow table is in essence a dictionary attack because it's a dictionary of pre-computed hashes. Brute force, on the other hand, is literally where you're just trying different iterations until you find one that works. This one's going to take the most amount of effort, I suppose. Trying all possible keys until one is found that decrypts the ciphertext. Here, the key length is important to determine the strength. Key complexity could be used as well, but you've got to remember with cryptographic systems, we're typically dealing with keys that are a hexadecimal or there's some sort of binary, ultimately a binary value. So even though actually passwords can be represented the same way, they just happen to be ASCII characters as opposed to hexadecimal characters. We typically with cryptographic processes have fixed length keys, especially with symmetric encryption algorithms. We don't have variable length keys. With passwords, they can be variable in length, and we can have arbitrary decisions on what kind of characters are included in those passwords. So brute force might be more effective with, say, AES or triple DES or whatnot, because we know we already know some constraining parameters to the possible key space and key length. Obviously, the longer the key, though, the more iterations we have to go through, which means that it takes a lot longer. With DES, we only had a 56-bit key, so it was relatively easy to break. SHA-256, for example, is considered to be much stronger than MD5 because it uses a 256-bit key, or, well, it generates a 256-bit output. GPUs, graphical processing units, which have been developed to with high CPU power, a lot of memory, a lot of operations per second, have revolutionized this idea of brute force because we can now use these GPUs as secondary processors to perform these functions. All right, because they have these ALUs, and ALUs are used to perform repeated mathematical calculations. All right, I don't know that we need to get into the details of what an ALU is, but yeah, they're just really, really powerful computing resources. All right. And they're ideal for that reason to perform these brute force attacks. How do we protect against brute force attacks? Strong password policies, complex, lengthy passwords or passphrases, policies that require us to change our password on a regular basis, password history retention policies, etc. Quite frankly, the simplest way to protect from a password authentication perspective is to use some sort of multi-factor authentication method. Simply relying on password authentication is just not that common these days. Reverse engineering is another method. We might buy a crypto product from a competitor and then try to reverse engineer that product. And not because we want to design our own product, but because we want to maybe find weaknesses in that particular product or gain knowledge about its proprietary operation. Random number generators. These have been successful against SSL, particularly many, many years ago. Random number generators became too predictable. And we'll see how random number generators, by the way, play a role in encryption later on when we look at the actual different chaining methods. So the older, kind of more original net random number generators were very predictable. We could kind of guess those random numbers, which then defeats the whole purpose of having the random number, which made the attack much more successful. Temporary files are something to consider as well. As files move through the computing system, they're stored in memory, they're stored in RAM. We might even have some files that are temporarily stored on a hard drive, and those files can contain information that would lead us to useful information for breaking cryptographic processes. All right. Next thing we're going to take a look at is we're going to take a look at some of the different types of ciphers that exist. Well, there's really only two, a stream cipher and a block cipher. And so we'll take a look at, by definition, what a stream cipher is first. Basically, we take plain text data in a stream cipher, stream-based cipher, and we combine them with a key stream. Not a key string, a key stream. The analogy I use to describe how we encrypt data with a stream cipher as opposed to a block cipher is, let's say the analogy for a block cipher. I want to fill a bucket up with water, and I want to add food coloring to change the color of the water to purple, whatever. So I fill the bucket up with water, I add the food coloring, I dump out the water. I fill the bucket up again, I add the food coloring, I dump out the water. That is kind of how a block cipher works. We're operating on blocks of information at a time. A stream cipher operates on the data as it comes out of the end of the hose. So I'm actually adding the drops of food coloring literally as the water leaves the end of the hose. So we're operating on bits of data at a time, not bytes or blocks of data at a time. Each plain text digit in this case is going to get encrypted one at a time with some sort of corresponding bit of or digit of the key stream. And then that would end up resulting in the ciphertext output. Since encryption of each digit is kind of dependent on the state of the cipher, we also call this a state cipher. All right, we'll take a look at, obviously, at different modes of operations for block ciphers and stream ciphers and so on. And there are many different types of stream ciphers. We don't really get into that discussion. You know, what is a binary additive stream cipher versus a synchronous stream cipher, self-synchronizing stream cipher, and so on. It's not important that you understand down to that level, what these, how these specific functions work. We will look at it from a block cipher perspective when we look at AES a little bit later on. Stream ciphers tend to be used, though, for their simplicity. And they're very easy to implement in hardware. We don't have to store large amounts of information. We're not making calculations or executing against large amounts of information. So they're very fast and very efficient. If a block cipher were to be used in an application that requires that speed, we would need to choose to either select whether or not we're going to have transmission efficiency in that case, or if we're going to have implementation complexity. We cannot, with a block cipher, we cannot directly work on blocks shorter than whatever the block size is. And we'll get into block ciphers a little bit later on. But if you have a 128-bit block cipher and you receive separate 32-bit blocks of data, plain text information, we would still have to fill up the block with other information. We can't just simply leave the rest of the block empty. So we would have to have a lot of padding, which means a lot of overhead, and so on. So stream ciphers work very well with in military applications, and they're just very, very efficient. The different fish algorithms are stream-based. I'm trying to think of some of the more common. RC4 would be one of the more common ones. That's the encryption method that was used in wireless back in the 80s, right? That is RC4 is a stream cipher. SEAL, SEAL, mid to late 90s. I'm trying to think of kind of the latest one. We don't deal with stream ciphers too much nowadays. They're not very common. I would say probably VEST maybe. VEST was created in 2000 and like the mid 2000s. But anyway, that's the function of a stream cipher. We perform encryption on a bit-by-bit basis, most commonly associated with streaming applications like voice or video. WEP used RC4, as I mentioned, Rivest cipher. RC stands for Rivest cipher. Ron Rivest created it. New wireless cryptography implements block ciphers. AES encryption, for example, is used with most modern encryption mechanisms in wireless. And that's because computing power is much more powerful, and mobile devices and computers are much more powerful, and they can operate on those blocks of data very efficiently. The cryptographic operation for a stream-based cipher is to mix plain text with a key stream, not a key variable, but a stream of bits that get generated by the crypto system, typically an exclusive OR operation, which is an extremely fast mathematical operation. I mean, 000, 011, 101, 110. Pretty simple, right? And it's XORed with a seemingly random key stream. Why would it be seemingly random? It can't be random because we're still going to have to decrypt the data at the other end. So it's not a completely random key stream. Let's see some of the rules. The key stream should not be linearly related to the crypto variable. Knowledge of the key stream output does not disclose the crypto variable or the key stream that was used to do the encryption. It needs to be statistically unpredictable, meaning that there has to be a pseudo-random behavior. We can't use frequency analysis to derive the plain text or even the key stream from the crypto text. It needs to be statistically unbiased. There should be as many zeros as there are ones, and as many double zeros as there are 0 ones, 1 zeros, and double ones. There has to be long periods of without repetition. Now, you might say, well, how is that possible, right? Because we only have 2 possible values that we can represent. So yeah, you don't want to have 1 1 1 1 1 0 0 0 0 1 1 1 1 1 0 0 0 0 1 1 1 1 1, that kind of thing. That's the repetition they're speaking of. It has to have functional complexity. I mean, if you think about the process of a stream cipher, it's pretty basic. We don't have rounds of operation. We don't have different confusion techniques. I mean, we're pretty much performing only one mathematical function to do the encryption. So that makes it, potentially easier to break, I guess. The key stream must be strong enough to not be easily guessed or predictable. In other words, over time, do we start repeating the bits of the key stream? If the key stream is too short, then we can start to do frequency analysis. All right. Again, the key stream are the bits that are inputted into the system as part of this encryption process. What is a block cipher? Block ciphers, which are much more common, are encryption mechanisms that operate on blocks of data. Plain text gets fed into the crypto system. It's divided into blocks of data. If it's a multiple of the ASCII character set, 8 bits each. So we are using binary equivalents for block sizes. That's why you're going to see block sizes that are represented in the powers of 2 format, to the power of 6 or to the power of 7, to the power of 8, etc. 64 bits, 128 bits, 192 bits. But most block ciphers use a combination of confusion techniques. And we will actually see this, maybe today, but certainly in the morning, how these block ciphers actually work. And I think it's perhaps one of the more interesting aspects of this entire section, because we get to see how the Rindell algorithm works. AES is certainly one of the most popular encryption algorithms today. We're going to get to see, in essence, literally how that algorithm works. We make blocks, makes a block cipher relatively stronger because of the combination of iterations and permutations that we go through than most stream-based ciphers, but it's also much more computationally intensive. And that's relative, obviously. Computing power is less expensive than it used to be. Many stream-based ciphers are implemented in hardware, and block-based ciphers are implemented in software. And that has to do with speed, right? Speed of computation. If you can imagine, even though a stream cipher is relatively, comparably less complex, it has to operate at a faster speed. So it's going to be done in hardware, and the block ciphers are going to be done in software. Not that you can't implement block cipher computations in hardware. There's certainly instances where you can do that. This concept, the initialization vector, is, from a cryptography standpoint, a pretty important concept. Sometimes called a starting variable. It is a primitive that we use mostly in the initial state of encryption. And it is either some sort of random or pseudo-random value that is generated using a random number generator, or in some kind of seemingly unpredictable format. In the case of block ciphers particularly, it is imperative that we introduce some sort of randomization for the encryption scheme. We have, in essence, an encryption process that is consistent and constant, regardless of whatever mode of operation that we're operating in. We have different modes of operation for block ciphers, and we'll get into the different modes of operation, the different block cipher modes of operation a little bit later on in this section here. But those modes of operation are consistent. We essentially perform the same transactions over and over again. So without having that cryptographic primitive in the beginning, there is no randomness to the process. And over time, we would be able to kind of identify, commonalities between the plain text and encrypted text and so on. And so initially, that initialization vector gets injected to kind of create that randomness. All right. And visually, we're going to see this a little bit later on. It'll make a little bit more sense when we look at the flow charts that I created. But it's absolutely critical. All right. And we'll look at the different modes of operation. Like I said, there are many, many different modes of operation. We have electronic code book, cipher block chaining, cipher feedback mode, counter mode, output feedback mode, lots of different modes of operation. It's basically just how we perform the iterations of encryption as a whole, as a cryptographic system as a whole. All right. The size of the IV that we inject into the system depends on whatever cryptographic primitive we're using. Typically speaking, it's going to be based on the size of the blocks that we're operating on. Typically, it's going to be the best size, or the best size is going to be the same size of whatever block we're operating on. So if it's a 128-bit encryption mechanism, we're going to have an 128-bit IV, just like we would have a 128-bit variable, a crypto variable as well. All right. The properties of the IV depend on whatever cryptographic scheme that you're using, but ultimately the end goal is to have some sort of uniqueness. No IV is ever going to be reused, at least for the same keying process. If we are using block ciphers and we have repeated IVs, we could maybe potentially introduce additional weaknesses and devolve that encryption scheme down to something that's somewhat predictable. If I have equal IVs, and actually let me explain this, because this is kind of the whole point here. I take my plain text, all right, and I send that into my algorithm. Well, not the algorithm, but the cryptographic system, right? Which includes the algorithm, but it includes also the mode of operation. If this never changes, and the crypto variable, the key, never changes, then the ciphertext output is going to end up being the same as the plain text input. Not the same, but it'll be predictable, right? Every time I encrypt that data, I'm always going to get the same ciphertext output as long as I'm putting the same plain text input into the system. All right. Now, if I introduce an IV, which is a nonce, it's a number that's typically only used once, into that system, visually we'll see how that looks later on, but if I put that IV into that system, it changes that behavior, right? This ciphertext output is going to be unique every single time I perform the encryption. And that's really the idea of having this initialization vector. All right, let's consider a scenario, right? Alice wants to encrypt a message using cipher block chaining mode. We haven't talked about what cipher block chaining mode is yet, but let's say that she uses cipher block chaining mode. And Evil Eve, somehow or another, is able to look at these encryptions and is able to even forward the plain text message that Evil Eve wants to be encrypted to Alice for encryption. All right, so this is what we call a chosen plain text attack. Now, let's assume that Alice sent the message with an initialization vector of A, all right? And we had the ciphertext block that we inputted and the plain text block of, not the ciphertext block that we inputted, but the ciphertext block that was outputted. We have the plain text that kind of identifies the plain text block of Alice's message. And then we're putting that through some sort of encryption system. What would end up happening is Eve can now determine what initialization vector B might be in the next message. And then Evil Eve can then test that guess by forwarding the plain text message to Alice with the IV2. and there was some sort of XOR operation with IV1, which is XOR'd with the plain text data that Eve presented, and then we are able to identify the scheme, the IV scheme that we're using for the cryptography. That's assuming that it wasn't random, right? That the randomization scheme wasn't selected correctly. I don't know if that made a whole lot of sense. It probably would have been better if I would have drawn a diagram, but we'll see some diagrams later on how this plays out. We know that block ciphers process data, and based on the mode of operation, we identify how encryption takes place. If I am using a stream cipher, the IVs are actually loaded into a state machine within the cipher. And we go through the process of taking that key stream, relating that key stream or computing that key stream with the initialization vector to derive a pseudo-random key stream that we use then for our encryption. All right. I don't know if that made sense or not. You know, you can kind of get in the weeds with this a little bit, and it takes a little bit to kind of break it down, but I do have some good diagrams later on that will help us understand how this process works. So let's go through these bullet points. It's an arbitrary number used along with the secret key for encryption. It's called a nonce. Nonce literally stands for a number used once. It prevents the repetition in data encryption, so it's more difficult for the hacker to use dictionary attacks or frequency analysis to find patterns to break the cipher. As an example, the sequence might appear twice or more in the body of a message. And with repeated sequences in the encrypted data, we could assume that those sequences in the message are identical. That's without the initialization vector. The IV prevents the appearance of corresponding duplicate characters or character sequences in the ciphertext. Several modes of operation have been invented which allow block ciphers to provide confidentiality for messages of arbitrary lengths. We'll look at the different modes of operation later on. The use of various modes answers the need for unpredictability in the key stream. Even if the same key is used to encrypt the same message, the ciphertext will be different each time. Not because we're changing the rounds of operation, not because we're changing the encryption method, but we're adding this crypto variable. So these are some different modes of operation. ECB as an example, electronic code book. As far as how it works, I'm going to defer that to later on when we actually look at the flow diagrams that I created to demonstrate how each of these encryption methods work. ECB, if you can imagine, we've got multiple encryptions that are taking place, but they're all independent of each other. What is the usage? Any file with non-repeating blocks, such as the transmission of DES keys or short executables. Really not used that much anymore. Cipher block chaining, as the name implies, the output of one block provides some input to the next block. This is typically going to be used for data at rest, standalone encryption, encryption on hard drives, etc. Cipher feedback mode. The cipher is used as a key stream generator rather than for confidentiality. Each block of key stream comes from encrypting the previous block of ciphertext. Doesn't make any sense? Got to see it visually. It makes much more sense when you look at it visually, but it's retired due to the delays imposed for encrypting each block of key stream. Output feedback mode. The key stream is generated independently of the message. Also retired because of avalanche problems, meaning that there wasn't enough of an avalanche effect. And finally, counter mode. So these two are kind of out. This one's kind of legacy. So counter mode, the key stream generator, we're using a formula, base plus n, where the base is the starting 64-bit number and n is a simple incrementing function. Again, doesn't make any sense. got to look at it visually. We'll take a look at that a little bit later on. High-speed random access encryption is needed. Examples are WPA2 and content scrambling systems. So we can kind of see really that there's only two modes that we would probably see on a regular basis, and these are the ones that we would tend to focus our attention on. Cipher block chaining mode, which is very common, and counter mode. We're not done with this discussion yet, though. We've got a lot to talk about with these different modes of operation. So I know we've kind of already gone through this, but I'm going to go through the process again. Consider how block ciphers are used with various modes of operation. We just saw that on the previous slide. The simplest mode is ECB, where plain text is divided into blocks and each block is encrypted separately. So literally we have, 1, 2, 3. We got our plain text and our ciphertext, plain text, ciphertext, plain text, ciphertext. There's no relationship between those encryption steps. There's no feedback. There's no input from an output. Everything is just encrypted separately. In cipher block chaining mode, blocks of plain text get XOR'd with the previous ciphertext block before it gets encrypted. So if you can imagine visually, you've got your initial plain text that you want to encrypt. You go through and you encrypt that. You get ciphertext output. You got another round of plain text that you want to encrypt, but we XOR it with the ciphertext output, and then we continue to do that as input and output. Every iteration or every step is chained together. That's what cipher block chaining mode is. In ECB mode, the same plain text will encrypt to the same ciphertext as long as we have the same key. Because there's no feedback, nothing changes, right? CBC does allow us to hide patterns because there's more confusion. We're taking the ciphertext output of the first round and XORing it with the plaintext input of the second round, but there could still be some patterns that are demonstrated if I have similar plaintext being encrypted using the same key. So we avoid this by adding the IV block that starts the key stream randomization. We don't add an IV in every round. We typically only add it to the first round, especially when we're dealing with CBC, to introduce that randomness. We don't need the IV to be secret. We just need to make sure it's not used every time. Because again, it is all about work factor. It's all about being able to identify repeatable patterns in the ciphertext output. The initialization vector is not a password. It's almost like a salt, if you will. It's public, it's published, but we don't want to reuse initialization vectors. They need to be randomly generated each time. One of the other aspects of any cryptographic system that makes it more secure inherently is the length of the key. The length of the key is generally directly associated to the work factor for crypta analysis or the overall strength of the cryptographic process. And generally speaking, the encryption algorithms that have shorter keys are considered to be less secure. Now, that's not to say that that's the only consideration that we have. There are many other considerations that we have to take into account when it comes to cryptography, weaknesses in the overall algorithms and processes, etc. But if I have a 56-bit key as opposed to a 168-bit key or a 128-bit key or a 256-bit key, it's going to be significantly different. Symmetric algorithms are designed with security equal to the key length. The longer the keys, the more computationally expensive those algorithms are. All right, which makes discovering or deciphering the key more expensive. It's going to require more resources, more time, etc. So key space, key length is also referred to as key space, is pretty critical. Block size. If I'm dealing with a block cipher, the block size just simply indicates how much data I am operating on. A block cipher has generally the size of the blocks of the data that I'm operating on generally have a direct relationship with the key space. So if it's a 128-bit algorithm and I'm operating on 128 bits of data, most likely I'm also using a 128-bit crypto variable. All right, and again, we're going to see exactly how a block cipher works when we break down AES later on. We do have to have full blocks if we are operating on blocks of data that don't fill the block size. We have to add padding bits to that block. So we're always encrypting the same amount of data every time, even though some of that information might not be, might not contain any actual data. What is the encryption system? Right now, when we talk about encryption or cryptography, a lot of people think, okay, well, AES is an encryption algorithm. AES is an encryption system. AES with CBC would be like an encryption system. Implementing AES with cipher block chaining. That is the encryption system. The algorithm is actually the underlying function of the encryption system, the underlying encryption methodology. So for in the case of AES, that would be the Reindel algorithm. So AES is not actually an algorithm; it's more of a system. So we will take a look at how that encryption system works. Well, initially we're going to just simply look at how the algorithm works. But then when we go and look at the cipher block chaining mode of operation, we'll see how the entire system works. If you want to understand how cryptography works, generally speaking, what are modes of operation, what are rounds of operation, what are confusion techniques, diffusion techniques, etc., you need to really understand how an algorithm works, and that's why we go through the implementation of AES a little bit later on. All right. All right, we're getting there. We're getting there. What is a null cipher? A null cipher is what we would refer to as a concealment cipher. It's where we take plain text and then we simply mix it with a lot of non-cipher material. As an example, probably one of the most common examples is steganography, right? We're not using cryptographic features, but we are hiding data in plain sight, if you will. All right. It is a cipher defined as a secret or disguising way of writing code. A null cipher may be used instead of encryption. If we're doing testing or debugging, or we need a low level of security, where we only are concerned about authentication, we might use a null cipher. IPsec and SSL offer kind of null cipher variables, if you will. Like in the case of IPsec, we have IPsec AH operations, authentication header operations, that doesn't include the use of encapsulated security payload. So a null cipher is, as an example, is well, just hiding information in plain sight. Let's take an example, right? Let's say that I wrote a letter, and the letter looks relatively harmless, and it's, if you were to capture or see that letter, it would look like a love letter, or it looked like a letter to a family member, or whatever. So there's nothing encrypted about it, but there is something hidden in the message, right? So you send that letter to somebody and you say, hey, I'm going to send you this letter. I want you to write down every fifth word so that you can see the hidden message, the hidden text. In that way, we're not really generating ciphertext. The message is sitting there in plain text. You just have to know how to decipher that message by using some sort of methodology. All right. This was very, very common. I used to watch a show. I forget what channel it was on. I don't know if it's still available on Netflix or not. It was called, or whatever channel it was on. I think it was actually on Netflix, called Turn, T-U-R-N. And it was about Washington and his spies and all of the different ways that they use different methods of encrypting data and sending secret messages and so on. It was very, very interesting. The reason I thought of that is because there was one particular method they used where they had this letter, right? And it just looked like a regular letter. No big deal. Somebody got that letter. They would read it. They'd say, oh, that's nice. It's a love letter or whatever. And then they would have this sheet of paper with holes in it, right? And that would be your key. And all you do is take that piece of paper and put it over the letter, and you would just read the letters that showed up in the holes. And that would become your secret message. That is a perfect example of a null cipher. We're not actually encrypting anything. Everything is just kind of in plain sight. All right? And then we see the example at the bottom. Interesting home addition to expand behind Eastern Dairy Transport intersection. Meanwhile, everything. Now you might read that and go, well, that person doesn't know how to write. But then you go and say, okay, take the first letter of each word, and then the message decodes to I hate bedtime. All right? It's kind of cryptography that you learn about in high school and stuff like that. All right, let's take a look at some other ciphers that might be used. The Playfair cipher, which is referred to as a substitution cipher, used in the 20th century and during the Allies in the Second World War. We send we agree on a word. In this example, the word is triumph. We construct a table using that word. Oh, thank you. Appreciate it. We construct a table using that word and the rest of the alphabet. So you can see the black boxes there represent triumph. But because of the size of the box, we had to use one letter twice. So we decided to use I and J twice because they look similar to each other. And this essentially becomes my cipher, my key, if you will. Okay? And then I come up with some sort of methodology for deciphering the real message that's hidden in the block of information. So the keyword is highlighted. It wouldn't normally be highlighted in the real world, but it is highlighted so we can see it easily here. And let's say I wanted to encrypt do not accept offer. And we would do that by grouping plain text blocks into two-letter blocks and spacing those repeated letters in a plain text file with a filler letter X. All right? If I had two repeated letters. I know that doesn't make a whole lot of sense, but thankfully we kind of break it down on the next page here. All right. Oops. There we go. I went too far. So the plain text would be do not attack, right? There's my do not. A, CX, CX, those are my T's. Or do not accept, sorry, those are my repeated X's. Do not accept offer, okay? And the X's are there because we have repeated letters. Now this is not by, I don't know if this is originally designed into the cipher or if this is just an example, but how did we derive FLOQ, IJ, PAZ, AZ, DHIJL, etc. from that plain text block? I'll have to kind of go back and forth here, but we'll take a look. We read the table and we look at where the two letters of the block intersect. So if we take DO as an example, and we go back and look at this table, let me go back and look at the table. DO here and here. So I'm going to create kind of a square or a rectangle that encompasses those two letters. Again, this is just the process that I would go to derive the ciphertext from this process. It's a documented process. So how did DO become FL? Well, if you look at it, in this particular case, we say, okay, DO, let's just take the corresponding letters on the opposite corner. So DO becomes FL. If for some reason it happened to be FS, then it would become KO. If it happened to be LX, then it would become OV, and so on. All right? So that's one iteration. So DO becomes FL. All right? Now what about NO? If I go back and I look at NO, I can't create a box, right? NO are right next to each other. I could create a box this way. So GS would be KQ, BK would be CG. But in this particular case, I don't have a box, I don't have a rectangle, I don't have a square. I just have two letters that are next to each other. So I have to decide how I'm going to translate that. And it got translated to OQ. All right? So we take that plain text block of NO. Both of those letters are on the same row. The ciphertext of those letters would be encrypted as OQ. Well, how did they do that? It looks like they just did a shift, right? They said NO. I'm just going to go ahead and shift over one space, and that's going to become OQ. So AB would become BC, VW would become WX, and so on. You get the idea? And we go through this process iteratively until we end up with the ciphertext output. What about OS? OS, now we have a different scenario here. OS, they're in the same row. So would that become potentially QV? It depends on what the substitution is. In this case, let's see what it became. OS would become QL, the next letter after O and the next letter after S being L. So they're actually doing the same method, right? What was it? It was, what were the two letters? Let me see here. OS, okay. So OS became QL. So they didn't go down to the next row. So O shifted over to Q, S shifted back to L. So they didn't go down to the next row, they just stayed in the same row. This is an example of just a simple substitution cipher. Now, is this secure? Probably not. But it is depending how complex this block becomes or how random this block becomes, you could add two blocks, you could have two secret words. There's all kinds of ways that you can add, make this more complicated to make it more difficult to decipher. But you could see how this would definitely be susceptible to frequency analysis and whatnot, because we're not really changing anything, or we're not really modifying data, right? I mean, we're modifying it, just not significantly. Okay? What is a transposition cipher? Many crypto systems, including AES or the Rindell algorithm, use the principle of substitution, exchanging one letter for another. But a crypto system that uses transposition or different permutations of transposition provide us additional confusion. We're trying to conceal the message by mixing the message, but mixing the message in a predictable fashion. Not predictable from the cyber attacker's perspective, but predictable from the encryptor and decryptor's perspective, Alice and Bob. Rail fence, using kind of a shift cipher, right? The message is written on a couple of different lines. Actually, this is not a ROT cipher. This is transposition cipher. Purchase gold, oil, and oil stocks. We write that message. Now, if you look at this, if you were to read it this way, it might look like randomness, right? In fact, you would write it that way, PRHSGLAD, etc. But frankly, if you just look at it this way, purchase gold and oil stocks, right? Pretty simple. Because the letters are the same as the plain text, we're not actually doing any substitution. Very, very susceptible to frequency analysis. Most of these basic ciphers are susceptible to frequency analysis, but this is what we call the rail fence. I don't see this used too often these days. Substitution tables, on the other hand, what we call S-boxes, what I call S-boxes, are used quite often. In fact, in Rindell, we use a substitution box or an S-box to perform one of the operations within the rounds of encryption. The sender and receiver decide on the size and the structure of the table that's going to hold the message. We see purchase, the same message, purchase gold and oil stocks. We place that into this rectangular substitution block. Now, if I was to read that table in a top-down manner, PAL, OO, USDIC, REA, etc. If we can agree on how to read the box, and if that method is confusing enough, we could potentially, hide the message. Now, this might work for a fifth grader, hiding messages from the teacher. You can imagine writing a note like this and to somebody in class, and the teacher gets it and looks at it and goes, "What is this? Are you playing some kind of game or something?" And as long as they don't understand, how to read it, this message anyway. If they had this, they would probably figure it out. But if that was the message, I don't know. That's just gibberish, right? All right. Another type of substitution cipher is a monoalphabetic cipher. We also have polyalphabetic ciphers that use multiple kind of substitution alphabets, but the Caesar cipher, we saw that in the very beginning of this chapter, or this module, is a very simple substitution algorithm where we just simply shift the plain text over 3 spaces to create the ciphertext. So A, B, C, D, E, F, G, all the way up to Z gets offset by 3 places, and then we scramble the alphabet, which would add additional confusion, right? Instead of D, E, F, G, H, I, J, K, L, M, N, O, P, we would scramble it around using, as an example, some sort of scrambling method that's predictable. Plain text bake would be substituted with GMDW, right? So if you, I'm trying to see how they relate to each other here. Certainly the top one makes sense, right? I don't know that these are actually related to each other. This one is a very, very basic cipher. We just shifted over 3 spaces. That's it. Here, it looks like, these aren't related to each other. I was trying to see if they were kind of relating these to each other, but quite simply, the letter B is always going to be replaced with G. The letter A is going to be replaced with the letter M. The letter K is going to be replaced with the letter D, which we see here, and the letter E is going to be replaced with the letter W, which we see there. As far as the remaining letters, I'm not sure, how they decided that P is going to be a representative of a C and so on. Maybe it's just a random selection. Or in this case, they're just showing us the plain text and what the corresponding ciphertext output would be. Very basic substitution cipher. But again, susceptible to frequency analysis, because every time we see the letter G, we know that that is going to be a B. And if we see a bunch of letter G's in our ciphertext, we might be able to infer that that's the letter B because we know the language of origin, we know the general context of the message, and as such, we're able to kind of infer or identify that letter is that letter, if that makes sense. So using a monoalphabetic cipher would allow that to happen. So oftentimes you'll see the use of what we call polyalphabetic ciphers, where I have multiple substitution permeations. So rather than having just a single alphabet, I have multiple alphabets. So maybe feed gets translated to IIJC the first time because we're using, let's see, FI, yeah, we're using substitution 1 in that case, but maybe in the next round, F is going to be represented by U, and then the next round, F is going to be represented by M, and then finally for substitution 4, F would be represented by Z. So this would definitely help with breaking the ability to do that frequency analysis because it's not random, but it does tends to look a little bit more random. And if you have lots and lots of alphabets, which is really how most S boxes work, we just have 24 or 48 alphabets or whatever that there's only so many alphabets you can have, I suppose, but we have a whole bunch of different alphabets that we're working with. We'll see that actually in the Rindell algorithm. One of the substitutions that we do uses the polyalphabetic function. Here's another example. Blide de Visionaire. Believe it or not, this is the encryption algorithm that's used for the passwords for Cisco. Not the level 5 passwords, not the hashed passwords, but the level 7 passwords. Developed by the French, it is a polyalphabetic cipher. You can see that we have multiple alphabets, 26 different alphabets, really, which is just a shifted alphabet each time, right? We start with A in the first substitution, start with B in the second substitution, start with C in the third substitution, and so on. All right, so the top row of the table represents the plain text values, and the first column of the table represents the substitution alphabets. So for example, in H, if I find the plain text H, and I am using this key, this substitution key, ficklefy, well, fickle with FI again, so I guess fickle repeated. I am going to find F, that's why it's highlighted, and that is going to be the substitution. For I am going to match that up with Q. Well, we don't have Q on the list. That's going to end up, I and I, right? And that's going to end up being Q. Okay, very, very simple substitution cipher, but really effective, honestly. If this is secret, which generally it's not, but if that is secret, it would be extremely difficult to decipher that text. What's really supposed to be secret is this key. This should be well known. In fact, in the AES, that substitution box is actually well known. It's published. It's part of the algorithm. But the keying material is what's unique. All right. Just a bunch of different examples of different types of ways to confuse and diffuse information. Modular mathematics. Yes, we are going to look at modular math quite a bit. Probably tomorrow. Looks like we're going to get close to getting to our AES stuff today, but not quite to it. So we'll wrap up domain 3 tomorrow. And I promise this is absolutely the longest domain. And we should make, get through the remaining domains fairly quickly. All right. Still have a lot of information to cover, but Modular mathematics is a way, again, for us to use an alphabet to represent numbers using mod values. The English alphabet is what we call a mod 26. Why is it called a mod 26? Because we have 26 letters in the alphabet. Okay? So if we start at 0, we go all the way up to 25. That's 26 possible iterations. So that's a mod 6. The use of mod 26, that means that when the result of the mathematical operation is less than or equal to 26, whatever that calculation is, then we subtract 26 from the total, and that gives us the value that we're going to represent that character with. All right? So the cryptographic operation is, in order to derive the ciphertext, we take the plain text plus the key modded at 26, which is written as C equals P plus the key mod 26. You'll see that throughout the rest of the chapter as well. C often stands for ciphertext, P stands for plain text, key stands for the keying material. And then you'll see like a 0 or a 1 or a 2 or a 3, depending on the round of operation. So let's take, for example, the letter N. It is the 13th letter in the alphabet, all right, which is less than 26. If the key used to encrypt plain text is Q, the 16th letter, in this case, remember we're talking about what we saw previously, right? This idea that we have this keying material and there are plain text data and we're using some sort of substitution. In this case, if the key that corresponds to changing that particular ASCII character is Q, then the ciphertext equals 13 plus 16. It is 13, which is our plain text, and 16, which is our key, right? P plus K. But we have to apply mod 26 to that value. Why do we apply mod 26 to that value? Because 13 plus 16 is actually 29. We don't have 29 positions. We don't have 29 positions. It would be the 29th letter, but because it's greater than 26, we have to subtract 26, which is really mod 26. We're modifying the number by 26 places. The ciphertext becomes whatever's left over, which is 3. And in this case, this is my ciphertext output, D. Surprisingly enough, it's a very simple operation, but this operation is used in AES. It's a little bit more complicated in AES because we have a Galois field that we're working with, and we have to do a lot of work with polynomials. That's a fun thing, but we'll go through that when we get to that section. The running key cipher. The key is repeated or runs for the same length as the plain text input. So the key of feed is used to encrypt the plain text P into cheek. The key is repeated as long as necessary to match the length of the plain text input. I mean, this is not uncommon. Obviously, the key space would be much larger than just FEED, but we are kind of representing this in a way that it's kind of easy to understand. The numbers under the letters represent the value or the position of the letter in the alphabet. So C is the 2nd position, H is the 7th position, E is the 4th position, etc. Okay? The key, F, is the 5th position, E is the 4th position, and so on. So C, remember the formula. Ciphertext equals plain text plus the key mod 26, right? Now, if I look at C and F, that equals 7, right? The 7th character is H. I want to make sure that I'm doing this correctly. Oh, they're not applying it to the top plain text. They're applying it to the bottom I got to relate these together somehow. So the top one's not really related to the bottom one. This is my plain text, and this is my key in this case. So D is my plain text, do not negotiate, or do not negotiate, I'm assuming that's what that means. And the key is KS0 or KSOSDFSH. All right, so D is the third letter of the alphabet. K is the 10th letter of the alphabet. P plus K is 13. We don't have to subtract 26 because it's less than 26. And N happens to be the 13th letter of the alphabet. O is the 14th letter of the alphabet. S is the 18th letter of the alphabet. 32 minus 26 is 6, and G happens to be the 6th letter in the alphabet. You guys get the idea. N is 13, O is 14, so it would be the 2nd letter in the alphabet because we would have to take 26 minus 27, or 27 minus 26. And remember, we're starting at 0, so 0 would be A and 1 would be B, and so on. You get the idea. All right? Lots and lots of different ways of creating this confusion and, you know.
Do they ask this calculation in the exam?
Oh, no, 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 no. Not even close. Yeah. You don't have to do any math on the exam in any form. You know, no binary conversions, no hex conversions, just very straightforward questions. All right. But it's still interesting, right? It's still interesting. What is a one-time pad? It's an encryption technique that cannot be cracked. One time. You get to use it one time because you only have a single-use pre-shared key. That single-use pre-shared key is not smaller than the message that's being sent. The plain text gets paired with that random secret key, which is referred to as the one-time pad. And then each bit or character of that plain text is encrypted by combining it with that corresponding bit or character from the pad using modular addition. All right. So by definition, a one-time pad is really just a key that's only used once. You know, it's very, very simple concept. The only cipher system asserted as unbreakable, if it's implemented properly, are referred to as the Vernam cipher or Gilbert-Vernam, incorporates the use of a key, but it's only used once, and it's as long as the plain text, but it never repeats. One-time pads uses principles of running key ciphers, using numerical values of letters and adding those values, adding those to the value of the key. The key is a string of random values that have the same length as the plain text. We never repeat, compared to the running key that may repeat several times. Remember, we talked about running key on the previous slide. One-time pads are not breakable by frequency analysis because there's no frequency. All right? The key has to be as long as the plain text, number one. We've mentioned that a couple of times. The key has to be completely random, uniformly distributed. We talked about the concept of uniform distribution, and independent of the plain text. All right. The key can never be reused in part or in whole, and the key must be obviously kept completely secret. So by, you know, Sarah, you kind of asked a question about the test with regard to what you need to know and what you don't need to know. It is possible that they might ask a question about, you know, what a one-time pad is, or they may reference a one-time pad in the question, or maybe even use it as an option as an answer. So understanding what these things are, this terminology, is going to help a lot, definitely. All right?
Thank you.
What are message integrity controls? Well, the name implies kind of what it does, right? Message integrity, you know, is where we simply ensure that messages aren't being modified. In cryptography, we use something called a MAC, or a message authentication code, which is basically just a piece of information that's used for authenticating a message, to confirm where the message came from, and then, of course, also to ensure its integrity. All right. So MAC values allow us to control the data integrity as well as the authenticity of a particular message. We need assurance that messages are not modified when they're being sent from Alice to Bob. In traditional cryptography, the symmetric algorithms produce a level of message authentication. What do they mean by that? I mean, I had previously mentioned that there really isn't any concept of authentication with symmetric algorithms. And there really isn't. In symmetric algorithms, there's really no way to identify an individual sender. But you would make the assumption that the sender is trusted because they have the secret sauce. They know what the secret key is. So even though that secret key is not tied to that individual, as a private key might be in asymmetric cryptography, there's a level of trust for that individual because they know the secret information. But there's no guarantee. All right? So two parties share that key. So it does say here there is an assurance that the message is from a trusted partner. Yes, if this, right? If the key is not discovered, yes. If the key we know is the key is secure and it hasn't been identified, yes, there's some trust there. Okay? The degree of confidence in integrity of the message is because errors or modifications of the message would render the message undecipherable. We're not doing hashing in this case. We're encrypting the data. So if somebody modifies the data, it would be extremely difficult for us to actually decrypt that information if it was modified, because they could only modify, and again, this is assuming this, but it would only be modifiable by just simply randomly changing the ciphertext, which means that the mathematical computations wouldn't work. There are very specific steps that are taken to encrypt the data. And I can't just randomly change the ciphertext and expect us to be able to decrypt that information by reversing those steps. If I'm doing a Boolean XOR operation and I take a 1 and a 0 and make it a 1, that's a normal operation. But if somebody randomly changes the values and, I'm somehow getting a 1 and a 1 equals a 1, that's not a valid XOR operation. With chaining type algorithms, errors destroy the remainder of the message. Yeah, there's an avalanche effect because a one small change in the message results in big changes in the output. That's what they mean by that. We're chaining the encryption processes together using CBC, and any kind of minor change in the input would result in a massive change on the output. Asymmetric algorithms provide message authentication for real, though. Why do asymmetric algorithms provide message authentication? Because they have private certificates. We use private information to ensure the authenticity of the source, right? The private key that only that source knows. All right. So MIC itself is not an algorithm. It's just a concept in cryptography, and there are various mechanisms that can provide message integrity, but MICs are just message integrity controls, and they can come in different forms. RSA, El-Gamal, ECC have authentication. Those are all asymmetric processes, so they're definitely going to have origin, non-repudiation of origin, and authentication of origin built into them just by the nature of the fact that they're asymmetric. All right. What is a symmetric cryptographic protocol? We have symmetric and asymmetric. We've kind of already talked about this quite a bit, but symmetric algorithms use the same key for encryption that they use for decryption. This is a shared secret key or a private key, and obviously we need to make sure that both parties have that key. The issue that we run into is that we cannot send that key or derive that key over an open channel, because then there's the possibility that somebody would intercept that key and then the key material would be exposed. So there has to be a way with symmetric algorithms for us to be able to establish a shared secret key over an unsecured channel. And one of the primary methods of doing that, well, we saw that in the context of that web authentication where I was authenticating the server using PKI. And we used that public key to encrypt a private key that we were going to use for our encryption. So that's one example. Another example would be something like a Diffie-Hellman key exchange process. We're going to go through that later, where we use modular math and various values to derive a shared secret key from private and public information. Conversely, we have asymmetric cryptography, which uses different keys. Okay, so what we're seeing here is we have the sender sending plain text information. We have some sort of encryption process, could be AES CBC, right? AES with the Rindell algorithm running in CBC mode, which is cipher block chaining. The key material is going to be an input to that process, which is then going to result in the ciphertext. But in order to decrypt that data, I need to know what that cipher key is. So this is the challenge, right? How do I get that key from there to there without some bad person in the middle getting that information? And we will talk about that. All right. Symmetric key algorithms are very fast. They're very secure. They're cheap to implement. The disadvantages is with key management. We don't provide, also don't provide benefits beyond confidentiality. We don't have non-repudiation of origin because the key is not tied to the individual. We also don't have any kind of message integrity, and we don't have access control, which is a kind of an authentication concept. So oftentimes you'll see like these symmetric algorithms that are paired with asymmetric processes to add those features, to add non-repudiation, at least initially when the clients are negotiating their secret channel, much like a TLS or SSL session. And then you'll also see message integrity components added on top of that. Symmetric algorithms provide a form of message integrity in the sense the message can be modified, but once the message is modified, it would be impossible to decrypt it, assuming the message is modified without knowledge of the key. If message is modified with the knowledge of the key, then we have bigger problems. Symmetric algorithms provide a measure of access control. No key, no decrypt. No decrypt for you, right? 10 people could have a copy of the key, though. How do we individually identify those individual 10 people? Because they're all using the same key. There's nothing that ties that key specifically to that user. Make sense? With symmetric algorithms, if the key to the secret file is shared between 2 or more people, there's no way of knowing who the last person was that accessed that file. Also, it's possible for the person to change the file and allege it was changed by somebody else because the key is not tied to the individual. It's very critical when we're dealing with a crypto system, especially for important documents and so on, that we have some other methodology of identifying individual user access and individual rights access. If a person receives a file, they can change the document and then allege that it was the copy that they received. There is no non-repudiation element. All right. We're kind of repeating ourselves a little bit, but these are important concepts. So let's talk a little bit about some of these standards. I'm not going to spend as much time talking about the data encryption standard. DES is, obviously kind of an old encryption standard. It's been around
gosh, I think since the 70s. I think it was I was 3 years old, maybe 1975. It came out, became a standard in 77. And it has many successors, right? Triple DES being kind of the most common. But the problem with DES, first of all, it's a Feistel algorithm, which is notoriously bad. We have 16 rounds of operation. We operate on block sizes of 64 bits, but the key space is only 56 bits. And that had to do with the fact that we were dealing with hardware in this case. We had to be able to fit the encryption process on a chip, on a single chip. And at that time, in the 70s, that's the best we could do, was a 56-bit chip. Okay. As far as talking about the algorithm and how what rounds of operations it does and so on, I don't think it's really that important. It's certainly not a protocol that we're going to see too much these days, so I'm not going to spend a lot of time talking about it. Okay. DES operates on 64-bit input blocks and outputs ciphertext into 64-bit blocks. 16 identical stages of processing. Now, that might sound bad, but it depends on the round keys, how the round keys go into each of those 16 identical rounds. And this may not make sense yet. And this is, again, the reason why I wanted to go through AES and kind of break down AES, because I wanted you guys to understand what we mean by stages of processing, rounds of operations, individual operations, and so on. But before we go into those main rounds, the blocks are divided into two 32-bit halves. That is, in essence, what the Feistel cipher does. We break the data up into two 32-bit halves, and then we XOR a subkey value, which is the 48-bit key. And then we use our shift registers and whatnot to go through the Feistel function. I think there's 8 of them, if I'm not mistaken. Or we're operating on 8 bits at a time, I should say. And because of the chip size, we had a parity bit, so the 8th bit was ignored, which got us down to the 56-bit operating process, the 56-bit key. Because every bit has a possible value of either 1 or 0, the effective key space is 2 to the power of 56. Looks like a lot. I don't know what that number is. It's a big number. But as far as computing goes, it's not very secure. 4 modes of DES, and counter mode was the primary mode of operation for DES as it was accepted. All right. There is a key schedule involved. I'm going to defer the discussion of key scheduling to when we break down AES, because it is important to understand the key scheduling technique. The key schedule is what allows us to, I wouldn't say create random keys for each round of operation or each iteration of operation, but the round key, which is the key used for that particular round of operation, is going to be a derivative of the overall cipher key that we're using in the cryptographic process. We'll talk about that when we get into AES. All right. All right. Now, what we're going to be looking at here, and I think this is important. So let's go ahead and take a look at some of the different modes of operation when it comes to encryption. The first one we're going to talk about is ECB, the simplest one to frankly understand. And by the way, not supposed to be used anymore because of its propensity for frequency analysis and the lack of pseudo randomness of the mode. But the message basically in this particular case is going to get divided into blocks, and then each of those plain text blocks is going to be encrypted independently, kind of in parallel operations. So if we flip over here, you can kind of see the diagram here.
So we have plain text block 1 goes through whatever encryption process. In this particular case, we're referencing DES. Keep in mind that the black boxes here it doesn't have to be DES. It could be any, realistically, any block cipher encryption algorithm. We have keying material that goes into the process. We run the encryption through the encryption algorithm, and then out pops our ciphertext. The disadvantage of this particular method of encryption is what we call the lack of diffusion. Because if we were to encrypt identical plain text blocks into identical ciphertext blocks, it wouldn't hide patterns very well. So it's not really recommended for use with cryptography. And for that reason, we don't really see it being used too often. Cipher block chaining mode is a little bit stronger than ECB. Each input block produces different outputs in this particular case. We'll take a look at the diagram in a second. It's been around for quite some time. I think it's been around since the 70s. What we do is that in each cipher block chaining process, each block of plain text gets XORed with the previous block of ciphertext before it gets encrypted. Remember, XORing is that Boolean operation where we take each individual bit and run it through the XOR process to result in some change in the state of that particular bit by using that logic. Each ciphertext block in this case depends on all of the plaintext blocks that have been processed up to that point. And then on top of that, we also add an initialization vector. So that would make each message unique because we use that initialization vector in the first block. All right. So the IV and the chaining function are new in this mode of operation. Remember, we talked about the IV before. It's just simply a randomly chosen value that gets XORed with the plaintext data before we actually run the encryption through our block cipher encryption algorithm. The output of that encryption results in the ciphertext. That ciphertext is then XORed with the plaintext of the next block, and so on and so forth. All right, the initial block, like I said, is XORed with the IV, and so on. So here is a picture of that process. All right, you can see that we have our plaintext block M0. That circle with the plus in it represents the XOR operation. We have an initialization vector, which is typically going to be the same number of bits or bytes that the plaintext block presents. And that would really depend on the blocks of data that we operate on, whether it's DES or triple DES or AES. And we have our ciphertext key or crypto variable, which results in the ciphertext output for round 0. That ciphertext output goes into the next encryption round, if you will. I don't know that we would really reference it as a round. The rounds are typically something that we see internally within the algorithm itself, but you get the idea, the next phase, if you will. So we take M1, XOR it with C0, run that through the encryption process with the round key or the cipher key, and then that results in C1. All right, so the mathematical formula for CBC is that the ciphertext is equal to E, encryption, times the plaintext XORed with the ciphertext of the previous round. Now that doesn't take into account, of course, the IV, that's the CI. We would still have to consider C0, which would include the IV as well. and that's after index 1. So we would have to take into account the index 0. Decryption would be that the plain text, so kind of working in the opposite direction, is D times CI XORed with CI where -1 basically. You don't need to know those formulas obviously for the exam. It's just a way of mathematically representing this encryption mechanism. CBC has really been kind of the most commonly used mode of operation. There are some drawbacks. The encryption is sequential. It doesn't operate as a parallel operation, meaning that it cannot be parallelized. It's a hard word to say. And the message has to be padded to a multiple of whatever the cipher block size is. One way that we handle that is through something called ciphertext stealing. We don't really need to discuss that, but decrypting is also a consideration as well. If I decrypt with the incorrect IV in the first block of plain text, then that's obviously going to be corrupted, and it's going to affect all of the other subsequent plain text blocks that we have. So because each block is XORed with the ciphertext from the previous block, not the plain text, that's a consideration. Also, the plain text blocks can be recovered if I have two adjacent blocks of ciphertext. So in that sense, we can operate the decryption as a parallel operation. And that can make decryption a little bit more efficient. All right. So that's cipher block chaining mode. Pretty popular block chaining method. All right. The next one we talk about is cipher feedback mode. There are other operations. One that I did not put in here is the propagating cipher block chaining mode, but it's not a very common mode of operation. So we'll take a look at cipher feedback mode. This one's a little bit more complex. We still can't operate in encryption in parallel. I cannot say that word. Holy cow! Parallelized fashion. We can do the decryption in that way, but not the encryption, because again, the previous block is going to offer an input to the next block. The input in this case is separated into individual segments, which can be 1 bit, 8 bits, 64 bits, 128 bits, which are in fact the 4 sub-modes of CFB. It's usually going to be 8 bits because that's the size of an ASCII character. And that's going to be represented as S in our diagram. That's that individual input segment. The encryption process is going to start with an initialization vector, and that's going to be chosen, and then that's going to be loaded into a shift register. The shift register is designed to allow bits of its contents to be shifted left or right. And again, this is just to add additional diffusion to the process. It is then run through the encryption algorithm. The first 8 bits that come from the algorithm are XORed with the first 8 bits of plain text, which represents our first segment. The 8-bit segment is transmitted to the receiver and feeds back into the shift register in the next round. The shift register contents are encrypted again to generate a key stream, which is then XORed with the next plain text segment. And we continue to do that until we have encrypted all of our plain text data. If the bits are corrupted or altered at any point, all the data from that point forward is going to be damaged. So let's take a look at the diagram, and I'll kind of break this down again. Obviously, well, I don't know if it's obvious or not, but you're certainly not going to have to know this for the exam. The first two that we talked about are relatively simple to understand. CBC, cipher block chaining, and ECB, electronic code book. Pretty simple to understand. If you're going to break down cipher feedback mode to its simplest form, it uses the entire output of the block cipher, right? We can see that C0 feeds back into the next stage of encryption. So if you look at the different modes of operation, the first thing you have to understand is that we require an integer parameter, and that integer parameter has which is listed as S in this particular case. S is the message block size. That's always going to be greater than or equal to 1, but less than or equal to B, in this case, the number of bits. So it's obviously a little bit more complicated, I guess, if we could say. But we can see that the operations are chained together, much like CBC. Changes in plain text are going to propagate forever through the ciphertext. Well, at least on the encryption side, we cannot run operations in parallel. We have to run the operations consecutively in series. The cipher feedback mode, we'll talk about counter mode as well. They have advantages over traditional CBC mode, which is that the block cipher is only ever used in the encryption direction. And so for that reason, in this particular case, we don't have to add padding. We don't have to do any ciphertext stealing, and so on. All right. Let's see. Do I have other ones? I think I might have one more here. Output feedback mode. Yes. Output feedback mode makes a block cipher essentially turn into a synchronous stream cipher. We generate key stream blocks. Those key stream blocks are XORed with the plaintext blocks to get the ciphertext. So like with any other stream cipher, flipping a bit in the flipping the bit in the ciphertext is going to produce a flipped bit in the plaintext in the same location. So it's very similar to the operation of cipher feedback mode, but instead of using the ciphertext result of our XOR operation, we look at cipher feedback mode here. This is the XOR result of the encryption operation. Instead of using that to feed back to the shift register for the key stream, notice in this case, we say the cipher key is the number of bits of the cipher key, but this ciphertext block is providing input to the next round, and it's not. If you'll notice here, the plain text information doesn't get XORed until after we've gone through the process of taking values from the initialization vector and the shift register and components of the ciphertext block output. Run that through the encryption algorithm with the cipher key. We take that output, we take a number of bits, which is the message block size, that's the orange highlighted area there, and then we XOR that with the plaintext block in the next, the next plaintext block, which then gives us the ciphertext block output, and that feeds back into the next iteration, if you will. Very similar to CFB, but we're using the ciphertext result of the previous XOR operation to feed back into our shift register for developing the ongoing key stream. That feeds the encrypted key stream itself back into the shift register to create that next component, that next S component of the key stream. The key stream and the message data are completely independent. The key stream is chained, but no chaining of ciphertext, meaning that we're not XORing the entire block of ciphertext. We're taking a portion of the ciphertext so that we can generate the key stream. All right. This is output feedback mode visualized, right? We have our initialization vector. We go through our encryption process, which results in our output S bits, which get XORed with the same amount of bits from our message text, our plain text message text, which results in the ciphertext. But notice in this case, unlike the previous example, cipher feedback mode, by the way, it's called cipher feedback mode because we're taking the ciphertext and it's feeding back into the system for the next round of operation, right? In this particular case, output feedback mode, because the ciphertext is not what's feeding back into the system, it's the output of the encryption process that's feeding back into the system, if that makes sense. All right. So is it important to know all these different modes of encryption? And we looked at this table previously, or we looked at the table previously on how these modes were used, and it ended up being that there were only two modes of operation that were really kind of used today, and that would be one of the things that you'd want to know. In this case, do you need to know that the output, looking at this diagram, the output feedback operation depends on all of the previous operations? Well, I guess, but the reality is that every one of these, that's the case, right? The only one that doesn't do that is ECB, where we're doing the encryption and parallel operations. All right. I would say that this is more for your information to kind of visually identify how these operations take place. I wouldn't spend too much time committing this to memory just for the exam. All right. And by the way, output feedback mode, as you can see here, as well as counter mode, are stream cipher are considered stream cipher modes of operation. The rest of them that we talked about are more for block ciphers. Okay. All right. Counter mode turns a block cipher into a stream cipher as well. It generates the key stream block by encrypting successive values of a counter. That's why it's called counter mode. The counter can be any function that's going to produce a sequence which is guaranteed to be completely random, right? Not completely random, but at least not repeat for a very long time. Incrementing by 1 would be an example of a counter that's going to repeat. Now, it is a finite field, so even incrementing by 1 means that eventually we're going to have to repeat, but not for a significant amount of time. All right. This is used in high-speed applications like IPsec or ATM. A counter, a 64-bit random data block, is first used as the initialization vector. The counter must be different for every block of plaintext, so each subsequent block counter is incremented by 1. the counter is encrypted like output feedback mode, and the result is used as the key stream, which then gets XORed with the plain text. Because the key stream is independent from the message, it can process several blocks of data at the same time, meaning that we can operate in parallel encryption and decryption mechanisms. Notice there is no feedback here. There is no feedback. All right. So visually, this makes sense. Counter mode was actually created by two very, very important individuals in the realm of cryptography, Whitfield Diffie and Martin Hellman. Diffie-Hellman. We'll talk about Diffie-Hellman a little bit later on. So there are similar characteristics in counter mode to output feedback mode, but counter mode is going to be much more suited for something that's going to be able to operate on multiple things at the same time, like a multiprocessor computer, and because we can encrypt in parallel. So the initialization vector is going to be random. That would typically be combined with the counter, and we can see the operation visually represented here. All right, there are some pretty decent videos on YouTube that kind of break these concepts down further and actually give you an idea with real data how that data is processed. But keep in mind that what we're talking about here is the entire system. The black boxes in each of these diagrams represents the encryption algorithm, which could be unique, right? Could be AES, could be DES, could be triple DES, or whatever. What we're looking at with these different modes of operation is just how we implement the rounds of encryption. So let's say, for example, that we're using AES. The black box is going to have, even in and of itself, is going to have multiple iterations of encryption. And then we'll take that encrypted information and process it through this system, ultimately getting our final ciphertext block, which is always our goal in the end for the final confusion, I guess, if you will. All right. There are other elements of or other modes and other cryptographic primitives that we can operate with, but again, it's not really critical that you understand those elements. I think this is an interesting subject, and ultimately I think that we could have a class by itself just to talk about these elements of cryptographic operations. But we got a lot of other stuff to cover, so we're going to continue forward here. What are some of the disadvantages of DES? First of all, because of the key space, it is very susceptible to brute force attacks. The key is only 56 bits long, and it could be determined by trying different possible keys against ciphertext until we discover the plain text that generated that ciphertext. And then knowing that, of course, we would know what the key material is, because that would be the only way to derive the plain text from the ciphertext and vice versa. DES can be deciphered using computing power and persistence. Criticisms of the structure of the DES algorithm exist as well. I'm not sure what those criticisms are, but obviously this is a legacy protocol. So I would imagine that there were few considerations relevant to what we see today in modern cryptography, right? The design of the S boxes that's used in the encryption and decryption operation was secret, and that might sound like a good thing. That components or elements of the encryption process is secret. But if we don't know how something works, we can't necessarily trust it. The components or elements of AES, for example, are not secret. We know exactly how the operation works in AES. We know what the S boxes are. We know what the different functions are within the different rounds of encryption. So it can be trusted. We understand exactly how it's functioning against the data. All right. What is a meet in the middle attack? As the name implies, the meet in the middle attack, which by the way is a known plaintext attack, is what we would define as a space-time trade-off in Crypta Analysis, because it relies on performing multiple encryption operations in sequence. It is a known attack which exponentially reduces the number of brute force permutations required to decrypt encrypted text by more than one key. We'll see a visual representation of this in a minute. Meet in the middle attack targets the block cipher cryptographic functions. So not stream cipher, but block cipher. The attacker applies brute force to plaintext and ciphertext of the block cipher. So if you can imagine, the plaintext is on the left, the ciphertext is on the right. If we're trying to attack both sides, ultimately we would want to meet in the middle, and meet in the middle would be where, essentially where we discover the key. All right. When we were trying to improve the security of a block cipher, it is kind of intuitive to say we're going to encrypt the data multiple times using different keys. And if you do that, you might think, okay, that's going to double or triple or quadruple the security of this scheme, right? Of this multi-encryption scheme that we've created, depending on how many times the data actually gets encrypted, because of the key space, right? We have this exhaustive search on different combinations of keys, and brute force would take a massive amount of attempts to get access to the data based on that. So a meet in the middle attack is really just a type of attack which takes advantage or weakens the security benefits of using multiple encryptions by storing intermediate values from those encryptions or decryptions and then using those values to improve the time that it's going to be required to perform the brute force of the decryption keys. So we basically, the goal here is to try to find the keys by using both the ciphertext and the plain text. And that would obviously be part of the composition, composition of different functions of the block cipher itself, and so on. So the algorithm and whatnot, we're not really concerned about that, but the idea is that we have a function for encryption and we have a function for decryption, and in the end, the goal is to try to identify the crypto variable or the key itself. All right. Attempts to encrypt plain text according to various keys to achieve an intermediate ciphertext. The text is encrypted by one key. Attempts to decrypt the ciphertext according to various keys, seeking various keys seeking blocks, key seeking block of intermediate ciphertext, which is the same as achieved by encrypting plain text. A match of the intermediate ciphertext means that it's highly likely that the key used to encrypt the plain text and the key used to decrypt the ciphertext are two encryption keys used for the block cipher itself. All right. It's called meet in the middle because that's what our goal is, right? We take our plain text block, we encrypt it with the first key. We take our, on the other side, we take our ciphertext block, we decrypt that ciphertext until we have a match, and eventually we'll be able to discover the key material. Does that make sense? Now there are variations of this as well. We don't need to get into the specific variations, but the extent of what you need to know for the exam in this particular case is really what the purpose of this particular known plain text attack is. All right. This was one of the reasons why, by the way, that we saw a triple DES variant as opposed to a double DES variant. When we went from DES, we didn't go to double DES, we went to triple DES. Speaking of triple DES, what is triple DES? Well, it's, a lot of people might classify it as essentially 3 times DES, right? It has various key sizes. I think the smallest key size is 112 bits all the way up to 168 bits. It operates on 64-bit blocks. It is a derivative of DES, so it does use the Feistel network. It has 48 rounds of operation, which are basically just DES equivalent rounds. It essentially just simply applies the DES algorithm 3 times to each data block. All right. And the reason this was developed was that the DES standard, that 56-bit key, was really not adequate with modern cryptanalysis techniques and computing power and so on, that triple DES was developed. Right now, today, obviously, triple DES is not considered to be secure either. I mean, this is a protocol that's been around since the early 80s, right? And there are obviously weaknesses in this operation because of the key space. There's actually 2 different ways to operate triple DES. We talked about the original DES cipher using a key size of 56 bits. When that algorithm was designed or when it was developed, that was sufficient. But again, because of increasing computational power, brute force attacks became much simpler. In essence, triple DES kind of provided this quick, simple method for increasing the key size of DES to protect against those brute force attacks. There's 2 approaches to the way triple DES works. The native approach was to use 2 keys instead of 1. We're going to encrypt each block twice. If the original key was, say, n number of bits, that would provide us at least a key equivalent of twice that size, right? But again, the double DES operation was known to be vulnerable to meet in the middle attacks, given that particular pair. So the keying options changed for triple DES. Keying option number 1, all 3 keys were completely independent. So you might see that written as like 3 TEA or what we call triple length keys. So that's the 168-bit variant, right? If you take 3 times 56, that's going to give you 168 independent key bits. The second option, keying option number 2, is that 2 keys are independent. So K1 and K2, we'll call it, are independent, but one key is equal to another key. K3, for example, might be equal to K1. So this is going to give us double the length of the keys. This is the 112-bit variant, and it's kind of a compromise between using 3 independent keys versus only having a 56-bit key. It is definitely an improvement, but not as strong as keying option number 1, which is to use 3 independent keys. There is another option which is never recommended. In fact, NIST says don't use it, is where all 3 keys are identical. This makes it backwards compatible with DES because essentially 2 of the operations get canceled out. You don't want to see this option. Okay, so we have a minimum of 112 bits if we're using the keying option where 2 keys are the same, but 2 keys are independent of each other. So K1 and K2 are independent, and K3 and K1 might be the same, or 168-bit version if all 3 keys are the same. All right. Still not used much today, obviously. AES has become pretty much the standard function for encryption. AES, which we're going to break down in a lot of detail shortly, is pretty much the standard that we use today. So in 1997, NIST issued a call, what we would define as maybe a competition, to replace DES and triple DES. The new algorithm had to be at least as strong as DES, operating on larger block size. It had to be more efficient but more secure, and it had to overcome kind of those performance issues that we identified with DES. DES was developed for hardware to operate specifically on a chip, and was too slow in software. Triple DES was even slower and introduced a lot of processing overhead. The product chosen, and there were many different individuals that kind of tried to propose the replacement for DES and triple DES. Ron Rivest put his design into the hat and whatnot, but the one that was chosen was the Rijndael algorithm. All right, or Rijndael, I guess it's pronounced Rijndael, it's Dutch, which is named after Dr. Joan Damon and Dr. Vincent Rijman. I think it's Ryman or Ridgeman. I don't know how they would pronounce it in Belgium. So Ross Anderson submitted Serpent, IBM submitted Mars, Ron Rivest RC6, and then RSA and Twofish. But the AES algorithm met all the different criteria. And we're going to get into the specifics of this protocol in quite a bit of detail. So AES is a cryptographic system which is a variant of the Rijndael block cipher algorithm. The Rijndael family of ciphers was used for many things, but there's different variations. We can operate on 128-bit blocks, 192-bit blocks, 256-bit blocks, and so on. There is a predecessor to this algorithm called Square. I haven't seen that in operation, but this was published in 1998. It operates on block sizes of 128 bits and primarily works on substitution and permutations, which we'll take a look at a little bit later on. Depending on the key size, you'll have 10 rounds of operation. for 128 bits, 12 rounds of operation for 192 bits, and 14 rounds of operations for 256 bits. All right, I'm not going to say a lot more about this algorithm right now because we are going to spend a lot of time taking a look at it. You know, the different operations, which include things like substitute bytes or shift rows, mix columns, XORing a round key, and so on. We'll take a look at that. All right. The techniques that are used, the substitution and permutation techniques that are used in the algorithm make this algorithm extremely efficient, whether you decide to run it in software or hardware. We don't rely on that Feistel network, which was notoriously not efficient. All right. And we'll again take a look at the details of this as we go through our next few sections here. All right, but before we get to that, let's go ahead and wrap up a couple of other definitions. CCMP, counter mode with cipher block chaining with message authentication protocol. Wow, that's a handful. Counter mode cipher block chaining message authentication code protocol, or what we would simply call CCMP, or CCM mode protocol, or counter mode CBC MAC. This is an encryption algorithm or an encryption protocol that was primarily designed for wireless networks and was implemented as part of the 802.11i standard. The 802.11i standard is the amendment to the original 802.11 implementation, and covers Wi-Fi protected access version 2, and essentially the standard just specified different security mechanisms for wireless networks. Okay, CCMP is a data cryptographic encapsulation mechanism to provide more efficient data confidentiality based on that counter mode operation that we talked about previously with the cipher block chaining message authentication code. Now, when we see a reference to message authentication code, that is going to indicate that there is some sort of hashing function with secret sauce, right? A secret key or a secret variable. This is used in conjunction with AES, the AES standard. And the primary purpose of CCMP was to add additional security over and above whatever the previous security mechanism, which was wired equivalent privacy, used in the original version of, or the original specification for 802.11 security. There were many vulnerabilities that were presented in WEP, and generally speaking, it's considered to be an insecure protocol. Okay. CCMP uses CCM. That's to say that it uses CCM mode, which we talked about as a mode of operation for our block cipher. But it's, in this essence, just an authenticated encryption algorithm designed to provide confidentiality, authentication as well, typically dealing with block ciphers that have a key length of about 128 bits. So we have a component for data confidentiality, and then we have a component for authenticity or authentication and integrity. So the CCM combines the counter mode component for the data confidentiality, and then the CBC MAC component is what's going to be used for authentication and integrity. All right. how does CCMP work? The AES is processed using a 128-bit key length and operates on 128-bit block sizes. We have 128-bit keys. We have an initial 48-bit initialization vector, and then we use the counter cipher, the counter component for data privacy, basically the mode of operation in this particular case. The cipher block chaining message authentication code component, like I said, is what produces that message integrity code. Now, keep in mind, when we talk about message integrity, right, as opposed to data confidentiality is the encryption component of any kind of cryptographic process. But obviously the data confidentiality is there to ensure that only the authorized parties can have access to the information. And I should have mentioned this before. I think I mentioned it briefly, but I'm going to restate this again. CCMP became popular in its use in WPA2. All right. When WPA came out, Wi-Fi Protected Access, WPA was kind of a stopgap measure to address a lot of the primary security concerns of the previous security standard, which is the wired equivalent privacy. And then on top of WEP, what they did is they added TKIP, the Temporal Key Integrity Protocol. And that's what generated or created this Wi-Fi Protected Access standard. So CCMP came out after WEP and WPA, which WPA was basically WEP with TKIP, the Temporal Key Integrity Protocol. I think we actually have a slide on TKIP a little bit later on. But it replaced WEP, but it didn't require that we had to replace physical hardware. The same hardware that we're using for WEP could be used for WPA because of the methods that we were using to add that additional security. When we went to WPA2, we had to change the hardware because now we're using AES encryption and the CCMP component, which provides that data confidentiality, the authentication, and the access control function. All right. So going back to the second to last bullet point here, cipher block chaining message authentication code is the component that provides proof of origin and also provides guarantees of integrity, message integrity. So just keep in mind when we're talking about CCMP, there are two different components. The counter mode, which is basically just AES 128-bit encryption, which provides the data privacy. The cipher block chaining, MAC, provides the message integrity. And then there's also an access control function, which provides additional security for the transmission. The AES encryption protocol was used by 802.11i, but that just happened to be the block cipher that was used. The actual encryption protocol was CCMP, or is CCMP, I guess. WPA2 is still used these days. All right. Now, as far as getting into the PDUs and what they look like and how the data is structured, not necessary for this class. All right. The 802.11i standard allows for the TKIP encryption as part of the 802.11i standard, which negotiates authentication and encryption algorithms between access points and wireless clients. It allows new algorithms to be added at any time and supported along with the previous algorithms. The use of AES CCMP is pretty much mandated today, which provides a higher level of security for providing protection for the MAC protocol data unit. MAC in this case is the media access control header. There's actually 5 different sections of the MPDU. The first is the MAC header, which contains the destination and source address of the data packet. And then we see the CCMP header, which is 8 bytes, and that has something called the packet number, the IV, the key ID, and so on. And then, well, we don't need to get into what the packet number provides, but and then there's other elements as well. The third section is the data unit, which is the data that's being sent in the packet. The fourth section would include, if I'm correct, doing this off the top of my head, fourth section I think is the MIC. Yeah, it would make sense because the last section, the fifth section, would be the frame check sequence. Remember, we're talking about framing in wireless, right? We're talking about wireless transmissions, which is a layer 2 concept. So the PDU is broken up into 5 sections: the MAC header, the CCMP header, and which includes things, the packet number and the key ID and everything. And then the third section is the actual data that's being sent inside the packet. The fourth is the message integrity code, which is what is going to provide the authentication of the message, as well as provide message integrity, hence the name, message integrity code. And then the frame check sequence is the last thing, which provides for error detection, not so much correction, but error detection at least. All right. What would you need to know about this for the exam? I don't recall a whole lot of detailed technical questions on the exam about these concepts, but I think it would be important to understand the progression of security in the wireless world. Starting with WEP, wired equivalent privacy, moving on from WEP to WPA, which was basically WEP with the TKIP, Temporal Key Integrity Protocol, and then moving on to WPA2, which incorporated the use of CCMP, which also required the use of AES, the Advanced Encryption Standard. The encryption algorithm that we used for WEP was RC4, the Rivas Cipher 4. Okay. All right, so what we're going to do now is we are going to start to go through the process of taking a look at in detail what this Rindell algorithm is. Now, you certainly are not going to have to know this for the exam. The reason I put this into our slide deck is because I thought it would be useful to see the process. We don't have to go through it in a massive amount of detail, but we would see the process, which would give us a better understanding in general of how these algorithms work. All right, so the Rindell algorithm is the algorithm that's used with AES, and obviously is part of the AES standard. And surprisingly enough, quite simple to understand. There are some elements of it that may be a little bit more confusing, but not for a computer, but maybe for us as humans that we don't do this stuff a lot. But hopefully, when we go through this breakdown, it'll make a little bit more sense. Now, the variation that I am using to demonstrate this process is the 128-bit variant. But it would be very similar if it was 192 or 256 bits. All right. So the key can be 128 bits. It can be 192 bits. It can be 256 bits with different rounds of operation depending on the key size. Like I said, for 128 bits, we're going to do 10 rounds of operation. We have an initial round. We have different main rounds, and then we have the final round of operation. And it is a block cipher. So we operate on blocks of data. So we work on an entire 128-bit block of input data by copying that into what we call an array or a state table. So you can see that 328831E0, actually I'm reading that wrong. I should be reading it based on the order of the bytes. 3243 F6A8 88 5A30 8D, etc. Those are hexadecimal values that represent our plain text data, right? Each of those hexadecimal characters is 4 bits in length, so 32 would be 8 bits of data. So that's the first thing that we do is we take our plain text data and we start to put it into these state tables in blocks of 128 bits. Now, what if I'm not operating on 128 bits of data? What if I'm only operating on, 30 bytes of data or 100 bytes of data? If that were the case, then I would have to add padding and so on to be able to make sure that we're still operating on the correct amount of data, right? So that's the first step. Divide the data up into blocks of 128 bits. The key gets placed into a similar block. In this case, 2 Bravo, 7 Echo, etc. All right. So we have our plain text data and we have our initial key. Now the whole operation, the whole Rindell operation consists of 4 major permutations, if you will. Substitutions / permutations. We have subbytes, which is substitute bytes. We use an S-box to do a byte-by-byte substitution of the entire block of plain text data. We'll see what that looks like in the next couple of slides. We have a shift row operation, transposition cipher, where we offset each row of the table. We have a mixed columns operation. Mixed columns operation is a little bit more complicated. We substitute each value in a column based on a function of values of the data in the column, where we're using finite math, arithmetic, and polynomials and everything else to do that. We'll take a look at that. There's a Galois field and reduction polynomial and several different things that we use to calculate those values. And then finally, we have our XOR operation, which is adding the round key. Each round has its own unique key for that particular round. And then on a side note, we have a key scheduler as well, which allows us to establish what each round key is going to look like. So this is visually what it looks like overall. We have our initial round of operation. We have 9 main rounds. And then we have our final round of operation. So these are the 10 rounds of operation. The initial round, we don't really count. So technically, I guess it would be 11 rounds of operation. But the actual permutations, there's 10 different permutations or 10 different rounds of operation where we actually have individual round keys for those operations. So in the initial round, we take our state information, which is our plain text. We take our key material. So this is our plain text, and this is our key material. Let me make that look a little bit better. And we XOR those values. That's a very, very simple operation. Each square gets XORed with each square in from the plain text data in the key data, the crypto variable. And then we go through these 4 steps, go around, go through those 4 steps, go around, go through those 4 steps, go around, go through those 4 steps 9 times. Okay? Each time we do that, we have an individual round key, which is going to be a derivative of our original key. We don't have 10 different unique keys. The round keys are variations of our initial cipher key.
All right, and then we shift down into the final round where we're only doing 3 operations with that round key, and out pops our ciphertext. All right, so let's take a look at the subbytes operation. Did I miss a step here? No. I guess I did kind of not document a step here. So if I took 32 and I XOR'd that with 2 Bravo, what I should get is 19. So I'm not going to do the whole block, but I can demonstrate at least that portion of it, right? So coming back here, I have 32 as part of my plain text data, and 2 Bravo is my key variable. Okay, so we have 32 and we have 2 Bravo. And we're going to do an XOR operation. This is the initial round that we're talking about. So 3 is 0, 0, 1, 1, 2 is 0, 0, 1, 0, and 2 Bravo is 0, 0, 1, 0, and Bravo is 1, 0, 1, 1, right? So Bravo in hex is 11 in decimal, which is equivalent to 8 plus 2 plus 1. 8 plus 2 is 10, plus 1 is 11. If I do my XOR operation, that would be a 0, that would be a 0, that would be a 0, that would be a 1. That would be a 1, 0, 0, 1, which would be a equivalent to a 1, 9. Does that make sense? I said we wouldn't do any math in this class, but you know, obviously when we're dealing with these algorithms, there's some basic math that we have to do. So this is my 32, and this is my 2 Bravo, and this is my XOR operation, which results in this output. So that's the initial round. We're just adding the round key by using this XOR operation. We can see 1, 9, 3B, E3. So this is the result after the first round, or the initial round, I should say. I'm going to put an I for initial round, okay? Which means now that we are in this phase here, which is to go through these 4 iterations. Now, I'm not going to do this 9 times. I just want to demonstrate to you guys kind of how each of these operations work. You know, we'll certainly see all of the iterations in the diagram or in the book here, but I just want to give you an idea of how each of these functions work. Okay, so now we're in the subbytes step or operation. All right, we use an SBox to look up the value of the byte in the input, and we substitute that value from the table. So the SBox contains all 256 8-bit word values, kind of randomly placed, if you will. So there's only so many combinations. 2 to the power of 8 is 256. And there's 8 bits in each of these numbers. 63 is 8 bits, 7 Charlie is 8 bits, 77 is 8 bits. So if you look, you can kind of find every single permutation, if you will. And I'm looking for one. I see F1. It should be in here somewhere. Of course, as I look for it, it's going to be harder to find. But it should go from 00 to FF, basically. We should see every permutation. I see 08, 0 Delta, 0 Charlie, 04. Why is it so hard to find 00 and FF? Anyway, they would be in here somewhere. Okay? So we take the 19. The X represents the first digit, the Y represents the second digit or the second value, which then gets replaced to D4. So you can see it's a very, very simple operation. 3 delta, 3 is here, delta is here, so that would be result in 27, and echo 3. There is echo, there is 3, that would result in an 11. Very, very, very simple operation. Not at all complicated. Every possible combination. All right. Now I know why I couldn't find the 0, 0 and the FF, because they're right here, right? There's my 0, 0, and there's my FF. Those are the combinations that we're talking about. All right. So these are all the possible. In other words, we can represent every possible combination of hex values from the state table to do the replacement. This S box is published. This S box is not random. It is predefined as part of the algorithm, right? So this is our substitution table. Very, very simple operation. Doesn't even really require any math, just replacing values. Then we move on to the second operation, which is shift rows. Actually even easier than the first operation. No shift on the first row. We're going to rotate over 1 byte on the second row. So 27 here moves over to here, and we shift everything left. So Bravo Foxtrot goes here. Bravo 4, 41, 27. So that was our 1 byte shift. And then here we have a 2 byte shift. So 11 is going to end up over here, and 5 delta is going to end up there. So that's our 2 byte shift. And then we have our 3 byte shift, which means that 30 is going to end up there, and everything else is going to shift accordingly. Very, very simple operation, right? Again, the point is that we wanted an algorithm that was efficient. Still offered security, but was very, very efficient. And obviously these operations are pretty basic for a computer to perform. So that is the second operation. Now the third operation, a little bit more complicated. All right? A little bit more complicated. So we're going to have to spend some time kind of breaking this down. Mixed columns. The mixed column operation, along with shift rows step, is a primary source of diffusion. Each column is treated as a polynomial over a Galois field and is multiplied modulo x to the power of 4 plus 1 with a fixed polynomial. Cx, 3x3, x2, x, and 2. Wow. So that seems confusing. It can be, but it's actually not as difficult as it might seem. This is the Galois field. These are the bytes that are being altered. All right, if we go back to our previous slide, we can see that we're operating on this column, D4, Bravo, Foxtrot, 5, Delta, 3, 0, and then we do similar operations on this column, and then this column, and this column. Okay? So the Galois field uses characteristics of finite fields with 256-bit elements. We use this reduction polynomial for the multiplication of the polynomials, because ultimately we still have to have an 8-bit output. When you're doing polynomial math, oftentimes it will result in a value that's larger than 8 bits. So we have to be able to reduce that polynomial to its 8-bit value. So how did I go from D4, Bravo, Foxtrot, 5, Delta, 3, 0 to 046681E5? Well, in order for us to get to that point, the first thing we need to understand is what is finite field arithmetic. Each column is treated as a polynomial. We use that reduction. It's all repeated. Interesting. Binary strings can be represented as a polynomial. All right, so this is not directly related to the algorithm. What I'm trying to attempt to do here is give you guys a better understanding of how this polynomial math works and how we can ultimately get to the result that we're trying to get to. Bit n equals x to the power of n plus 1. Bit 3 equals x3. Bit 2 equals x2. Bit 1 equals x1, x to the power of 1, and bit 0 equals 1. So again, depending on how large the field is, will determine how many x values you need. So bit n, x to the n plus 1. So bit 4 would be x to the 4 and so on. All right. So a 00110110 is x5, x4, x2, and x. Now, how do we get that? If you look at the positions, this is bit 0, which would be represented as a 1. Because the bit is off, the 1 isn't listed here. This is bit 1, which is represented simply as x. Because that bit is on, it is represented in the polynomial. This is the second or the third bit, and it's going to be represented as, well, actually it's bit 2, I should say, because we start at 0. It's going to be represented as x to the 2. Bit 3 is off, so we don't have an x to the 3. Bit 4 and bit 5 are on, so we have x4, x to the power 4, and x to the power 5. Another example, 1001, 0011. Bit 1, or I keep saying that, bit 0 is on, so we have a 1. Bit 1 is on, so we have the x. 2 and 3 are off, 4 is on, so we have x to the power 4. 5 and 6 are off, 7 is on, so we have x to the power of 7. I'm looking at this formula. This doesn't look right. I'm trying to think of why I wrote it that way. Bit n equals x to the n plus 1. Seems like bit n should just be x to the n, not n plus 1. It's probably a typo. But in any event, this is absolutely correct, right? This is how we represent binary strings as a polynomial. All right. So if I were to say XOR those values, so here's a hex 36. Hex 36 is a 0011, that's my 3, and a 0110, that's my 6, because that's the 4 and the 2, and a hex 93. This is 8 plus 1, which is my 9, and this is 2 plus 1, which is my 3. If I convert those to a polynomial, we don't have the 1. Oops, turned off my pen. We don't have the 1. We have x, we have x2, no x3, x4, x5. x5, x4, x2, and x. And by the way, I'm probably not using the right terms to describe these components. I'm not a mathematician. I understand the general concept of how the math works, but don't go crazy if I'm not using the right terms to describe distribution properties and values and whatnot. I'm trying to break this down to the simplest way possible, right? So we have 1 here, because that bit is on. We have x here because that bit is on. x2 and x3 are off. x4 is on. x5 and 6 are off. x7 is on. Now, if I were to add those polynomials together, the principle or the properties of adding these polynomials is whenever there are duplicate entries for each polynomial, they cancel each other out. So x cancels each other out, x4 cancels each other out. That's the distributed property of adding these polynomials. Again, if I'm not using the right terms, I apologize, but that's the way that I'm describing it. Okay, So what we're left with is x5, x2, x7, and 1. There's my x5, there's my 2, there's my x7, there's my 1. Here I'm just kind of reordering it. So x7, x5, x2, x1. So the 1 represents that first bit, or bit 0. X is off. There's no X represented here, so that bit is off. X2, that's the second bit, is on right here. X4 and 5, or 3 and 4 are off. 5 is on. 6 is off. 7 is on. All right. So in the end, hex 36 plus hex 93 ends up being hex alpha 5. Okay? If it was that simple, that'd be great, if that's all we were doing. We are not doing that. We're not adding polynomials. We're multiplying polynomials. This symbol that you see here is a multiplication symbol, right? So we're not adding the polynomials, we're multiplying the polynomials. So what if I wanted to multiply polynomials? I do the same basic conversion process, but then I have to distribute the values across each polynomial. And again, not using the right terms, but I'll see if I can kind of demonstrate this. We understand how we get the 3 and the 6 here. That's just our binary conversion. The 9 and the 3 here, that's our binary conversion. We also understand how this would be represented as this polynomial. The 1 is off, x is on, x2 is on, x3 is off, x4 is on, x5 is on, x6 and x7 are off. Okay? Same thing here. 1 is on, x is on, x2 and 3 are off, x4 is on, x5 and 6 are off, x7 is on. Make sense? So now, if I multiply these together, the way that I do this is I essentially distribute this across that polynomial. And I just add the exponents, because ultimately that's going to end up resulting in that powers of 2 being calculated correctly. So 5 and 7 is 12. All right. And I kind of did this in the colors. So these are the 4 values that are, so we got 1, 2, 3, 4. And then here, 1, 2, 3, 4, etc. So we got 12. And 5 plus 4 is 9. 5 plus 1 is 6. And x to the power of 5 times 1 is x to the power of 5. 4 plus 7 is 11. 4 plus 4 is 8. 4 plus 1x is 5x. And x to the power of 4 times 1 is x to the power of 4. 2 plus 7 is 9. 2 plus 4 is 6. 2 plus x to the power of 2 plus x to the power of 1 is x to the power of 3. And then x squared times 1 is x squared. You get the idea. So we got 7, we've got 5, and we've got 2. And then we have x times 1 is 1. So now we're getting back to just adding the polynomials together. Why do I have all the ones that are underlined? The reason I have all the ones underlined is because those are the ones that cancel each other out. x9 cancels each other out. x6 cancels each other out. x5 cancels out. x8 cancels out. And finally, x2 cancels out. So we have x12 plus x11, x to the power of 11, x to the power of 4, x to the power of 3, x to the power of 5, and x. All right? So multiplying these two hexadecimal values together results in that binary string, which poses a bit of a problem. Because that is a, let's see, how many bits? 4, 8, 12, 13-bit field. It's not 8 bits. Remember, we have to reduce it to 8 bits so that it can fit into our output, our state table. So we have to reduce the polynomial. And we use this, if you recall in the very beginning of this section, we talked about this reduction polynomial. X to the 8, x to the 4, x to the 3, x, and 1. So, which is this value. So if you look at the operation, we take our reduction polynomial, we XOR it with the output from our multiplication of our two hexadecimal values. And eventually we'll be able to reduce the number down to an 8-bit value. So 1 and 1 is 0, 1 and 0 is a 1. Standard XOR operation, 0 and 0 is a 0, 0 and 1 is a 1, and so on. And we keep doing that. So we've reduced it down to from a, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13-bit value. Down to 1, 2, 3, 4, 5, 6, 7, 8, 9-bit value. And eventually we'll get down to our 8-bit value. All right, we have to carry down these places until eventually we're reducing this down to an 8-bit value. All right. And by the way, we're still XORing the polynomial, and even though we've already kind of reduced it down, well, we actually technically, I guess we didn't really reduce it down completely until the final step, which resulted in 0, 1, 0, 0, 1, 0, 0, 1. So what's the final conclusion? Multiplying hex 36 times hex 93 results in hex 49. I know it seems like a lot of effort, and probably it is, to understand this process. It's not a complicated process. Mathematically, computationally, it's not an expensive process. It's just something that you're not familiar with because we haven't done this. You know, gosh, I can't even remember when I actually did polynomial math. Most likely it was in middle school. All right. So in the end, I'm not going to go through every detail here. I just kind of did one example. We are doing our vector calculation for that results in the 0, 4, basically. So we take 0, 2 times D4. This is how we distribute this mixed columns function and ultimately get the answer. 0, 2 times D4 plus 0, 3 times sorry, let me redo that. 0, 2 times D4 plus 0, 3 times BF plus 0, 1 times 5D plus 0, 1 times 3, 0. All right, so these are the binary representations of those values. 0, 2 times D4, which is ultimately going to be, so let me kind of, it's not drawn very well here. I should have put a little bit more information in here. This represents this here represents this represents this, and finally that represents that value. All right, so we understand how we're getting the binary values. 0, 2 is 0, 0, 0, 0, 0, 0, 1, 0, and delta 4 is 1, 1, 0, 1, 0, 1, 0, 0, which ultimately results in those polynomials: x to the 8, x to the 7, x to the 5, x to the 3. Because if I distribute this, x to the 8, x to the 7, x to the 5, x to the 3, do the same thing for the next, but I have to do both numbers, right? X to the 8, x to the 6, x to the 5, x to the 3, x to the 4, excuse me, x to the 3, x squared, x to the 1, and then x to the 7, x to the 5, x to the 4, x to the 3, x to the 2. So by the time I've distributed everything, it's kind of crazy actually. This is what I end up with in the end. Okay. And keeping in mind that any values that are any pairs get zeroed out, right? So I kind of reordered it based on the pairs. And in the end, this entire calculation gets reduced to x2, x squared. And x squared looks like this, 0, 0, 0, 0, 0, 1, 0, 0, which goes into that box. And then I do the same thing on this row for that value, that value, that value, and that value. And then I do the same on this row for that value, that value, that value, that value. And eventually I replace all the values. I mean, does that kind of make sense? I mean, it's something that you could easily do on paper as long as you felt comfortable with the polynomial math. It's not calculus, right? It's not a complex calculation. And again, like I said, I'm not really using the right terminology, probably, defining these variables the correct way. But this is definitely how the math works. And I'll do that for each column. So in the end, I end up with, this output, right? You got to remember where we're at. We're on the third step of our permutations, right? Easy enough. SBox, substitute bytes, shift the rows. Don't shift any bytes in the first row. Shift by 8 bits in the second row. Shift by 16 bits in the third row, and shift by 24 bits in the fourth row. This was the operation that required the Galois field and doing that polynomial math and polynomial reduction and whatnot to be able to do the columns, each of the columns. So now we're on the final step, which is really just like this step, right? Taking that round key, which is a derivative of the initial key, and XORing that round key with the output data from those first three operations. All right. So substitute bytes, shift rows, mix columns, and then we go through the finite math, and then finally adding the round key. The key is actually going to get modified for each round by dividing the key into 16-bit pieces, or 4 4-bit words, and then expanding each piece into 176 bits, which is 44 4-bit words. I actually have a diagram of the key algorithm, the key schedule algorithm, in this document as well. The key is arrayed into a square matrix, and each column is subjected to rotation, shifting the first column to the last. 1, 2, 3, 4 would become 2, 3, 4, 1, and then substitution of each word of the key using an SBox. The result of these operations is then XORed with the round constant to create a key that's to be used for that round. The round constant is going to change for each round, but those values are predefined. Each of the previous steps, except for the mixed columns, is only done for 9 rounds. Each of the previous steps, except for mixed columns, is only done for 9 rounds. We do the remaining steps for all 10 rounds. AES is a strong algorithm. It's not considered breakable at any time in the near future. So let's take a look at kind of the summary of this operation. So now we're talking about adding the round key. Whatever that key is, right? We'll look at the key scheduler, but I'm not going to spend a lot of time on how the keys are created. We know what an XOR operation is. So this was the output in round 1, after the initial round. This is the output of the state table after mixed columns. This is the output after we've added the round key for that particular round. Now, notice this round key is different than our initial key, right? Our initial key was 2 Bravo, 7 Echo, 15, 16. This is the round key for round number 1. And we just kind of go through that process multiple times. So we start by doing our XOR operation with the round key, which is the primary key, the main key that we've selected. We do our, so this output here is a result of this operation, this XOR operation. Substitute bytes, shift rows, mix columns, round key, XOR. This output is a result of all of that. Substitute bytes, shift rows, mix columns, XOR the round key here. This output is a result of all of that, and so on and so on. And then we do that multiple times, right? We do that actually 10 times. Well, technically 9 times, because on the 10th round, which is the final round, we're not doing the mixed columns. In the end, this is the ciphertext output that we receive. Based on all these changes and all these levels of confusion. And keep in mind that we're not even talking about the mode of operation at this point. We're simply talking about the black box that was listed within counter mode or output feedback mode or whichever mode of operation that we're using. So we also have that additional confusion with the plain text being encrypted and then the ciphertext output feeding back into the next round of encryption. Plus, on top of that, adding the initialization vector as well. All right. Now, I'm not going to go through this in detail. This just describes how each of the keys are generated. Expanded key is seen as an array of 32-bit words, numbered from 0 to 43. The first columns are filled with a given cipher key. That's this 2 Bravo, 7 Echo, 15, 16. That's kind of our original key. So step number 1, we do a rotate word. The 09 Charlie Foxtrot 4F3 Charlie goes into this column. We do that, do the substitute bytes, do our XOR operation. Basically this is just how we're deriving each of the keys for each of the individual rounds. All right. And if you look at each step, step 1, step 2, step 3, step 4, here's my substitution box. Or my substitution box up here. You can kind of get an idea of how this process is working. Step 5, step 6, step 7. So we go through 7 different steps just to generate the next round key. Basically is what I'm describing here. So this cipher key, which was our original cipher key, resulted in round key 1 by going through these 7 steps, which includes, transposition, substitution, and Boolean operations like XOR operations. Nothing really complicated, right? We're not doing any polynomial math in this case. So eventually we get to the point where we have established the round keys for each round. So we would have our initial key plus 10 additional round keys that would be used as part of our process of encryption. Okay? Alrighty. All right. A couple of other algorithms that we'll just mention briefly before we wrap up this section. The International Data Encryption algorithm, developed as a replacement for DES, 128-bit key, operates on 64-bit blocks, 8 rounds of transposition and substitution using modular addition, which is what we kind of talked about previously, plus multiplication, and bitwise exclusive OR operations. Bitwise exclusive OR means that we're operating on, or we're performing exclusive OR operations on a bit-by-bit basis. CAST, developed in 1996, 128-bit version, a 256-bit version. We have keys between 40 and 128 bits in length, 12 through 16 rounds of operation, depending on the key space. It is a Feistel block cipher with 64 operating on 64-bit blocks. And CAS 256 was submitted as an option for our candidate for AES. It failed. 256 CAS 256 operates on 128-bit blocks with keys of 128, 192, 160, 224, and 256 bits. The reason that it failed is because the Feistel algorithm is really inefficient. And one of the requirements for AES was that the protocol had to be much more efficient. It does 48 rounds, and it's described in RFC 2612. I'm not spending a whole lot of time on these because, well, frankly, you're not going to be really tested on these at all. But I want to make sure that you know that these different algorithms exist. Secure and fast encryption routine. Again, 128-bit blocks. It's a block cipher as well. And Blowfish, symmetrical algorithm, extremely fast cipher, implemented in as little as 5 kilobytes of memory. It is also a Feistel type cipher. It divides our input blocks into 2 halves and then uses those to XOR against each other. Blowfish operates in key sizes from 32 bits all the way up to 64 bits for input and output blocks of 64 bits. Twofish, also one of the finalists for AES, an adapted version of Blowfish, operates on key space of 128 bits, 192 bits, 256 bits, and operates on block sizes of 128 bits. It's a symmetric key block cipher as well. Oops, hold on one second. Sorry about that. But it wasn't selected ultimately. It did use like pre-computed S boxes, just like AES does. And it goes into different permutations. But it was slower. Twofish was a little bit slower than Rindell. You know, I'm not going to suggest that that was the reason it wasn't selected, but it was one of the finalists at least. All right. RC5, Rivest Cipher 5. Now, if you recall, RC4 was the algorithm that we were using for wired equivalent privacy. RC5 is also a symmetric key block cipher. Very, very simple algorithm. RC stands for the Rivest cipher, or Ron's code, if you want to call it that, because Ron Rivest developed it. And I think I misspoke. RC5 was not the proposal for the replacement for the candidate for AES. It was RC6, but RC6 was based on RC5. Operates on variable block sizes of 32 bits, 64 bits, or 128 bits. But the key size goes anywhere from 0 to 2040 bits. And depending on the key size will determine how many rounds of operation. Now, it's interesting that they mention a key size of 0 bits. And rounds from 0 to 255. I haven't really looked at it too much, but you know, what would be the implication of doing having a key of 0 and no rounds of operation? I guess that would just be the plain text, maybe. I don't know. It is a Feistel structure, has a Feistel structure as well. The original specification suggested 12 rounds of operation, but again, it can go all the way up to 255 rounds of operation. There's a bunch of modular additions that take place, a bunch of different exclusive OR operations that take place. but the Feistel network is what's used as the structure of the overall algorithm. There's a key expansion component, and there's other aspects to the protocol. But again, like I said, it's not important that you know the specifics of this particular protocol, just that it exists and you know what its history is and so on. RC5 is defined in RFC 2040, 4 different modes of operation. It is a block cipher similar to DES in electronic codebook with ciphertext blocks that result in the same length as the input. RC5 CBC is a cipher block chaining form of RC5. We talked about the different modes of operation. And then RC5 CBC pad combines the chaining with the ability to handle an input plaintext of any length. And the ciphertext will be longer than the plaintext by at most 1 block. And then RC5 CTS, which is ciphertext stealing, and it generates ciphertext that's equal to the length of the plaintext of any length. All right. The 12 rounds on the 64-bit blocks, there were some weaknesses in this. It was susceptible to a differential attack using multiple plaintext blocks. So for that reason, it was recommended generally that you would do 18 to 20 rounds to circumvent that, or at least to mitigate that vulnerability. You know, we don't see this protocol used too much today. All right. RC4. RC4 was the stream cipher that was developed for wired equivalent privacy. We do tend to use stream ciphers in wireless because of their implementation. We want to make sure that it has it's quick and very simple. RC4 had a lot of weaknesses though, which basically defined it as an insecure protocol. It was particularly vulnerable when the beginning of the output key stream wasn't discarded. We were using kind of non-random or related keys throughout the process. And that was actually one of the key weaknesses to that made WEP somewhat insecure. It is a stream cipher. Operates with key sizes from anywhere from 40 to 2048 bits. I know it says variable key length from 8 to 2048 bits, but I think generally speaking, most people will agree that 40 is kind of the low end for this particular algorithm. It only has 1 round of operation, being that it's a stream cipher. We're not going to have multiple rounds of operation. All right. Let's see here. What are the advantages and disadvantages of symmetric algorithms? Symmetric algorithms are very fast, which is why almost always they are used for bulk encryption. They're a secure method of providing confidentiality, some integrity in the sense that as long as the key is protected, will have integrity and authentication. But again, that's not traditional integrity and authentication like we talk about for an asymmetric process. The reason we define integrity, authentication, and integrity in this case is because we kind of assume that the shared secret key that's being used with the algorithm is kept secret, right? That's kind of the point. And as long as that key is kept secret, yes, there is some semblance of integrity and authentication. But again, it's not tied to an individual user. Many algorithms can be implemented in hardware or software key management is difficult in this case because we are using a shared secret key. Those keys have to be derived, they have to be exchanged, they have to be stored, they have to have a specific lifetime, and eventually they have to be destroyed. So that as the need grows for implementing these encryption algorithms, the number of keys are going to grow exponentially based on the implementation of multiple instances of this of these algorithms. So for example, if you had 10 users, that requires 45 keys. But if you have 1,000 employees, you're going to need 500,000 keys. That's that formula that we talked about, n times n minus 1 divided by 2, which derives the number of keys that we're going to have to generate. We're not able to provide non-repudiation of origin because the keys aren't tied to an individual user. We cannot do digital signing because, again, the keys are not tied to an individual user. The same key that I use to encrypt is the same key that I use to decrypt on the other side, and it's not tied to an individual entity. 2 or more people are going to share a symmetric key, so it is impossible to prove who altered data. If data was altered, there's no non-repudiation of origin. There needs to be a process in place to ensure that the key is selected randomly from the entire key space. There's no way to recover lost or forgotten keys. We don't want the key space or the key crypto variable to be predictable. Because symmetric algorithms require both users to share the same key, there can be issues with key distribution. We'll talk about Diffie-Hellman as a key exchange process in a little bit. Users must use out-of-band channels, like distributing the keys in person, mail, fax, telephone, courier, etc. I mean, this isn't really entirely true now. We obviously have electronic means for deriving and distributing keys. Although I would say that the Diffie-Hellman key exchange process is more of a derivative process. It's not a sharing process, right? We're actually still not, even with Diffie-Hellman, not sharing a key. We've come up with a method of deriving a shared secret key over a public channel. We'll take a look at what that looks like here in a little bit. The use of out-of-band channels should make it difficult for an attacker to seize both the encrypted data and the key. Certainly the encrypted data would be accessible because that's what's being sent over the channel. But if I'm using some sort of out-of-band method to exchange keying information or to derive key information, that would be separate from the transmission of the encrypted data. Other methods of exchanging symmetric keys, we use an asymmetric algorithm. That's essentially what Diffie-Hellman is. We also talked about that concept remember I drew the diagram with the web server when we were talking about public key cryptography. The web server would present its digitally signed public certificate to the client. The client would verify that identity and authenticate that endpoint based on the trusted third party, the root certificate of the CA. Being that the certificate that's being presented was digitally signed by the CA, but then in turn I would use that certificate to encrypt the shared secret key that we were going to be using for the bulk encryption for the transactions between the server and the client. So I demonstrated that. We'll take a look at that again in a little bit here. All right. What is an asymmetric algorithm? We talked about that quite a bit. Asymmetric algorithms are algorithms that use different keys, right? 2 different keys. They're linked mathematically, but they're mutually exclusive. Now, what does that mean? That means that there is no way for you to derive a private key if you know the public key. It's not feasibly possible, which is a really critical concept because the public key is by definition public. So if there was a way to derive or infer what the private key was from the public key, then it would defeat the whole purpose of the security. All right. For asymmetric algorithms, half of the key pair is used for one function. The other half of the key pair is used for another function. Depends on what your overall goal is. If your overall goal is encryption, I'm going to use the public key of the receiver to encrypt the data, which means that the private key of the receiver would be used to decrypt the information. If the goal is for non-repudiation of origin, authentication, and message integrity, then I'm going to encrypt the data with my private key, and you're going to decrypt the data with my public key. So the sender's private key, the sender's public key. It doesn't guarantee confidentiality because everybody has access to that public key. But the only individual that can create that data is the individual with the corresponding private key. So that's going to provide a level of non-repudiation and authentication and so on. All right, we will talk about Diffie-Hellman a little bit later on, a couple of mentions of that. For asymmetric algorithms, if a person wants to communicate using an asymmetric algorithm, the first thing that they would do is generate a key pair. This is done cryptographically with an application or PKI without user involvement. One half of the key pair is considered secret. Only the holder of those keys knows what that value is. This is called the private key. The other half of that key pair can be given out freely to anybody that wants a copy or requests a copy of it. This is referred to as the public key. We kind of already discussed this previously. Asymmetric algorithms are one-way functions, meaning that the calculation that's done in one direction is very simple, but in the reverse direction, it's practically impossible. It's not entirely impossible, but from a work factor perspective and from a feasibility perspective, it's pretty much impossible. The process to generate public keys is very simple, and providing that public key does not compromise the private key, because the process to go from a public key to the private key is computationally infeasible. Clearly, those keys have to be relatable. They have to be related to each other. We can't just have completely random private and public keys, because one key is used to do one thing, the other key is used to do the opposite. So they have to be related to each other. But it's just not feasible to take the public key information and somehow derive private key information from that. So what if I want to send a confidential message? Because keys are mutually exclusive, any message that gets encrypted with the public key can only be decrypted with the corresponding private key. So as long as that private key is secret, as long as that private key is not compromised, this provides a level of confidentiality. But it's important to understand, and this would more likely be on the exam than anything else, is what key do I use for what purpose? Do I use the sender's private key, the receiver's public key, the receiver's private key, the sender's public key, etc.? I don't know. Which one do I use? It depends on what your objective is with that cryptographic process. If confidentiality is the goal, I would need to generate the message and encrypt the message with the public key of the receiver, which, by the way, would have been shared with me in advance. Now, you might kind of think about that and go, well, if I'm encrypting with the public keys are public, I mean, doesn't that open up some vulnerability? And the answer is no, because the only way that I can decrypt that data is with the corresponding private key. I have to use the corresponding private key, which of course would be private. That's the whole point. So, and we'll see a pretty diagram that describes this in a little bit. but only the receiver has that private key. So only the receiver ultimately would be able to decrypt that data and view it. So I've got this plain text block that I want to send securely to the receiver. This is Alice. This is Bob. All right. So there has to be some sort of encryption process. I take Bob's public key, which I use for the encryption process, which results in ciphertext. Bob receives that ciphertext and decrypts that information. I should use public with Bob's private key, which then results in Bob knowing what the plain text data is. As long as that private key is not compromised or otherwise exposed, then that ciphertext can only be decrypted by Bob. All right. What is an open message? When messages are encrypted with the private key of the sender, it can be opened or read by anybody who possesses the corresponding public key of the sender. The reason this is referred to as an open message is because confidentiality is not our goal. We're not trying to hide the information. We're trying to incorporate non-repudiation of origin, proof of origin, and message integrity. So if I encrypt data with my private key, the sender's private key, anybody who has the public key can decrypt that information. But if somebody decides that they want to modify that information and then re-encrypt it, they wouldn't be able to do so because they don't know the private key. Private key is private. This is what we refer to as open message. The sender takes plain text block of data. They use the key material, which is, we'll call this Alice again, the private key of Alice, to encrypt the data, which results in ciphertext. And then Bob over here, the receiver, wants to decrypt that data. They're going to use the public key of Alice to do so, to decrypt that information. What we might refer to on the exam as a proof of origin operation. Proof of origin operation. All right. What if I want to combine these functions? By encrypting the message and then applying the proof of origin, we get the best of both worlds. So I take my plain text block of data. I encrypt that data with the private key of the sender. That's the proof of origin operation, which results in some sort of intermediate ciphertext. I then encrypt that data with the public key of the receiver. So here's Alice, here's Bob. The public key of the receiver, which is our confidentiality operation, which results in our ciphertext. When Bob receives this information, they are going to decrypt that information with their private key. And then they're going to verify proof of origin with the public key of the sender. So now we're not only applying confidentiality concepts, but we're also applying message integrity, non-repudiation of origin concepts as well, or proof of origin concepts as well. Make sense? Oftentimes, this is going to be the implementation because we want to really have everything in that transmission. So we mentioned RSA before. We didn't really get into the specifics of RSA. RSA stands for Rivest, Shamir, and Edelman. It's been around since the 70s. and it uses generally key sizes from 2048 bits all the way up to 4096 bits. Pretty typical. I mean, it's a relatively popular implementation of a crypto system for secure transmission. It is also one of the oldest ones. In a public key crypto system, the encryption key is public and separate, as we've been talking about, from the decryption key, which is the private key. An RSA system, or a user that's utilizing RSA, creates and publishes a public key based on two large prime numbers. And then there's some sort of auxiliary value that gets calculated in this as well. The auxiliary value is not really represented here. We see A and B equals C, and A and B would be in essence the prime numbers, the large prime numbers. All right. RSA is based on mathematical challenge of factoring the product of two large prime numbers. Prime numbers are only prime number can only be divided by one and by itself. The factoring is defined as taking a number and finding the numbers that can be multiplied together to calculate that particular number. For example, the product of A times B equals C. C can be factored into A and B. So 3 times 4 equals 12. So 12 can be factored into 3, 4, 6, 2, 12, and 1. Those are not prime numbers, right? So the RSA algorithm uses large prime numbers, and when those are multiplied together, it's exceedingly difficult to factor. So successful factoring attacks against 512-bit numbers, about 8,000 million operations or MIPS per MIP years, I should say. And if we're talking about a 10,000 or 1,024-bit number, exceedingly difficult. So the secrecy, or the security, I guess, of RSA relies on this practical difficulty of factoring the product of these two large prime numbers. We talked a little bit about that before. That's called the factoring problem. And then breaking RSA would be defined essentially as the RSA problem. RSA is a relatively slow algorithm. It's not going to be typically used to directly encrypt data. Most cases, it's simply going to be used to transmit shared keys that would ultimately be used for our bulk encryption or our symmetric encryption. So that's one of the things to consider. The RSA algorithm is broken up into basically 4 steps. We have a key generation step, we have a key distribution step, and then of course we have our standard encryption and decryption step. All right. I'm not going to get into the modular math and the modular congruence, as they say, for essentially the math involved for deriving the material, but we just want to have a general understanding of what are the components of an asymmetric algorithm. What are the fact that we use prime numbers, and in the case of RSA, those prime numbers are typically P and Q. And those would always be kept secret, of course. We would never want to divulge those prime numbers. The compute component, which is N typically in this case, is a modulus for both the private and public keys. And its length, and that's ultimately how we describe RSA, is expressed in bits, or the key length. Again, we don't need to get into the details of the math. So what is the Diffie-Hellman key, or Diffie-Hellman process, I should say? Diffie-Hellman is primarily used for key exchange, but what is that that process. So Diffie-Hellman key exchange process provides us a way to establish or at least share a cryptographic key over an open channel, over a public channel, and is really a critical element to bulk encryption and to symmetric cryptography. A key exchange algorithm is used to allow users to exchange or negotiate, and in this case it would primarily be negotiate, a secret symmetric key that should be used for bulk encryption, because asymmetric processes are not fast, they're relatively slow. They're not typically used for the bulk encryption. The Diffie-Hellman algorithm does not provide for message confidentiality, but is useful for applications like public key infrastructure. And it's based on discrete logarithms, a mathematical function based on finding primitive roots of a prime number, which we had talked about with regard to RSA. And I don't know why I did this, but there's the primitive root formula, which you will not need to know for the exam. Okay? I mean, think about what the goal is here, right? Traditionally, secure encrypted communication between Alice and Bob is going to require that they somehow exchange keys, but it has to be done in a secure manner. I mean, it could be technically a paper key list that would be actually physically transported, but that's not really very practical, right? The Diffie-Hellman key exchange method allows Alice and Bob that don't have any relationship, prior relationship, other than what their goal is, to jointly establish a shared secret key over the insecure channel. And then that key can subsequently be used as the bulk encryption key for our symmetric key cipher that we're using for the bulk encryption. This has been around for a long time, right? Mr. Diffie and Mr. Hellman published this in the 70s. I think it was 1975 or 76. It's since been updated, but for the most part, it remains the same. All right. Now, as far as the operation goes, Diffie-Hellman key exchange allows us to establish a shared secret key between two parties, Alice and Bob, in this case, for that secret exchange. Oftentimes, when you see this process demonstrated, we use paint buckets or colors to describe the process. So let me go to the diagram here. I did put the math in the diagram. So it's not going to be important that you understand prime P and generator G and primitive root of P and so on. So the paint buckets are here to demonstrate visually kind of how this process works. So I'm going to break down this process using those paint buckets. So we have Alice and Bob. They need to first agree on some arbitrary starting color. Okay? That arbitrary starting color doesn't need to be secret, but every time we do this process, it should be different. So in our example, this starting color is yellow. Okay? And it doesn't matter if Evil Eve in the middle sees that. It doesn't have to be kept secret. Subsequently, each person, Alice and Bob, would also select a secret color that they would keep to themselves. All right? That secret color, obviously, by definition, would be secret. And that would be orange for Alice and green for Bob. The critical part to this entire process is that Alice and Bob now need to mix their own secret color with the mutually shared color that they agreed on, which would result in, you know, a couple of different mixtures. Now I'm getting into where I don't know, I guess light blue from Bob's perspective and some sort of, I don't know, nude color or light pink color, whatever, for Alice. Okay? Now, if I was to tell you, if I was to give you a bucket of paint and say, hey, here's a bucket of paint, you unmix that paint and separate the colors so that you can represent the colors that I use to create that that paint. I didn't say that very well, but that would be very, very difficult to do. If I gave you a paint, you know, a bucket of paint that was green or blue or whatever, and I said, now tell me what colors did I mix to create this paint, it would be very difficult to do that. Extremely difficult to do that. Okay? Once they've done that mixing, they're going to publicly exchange those two mixed colors. So far, so good. Now, they're different values. We call it Y sub A and Y sub B in this particular case. Even if Evil Eve sees that information, doesn't really matter, because Evil Eve would not be able to derive the secret values or the secret X sub A and X sub B based on that, because it's just not computationally feasible. The final step is that each of them would mix the colors they received from their partner. Bob would mix the colors that it received from Alice, and Alice would mix the colors that it received from Bob with their own private color. In the end, because you've mixed essentially the same colors, the final mixture, which is that lovely shade of brown there, is going to be identical for both parties. Guess what we have? We now have a common paint. We have a common secret key. Now, I know it's these little boxes here, this orange and green box, shouldn't be in this Evil Eve column. They should kind of be over here in Bob's column and Alice's column. But the common secret, which, by the way, would be also in Bob's column and Alice's column. So this box here, Evil Eve does not see that box. Those are my private boxes. All right. If for some reason Evil Eve was listening to this exchange, they would only know the common color and the first mixed colors that we see. But it would be extremely difficult for Evil Eve to determine the final secret color, that lovely shade of brown there, which brings us back to the analogy of a real-life exchange with large numbers rather than colors. The derivative or the determination of those large values are computationally expensive. It would be impossible to compute in a practical amount of time, even for the powerful computers that we have today. All right, now if I was to go ahead and break this down to the mathematical, the cryptographic explanation, we are talking about things like multiplicative groups of integers with a modulo p. P is going to be the prime. G is what we call the primitive root of modulo p. Those values get chosen to ensure that the shared secret can take any form of 1 to p minus 1. So the non-secret numbers, like P11 and G7, P is the primitive and G is the primitive root of modulo P. And then we have some secret values as well. The secret values, the secret integers, X sub A, and in the case of Bob, X sub B. All right. So Alice and Bob kind of publicly agree on modulus P. In this case, it's 11, and base G, which in this case is 7, which, by the way, happens to be the primitive root modulo 23 of 11. Alice chooses her secret integer, in this case is 6. Bob chooses his secret integer, in this case is 8. Actually Bob sends actually Alice, excuse me, I apologize, sends Bob A, right, y sub A, which is G to the power of A mod P. All right, we can see the formulas listed there. Y sub A is equals G to the power of A, or X sub A in this case, mod P. And on Bob's side, Y to the B equals G to the power of X sub B mod P. All right. Modular math. We did a little bit of modular math when we started this cryptographic section. So Bob going to choose his own secret integer, in this case 8. It's going to send Alice X or Y sub B, which is G to the power of X sub B and mod P. And Alice is going to then compute S, the secret key. And Bob computes S as well. Now from Alice's perspective, it's going to be the Y sub B mod P. And from Bob's perspective, it's going to be Y sub A mod P, which then ultimately results in a shared secret key. In this case, no, the number is 3. Does that make sense? So we arrive at the same value. The only things that are secret in this entire process are A and B. P, G, G to the power of A mod P, and G to the power of B mod P. These are all going to be sent in the clear text. Obviously, we're going to be using much larger values than what we see in the diagram here. That's the whole point, is just to demonstrate this concept. All right, El Gamal, a cryptographic algorithm based on Diffie-Hellman, but includes the ability to provide message confidentiality as well as digital signatures. It was based on the same mathematical functions of discrete logs, and it consists of 3 components: key generator, encryption, and decryption algorithm. Elliptical curve cryptography, we'll spend a little bit more time on this because this is kind of mainstream. It is also a type of public key cryptography, but it's based on algebra. It's not based on discrete math. It's based on elliptical curves over what we call finite fields. Notice the second bullet point. The algorithm, which is too complex to explain the context, has advantages for strength and speed. Now, what would ECC be applicable for? Key agreements or key exchanges, digital signatures, pseudo-random number generators, and so on. And indirectly, it can be used for encryption by taking that key agreement principle and then using that with some sort of symmetric encryption scheme. And factorization algorithms use this as well. It is a asymmetric public key cryptographic process. Now, as far as getting into the scheme, the discrete logarithms that we use and the math that we use for the scheme, it's not really something that we need to get into in this section here. Elliptical curve algorithms have the highest strength per bit of key length than any asymmetric algorithm. The ability to use much shorter keys for ECC implementations provides savings on computational power and bandwidth. That would be the kind of thing
that you would be tested on? You know, what would be the benefits of using ECC as an asymmetric encryption algorithm as opposed to, say, RSA or DSA, the digital signature algorithm, or Rivas-Shamir Nadelman? Because you can effectively achieve the same or better results from a secrecy standpoint with shorter keys, would be the answer to that question. This makes ECC especially beneficial for implementations on smart cards, wireless networks, and other similar applications. Elliptical curve algorithms provide confidentiality, digital signatures, and message authentication services, which makes sense because it is an asymmetric encryption process, private and public key pairs. What are the advantages or disadvantages of an asymmetric key algorithm? It is possible to send messages across untrusted medium securely without the overhead of key exchange or key material. That would be obviously considered an advantage. What do they mean by that? Use the public key to encrypt. Use the receiver's public key to encrypt. Use the receiver's private key to decrypt. We don't have to exchange any shared secret key. The only thing that I would have to do is ensure that the sender would have my public key, but that could be shared relatively easily. We know that it already applies, or it already provides non-repudiation of origin, data integrity, non-repudiation of delivery, obviously access control. I'm trying to think of non-repudiation of delivery. How could we guarantee non-repudiation of delivery? That'd be a tough one to describe. I'm thinking about how to define that. It's not like we're providing some sort of sequencing or acknowledgments in this case. I suppose if you're using a public key to the receiver's public key to encrypt and the receiver's private key to decrypt, that would provide some sort of non-repudiation of delivery, because the only way that you were able to get access to the information was that you received it, because you would have had to use your own private key to decrypt it. I'm not sure what they mean by that definition or that specification. Asymmetric cryptography is extremely slow compared to symmetric. It is extremely problematic with speed and performance, and impractical for encrypting large amounts of data. There are much larger keys and much more complex computations, which makes it harder than dealing with smaller keys. Ciphertext output from asymmetric algorithms is also much larger than the plain text. With a bulk encryption algorithm, a block cipher, the ciphertext output is always the same size as the plain text input. Not the case for asymmetric algorithms. So it's not really effective for security of large messages, but it is effective if you want to employ integrity, authentication, and non-repudiation. Hybrid cryptography is really just the process of utilizing both. I described that when we were doing that discussion of PKI with the web server and exchanging asymmetric keys for authentication and proof of origin, and then using that asymmetric cryptography to establish and securely exchange our session keys, and so on. That's what we would consider a hybrid cryptographic environment. Symmetric cryptography for encrypting large files can handle the encryption and decryption process with very little impact. Asymmetric cryptography for the initial setup of the communication session through the exchange and negotiation of symmetric keys. I remember that process. You've got the web server. I send my public key. The client uses that public key to verify the authenticity of the web server, but also uses that public key to encrypt the
shared secret key that we're going to use for the exchange, and then I use my private key to decrypt, and in the end we both end up having the same key for bulk encryption. The symmetric key is only needed for the length of communication. Well, that's why it's called a session key, and oftentimes that key will have a lifetime. That lifetime will be defined based on one of two parameters. It'll either be based on how much data was encrypted with it, with that particular key, or what the lifetime of the key is based on a timestamp, right? Maybe the key is only going to be valid for 8 hours or 4 hours or whatever. So the message gets encrypted with the symmetric key, sent to the recipient. And then, actually, let me go back. Well, let's just go to the diagram, right? Because the diagram will show us visually what that looks like. And we've seen this already, just in a kind of a different format, right? I have plain text data that I want to send, which in this case, using HTTPS. But before I can get to this step, I need to do this step first, right? So let's say, for example, this is the web server. The web server is going to present its public certificate, public key, which is right here. I'm going to generate the key that's going to be used for my symmetric encryption. We're going to encrypt that with the public key of the receiver. That's my session key. And then I'm going to decrypt that with the private key of the receiver, which is the web server in both cases. Then I can use that that session key to do the actual bulk encryption. So I need to send plain text data. I'm going to encrypt it using the symmetric key, which is my session key, and then we'll decrypt that data using that same session key. Make sense? All right. Probably could stand to redo this diagram. It's a little bit confusing, but. So what is a message authentication code? We actually talked about this as well previously. A MAC, which is identified generally as a tag, is just some piece of information that provides us the ability to authenticate a message. Basically to confirm that that message came from a particular sender. We're not talking about confidentiality. We're talking about authenticity of origin. But then there's also a secondary part to this, which is integrity. The MAC value is what actually is used to protect the message's data integrity and to provide that authenticity. The term message integrity code is sometimes substituted for this particular term. All right. But to distinguish the use, to distinguish from MAC as in media access control address, MAC address, MIC is often used instead of MAC, right? To refer to a message digest. So you may see references to MAC or you may see references to MIC, but it basically is the same thing. The MAC as a cryptographic checksum is a small block of data generated using a secret key that we append to the message. The message is received. The recipient can generate their own MAC using that secret key. Why is the secret key important in this case? We talked about this previously. If I was just doing hashing, there would be no protection, right? If I was doing an MD5 hash and I had my data and I took my data and I ran it through the hashing process and I got the digest, right? And I sent that digest along with the data, who's to stop anybody in the middle from intercepting the data, which is in the clear, because we're not providing encryption, throwing away the old digest, the original digest, modifying the data, and then recalculating a new digest. Everybody knows how MD5 works. Everybody knows how SHA works. So there would be no guarantee of integrity. So it's extremely important that we have some secret material that goes into that process. And that's what this second bullet point is representing. Messages received, the message is received and the recipient, sorry, let me go back to the first bullet point. A cryptographic checksum, which is a hash, is a small block of data generated using a secret key to append to the message. That's the key element here. There has to be some secret sauce. Otherwise, there is no guarantee of integrity. It still doesn't provide authentication because generally that secret key material is well, I mean, in PKI it doesn't have to be common between the parties, but in some cases it can be common between the parties. The message is received. The recipient can generate their own MAC using that secret key to know the message was not changed. In other words, we're going to receive the data. I have my secret keying material that was stored locally. I know what algorithm we're using to generate the hash. So I basically do the exact same calculation. And if the MACs match, then I know that the data was not modified. So again, this is only going to give us assurance as long as nobody has access to that secret key. The MAC is a small representation of the message. That's by definition how hashing functions work. We take a variable length input data, block of input data, and we always generate a fixed length output hash of that data. So given the MAC and the message that generated it, because the message again would normally be sent in the clear, it's impractical to find another message that would generate the same MAC. That would be referred to as a collision. We talked about that previously as well. MAC is generated using the DES algorithm in CBC mode, and secret DES keys are shared by the sender and receiver. The MAC is the last block of ciphertext generated by the algorithm. The block of data, which is typically 64 bits, is attached to unencrypted messages and transmitted to the far end. The previous blocks of encrypted data are discarded to prevent attacks on the MAC. The receiver can just generate its own MAC using a secret DES key shared to ensure message integrity and authentication. I mean, the key space, the keying material doesn't have to be significant because we're only talking about protecting integrity, though I will say that most hashing processes don't use DES anymore. All right. So what is HMAC? Not an entertainer. HMAC is called Keyed Hash Message Authentication Code, or what we call a hash-based message authentication code. Okay. It is, in essence, a special type of MAC that uses a cryptographic hashing function. But, and this is the important piece, it also incorporates the use of a secret cryptographic key. All right. Now, HMAC can provide at least some level of authentication because we have a shared secret. We're not using digital signatures like we would with asymmetric cryptography. So HMAC allows us to trade the need for having complex public key infrastructures by relegating or delegating the key exchange to the parties involved in the communication. They would be responsible for essentially establishing the trusted channel and somehow agreeing on a key prior to doing the communication. All right. Now, in this case, we might use something like SHA-2 or SHA-3, the secure hashing algorithm, for the calculation of the HMAC. And it has, relatively, strength, has good strength. All right, two passes of the hash computation. The secret key is going to be used to derive the inner and outer key, and then the first pass of the algorithm is going to produce an internal hash, which is going to be derived from the message and the inner key. And then the second pass is the final HMAC code, which is the digest that gets outputted from the system, which is derived from the inner hash being hashed with the outer key. All right. You don't need to know that for the exam, but there are multiple hash functions: MD5, SHA-1, SHA-224, SHA-256, SHA-512, 384, etc. All right. All right, well, that officially ends our discussion of cryptography. We're still not done with the domain, so